Okay, right. I think we will start. So good morning, everyone. Welcome to this 150th edition of the Zak World of Facade conference series. My name is Ahmed. I'm part of the organizing team here at Zak. I'll quickly introduce the Zak World of Facade conference series to you. So we've been doing this event since 2012. We finished around 149 editions. This is the 150th one. This is the second one in Toronto and the fourth one in Canada. We did our first one in Toronto back in May 2022. We did Vancouver and Montreal last year. Back to Toronto again this year with a newer, fresher, bigger agenda. These events are all across the globe, from New Zealand up until Canada. The way facades are designed, engineered, installed in all these regions are completely different. So for us, it's a custom agenda at every event. We need to adapt to what the local city, what the local region demands for. In some places, it's about cost. Some places, it's about energy. Europe is all about refurbish, reclad, adaptive reuse, carbon. Middle East is all about complex geometry, giga-size projects. So it's very interesting for us to curate these events in these respective places which are more relevant to the respective region and zone. It gives us an edge in terms of bringing people from different parts of the world coming into another region and sharing their expertise and what's happening. These events are not possible without our event partners. I'll take a couple of moments to thank all of them, starting with our presenting partner, Rayner's Aluminium. Rayner's Aluminium is from Belgium, one of the world leaders in aluminium door, window, curtain wall systems. They're present here in Canada since many years. Toronto is their North American head office for their operations here. And they have been a great supporter of this conference series here in Canada and also North America. We'll start with our associate partners, AGC Interpaint. AGC Interpaint is one of the leading value-added glass processors, coaters in the world from Germany. Interpaint Group, formerly known, now part of AGC. BM Windows is one of Asia's leading facade contractors out of Vietnam. They are now exporting their engineered unitized solutions globally, including Canada. Cosentino is a Spanish company, part of the, their product for the facade is Decton, which is a non-combustible cradle-to-grave cladding product, which is now picking up a lot of traction and now being used as a solution against conventional composite panels. China Southern Glass, again, one of the leading value-added glass processors out of China with their own in-house coatings, exporting glass globally. EOT is from Germany, so EOT's rain screen cladding division, where they have the fixing systems, are exhibiting here with us. Engineered Assemblies, a Canadian company, the distributor of cement boards, ceramic cladding, terracotta, you name it. They've got a wide range of slate. They've got a wide range of cladding materials for the facade. Equitone is a European company. They are part of the ETEX group. They have a fiber cement cladding product, which is again a non-combustible cradle-to-grave product. Euro Architectural Components is a Canadian company. They've got glass hardware, fittings, railings, and other accessories for glass and the curtain wall. GlasCurtain is exhibiting here with us for the first time. They've got some interesting solution, which is basically a fiberglass-based door-window facade system, which is again a newer alternative to your conventional curtain wall materials. Guardian Glass is one of the world leaders in coated glass solutions, needs no introduction. Janssen is from Switzerland. They are world leaders in steel door-window facade profile systems. Mitrex Cladify, it's a Canadian company. They're one of world leaders in building integrated photovoltaic solutions, which is again picking up a lot of traction now. They've got a wide range of varieties and finishes in BIPV. Northern Facades, part of the Flynn Group, Canadian, again into rain screen cladding, fixing systems, and other value-added accessories for facades and cladding. Ontario Panelization, a Canadian company. They're into fabricated panels, into also BIPV photovoltaic solutions and other fabricated solutions for ventilated facades and cladding. Saint-Gobain Glass, again, global leaders in coated glass solutions. They are here with their new low-carbon glass, which they are promoting at this event. Sound Solutions, another Canadian company, distributor of leading European materials, NBK, terracotta, they've got ceramics, they've got synthetic stone and a lot of other value-added products, membranes also, so lots of solutions with Sound Solutions. Walker, again Canadian, got a lot of value-added glass products, bird protective glass and a lot of other interesting stuff. And of course, our next few events here in North America, we're doing Austin next month. We finished Miami last week, so we're coming from Miami, so Austin's next month. We go back to Vancouver. Vancouver was a surprise for us, turned out to be a very, very large event. There's lots happening in Vancouver, so we are returning much earlier than originally planned. And of course, our biggest one is the New York event, which is a 600 plus people event. Split into 3 tracks, so that's our flagship event here in North America and the second largest in our global series after London. So these are what we do. These events are again networking events where we invite people to talk about the way design, engineer, install facades. It's all about storytelling. Every person has a different story to tell. It could be a project, it could be a product. So this is something which we go around and try to unite people. All our associate partners have exhibit booths outside in the exhibit area. That's where tea, coffee, lunch, and the post-event networking will take place. Please do drop by their booths and tell them a hello. They've been extremely supportive all across these events globally. We have recorded today's event, so those who have given us permission to share their presentation with you will share the video recording of their presentation via a YouTube link a week from when we complete this event, along with a feedback form. So once you're able to fill up the feedback form, you will get access to the YouTube link. We won't take any questions today. We'll go straight into the agenda. We've got a packed agenda for sessions. Very interesting set of speakers today, talking on a wide range of topics. So my role ends here. I'd like to call upon today's event host. I'd like to call upon Luka. Where are you, Luka? So Luka is from Purpose Building. He's going to be hosting today's event, and he's going to be introducing all our speakers and ensuring we don't go over time. Luka, over to you. I'm done. Thank you.
Thank you. Good morning, Toronto. Okay, one more time. Good morning, Toronto. Good morning. All right, much better. Thank you very much. I am your host and MC for today. Just tell you a little bit about Purpose Building. We founded the company after nearly 20 years of doing sustainability consulting about 5 years ago with a very simple mission: to accelerate real estate to more planet-positive performance. We focus on new development, existing building, and portfolio strategies in nearly all sectors, and tend to work with some of the largest real estate companies in Canada. And the way we succeed at our mission is to focus on what matters most. And I'm going to be sharing with you 3 insights today, as over the course of the day, about stuff that we've been learning about facades. Performance related, what matters, what doesn't, what to focus on, what we spend a lot of time on. Secondly, we inspire confidence in teams to do something that we haven't done before. We have a tremendous challenge ahead of us. All of you in the industry are in the driving seat of creating climate action, but we need to go faster and we need to go farther than we've ever gone before. So the opportunity and the challenge is monumental. And lastly, we create compelling materials that actually motivate action. A lot of us have written lots of reports over the years that tend to sit on desks and shelves. That's not what we're about. We need change, we need it now, and we need lots of it. So I'm going to do 3 tips. The first one, just show of hands. I'm going to ask, what do you think matters most in terms of reducing thermal energy demand? How much glass we have in a facade, or the performance of that glass? First, who thinks glazing ratio is the ultimate driver of demand reductions? Handful. What about glazing performance? More. Okay, you're right. And in particular, what we've been focusing on are all the tiny thermal bridges that can make or break a product. And so there's lots of great frames, lots of great products out there to check out. Please, please don't get into design development, or for God's sake, don't get into working drawings without having lots of conversations about how those walls and windows and all the various components of the facade fit together. That's where the performance is made or broken. So that's number one. I'll share a couple of more when I'm back up here later. We're going to launch right into it. Our first speaker is Alex Josephson, president of Partisans, and he's going to talk to you about improbable facades made possible. Come on up, Alex.
Thanks, man. Hey, everybody. I'm going to the OAA conference after this. Who else is an architect going to the OAA conference this year? 2. I'm sorry, the powers that be are going to be upset at me. I'm going there afterwards. So I'm just super grateful for the invite. Thank you to Susan and Ahmed. And it's amazing to see the crowd here today. Clearly, Zak has an audience. So why do we call ourselves Partisans? We call ourselves Partisans because I think that creating great architecture takes a village. You can't do it on your own. It's not about a singular ego. You have to be super passionate about it. And the topic of improbability is always sort of like nagging at me because some of the projects we're doing haven't been built yet. And I think today is also about discussing the technical elements. It's not just about a pretty form. It's about executing things that people don't think you could really do. But if you come together with groups of people like you in the room today, I think we can make anything happen. And I think the world's becoming a more beautiful, high-performance place as a result of that. So our projects range from everything from products to skyscrapers and master plans, affordable housing, purpose-built apartments. Our client Fitzrovia recently said, you know, apartments are tough. Can you make one beautiful? We said we could try. And so the question is, in Toronto at least, we came up with this fictitious tower called the WTF tower. You can you can translate it. WTF for Toronto, what are we doing? We know what they're doing in Shanghai, and we know what they're doing in other places. And I had an interesting conversation with a glass engineer once from Eckersley O'Callaghan, and I'm super excited to see Lisa's presentation today after mine. They were like, yeah, in New York, you can kind of do probably 25% of your facade really interesting and custom. Calgary, maybe 4%. Toronto, maybe 7%. So, you know, really, in the end, these buildings are financial instruments. They have to make sense financially. And we've tripped up a lot in the beginning 10 years ago when we started working with developers. And we have to basically come up with creative sleights of hand in order to make these things possible. So I'm going to go through 55 Yonge, as well as Elm Street and the Rolex store we just finished. So here's the financial spreadsheet in 3D. It's 70 stories. It's cut at the top so that you can take advantage of every inch possible out of the sun and solar impacts on shadows. And the question is, what do you do with this hulking mass? How on earth do you start to tailor something that could at least be appreciable as an impact on city building, high performance, as well as responsive to the environmental realities and context of the site? And we thought about how high performance textiles, high performance weaves are really advancing in other industries such as automobile, aerospace, but also fashion. And we thought, well, how can we do this in the context of architecture? How can we start to design for high performance, but also beauty and control cost? How do you create architectural lingerie, basically, to hide the financial model and make it beautiful and fulfilling for everybody involved? And so 55 Yonge really is like a dress for a mass. And the way we make it possible is the places that you see that are very curved are actually just trellises. So it looks like this is all envelope, but the stuff that's doubly curved is actually It's actually just a trellis. And so what that allows you to do is you have these conditions in the building from the grade to the transition between the podium and the tower and then the sky houses at the top, where basically the performance of the envelope and the form of the building are dissociated, right? And it also creates shading, especially for the west side of the building. The analysis of fenestration and coverage in at least Toronto for TGS is important. I know that no one put their hand up, but the less glass, the more insulation, the higher the performance. I don't care what you say. You can use triple glazed all day long, but you have to get your ratios to a point where the performance actually hits the targets. And until you show me a cost-effective quadruple pane full curtain wall, I don't think you're gonna surpass the performance of insulation, unless anybody can prove me wrong right now. So the idea of this building is that it's a curtain wall with a high-performance responsive, what do you call jewelry on it, that actually is different based on the exposure to the sun. So you have the floor plates, the curtain wall system, and then the actual panels that form the textile, the architectural textile. There's certain conditions where there may be balconies or Juliettes, and we've engineered these into the actual system as part of the curtain wall. We're working with a local curtain wall manufacturer, I'm sure you can guess who, potentially on the execution of this. But we've talked to people globally about how we can procure some of these more exotic geometries in the panels. Everybody who looks at this is just like, I don't get it. Like, how does this make sense? There's so many different panels. But the reality is there's actually only a few different conditions. And there's a highly repetitive nature to the textile, makes it something that you can actually build. The first way we do this is you take the massing, we find our conceptual approach, and then we panelize it using different scripts that we've written in Grasshopper to actually formalize and output the drawings for each panel. So what we do is we algorithmically generate each panel while actually baking the entire building at once as a model. So what you have are a system of scripts where the entire facade is broken down from its earliest stages to analyze how many panels there were. When we first did it, the number of different panels was extraordinary. It was like thousands. And through the process of weaning down and actually economizing on geometry and making some tough choices, you can actually get to a viable panel makeup. So this was sort of, I would say, halfway through. We got to about a 50% ratio where 50% of the building was only 2 or 3 panels. We're now at 78%. So I think the magic on these is to really take a project, allow it to be as ambitious as it possibly can be, and then use technology to actually spin down to a point where everybody's happy. The facade manufacturer's happy, the client's happy, the construction manager's happy. The elements of the project that are complex are isolated from the panels that are more repetitive. But we can't do this without Grasshopper, and we can't do it without algorithmic sensibilities to the process. Elm Street. So again, here's the financial model. And the question is, how can we innovate? I've always loved the revision cloud in architectural drawings personally, so this is our revision cloud. The concept is, how could you create a kind of articulated building that feels like a cloud or an organic element that's growing from the ground? The issue with this is that you get a huge number of different components. This is actually, instead of a curtain wall, this is a unitized just window insert with solid panel. And with this project, we've started with this. It was, again, about 50%, and we're now about 80% 2 panels. And so you start to get to economies of scale and repetitiveness that allow the project to actually be viable by making sacrifices that are minimal, but at the same time preserving the concept. All of these things, like the detail of articulations of mullions, go through a process of value engineering, essentially. So, for example, this component's been thrown out, and in exchange, we get a reveal on the concrete cementitious panel that's built out of molds. So this project is really about working with mold makers and designing molds so that they can last, but also trying to create articulations within the art of casting versus assembly of aluminum panels or jewelry. And then the windows themselves fit in like just an insert, and they can be installed from the inside. So all these things are essentially run through the process of what you'd call prototyping, and the goal is to get to a point where the repeatability and the number of unique panels is reduced to almost, it has to be within 5, in our experience, to be financially viable. We're talking about money a lot today. We're supposed to be talking about climate, but I think they're related. And then you can see how the system comes together, and there's backer wall behind. And this is how it articulates in 3D. And we're very interested in working with different materials. The idea that everything has to be a curtain wall, or you need to focus on one or the other, I really love the idea of working sculpturally and being able to really work with different kinds of experts and fabricators all over the world, in this case, mold makers. We've even talked to some companies that would have liked to have done this out of metal, but I mean, with respect to these forms, I think that mold making is a fascinating approach. Toronto's doing a lot of precast. I think a lot of it's very beautiful, but some of it can be very thick, and the question is, for this project, how could we get the thickness down? Because you start to get a lot of mass, and then that's a lot of embodied carbon. Our last project I'm going to show you today is a kind of first experiment with this. It's the Rolex store. This was the existing building, and I think this is an adaptive reuse as well as a story about the regeneration of Toronto's retail make-mile. This building, built about 50 years ago, has a classic kind of fin system, not very well loved. Bloor Street in the last 10 years, before the last couple of years really, the pandemic, had been, I would say, neglected or not focused on. And the question was, for our client, RDV, who's been there for 50 years, how do we create a new facade, a new identity for the entire base of this building? And how do you do that being inspired by the jewelry that they actually sell? And so when I think of watches, I think of, or in the case of Rolex, I think of the magnifying lens, I think of curved glass. The curved glass got engineered out of this one. But I think of links. And so all these little details really inspired how we would approach the building and how to link itself to the existing facade. And instead of turning our back on it, making the existing facade performative in some way from a design perspective. This idea of adaptive reuse doesn't mean you have to replace the entire building. I think you can do something that enhances an existing facade or increases its aesthetic performance. So our process is really related to model making and mold making. We did several dozen different molds, several dozen different patterns. We worked with North Glass in China to do a series of experiments around curved glass. It's funny, every time we try to put doubly curved glass into our projects, the clients, especially with doubly curved glass, the clients basically say, well, how many extra pieces do we have, and how do we insure it, and how do we replace it? And it becomes a bit of an insurance, a circular discussion around insurance versus, like, do you want the glass or do you not want the glass? And I find that in Toronto, at least, we have these discussions a lot more than other jurisdictions. I'm not sure why. I think it might be cultural, but the issue of using curved glass seems to kind of be limited to like a one dimension of curvature, whereas we're interested in a doubly curved installation. The mold making process involved modeling the possibilities in 3D, building plastic and silicone molds, creating different versions of the facade, and then executing models. On this project, we also work with Arturo Tedeschi in Milan on the algorithmic qualities of the patterning. We eventually settled on not mold making, but actually milling this out of stone. And we love stone because not only is it a natural, authentic material, it turns out it's very sustainable. We had two options. We could precast this with concrete or with a kind of EFIS composite. And we thought about doing that with our team in California. But in the end, the client decided, you know, we're really interested in stone. We love the way it feels. We love the way it looks. And so we ended up working with stone. The question was, okay, we're going to work with stone. How do you install a 2,300-pound piece of stone on a 4-foot hoarding in downtown Toronto on a building that has to be retrofit? And I think that the technicalities around logistics on retrofit become a really big issue when it comes to just the practical realities of the city. We had to build a special scaffold to actually boom and slide the pieces in within the 4 feet allowance of hoarding. And I know this sounds like nerding out and kind of like funny, but the idea that the hoarding is sort of the tail wagging the dog on the maximum size of a piece of stone or material or glass that we could bring into the project was sort of a fascinating project unto itself. So we ended up having to design with the mason and the CM, all these sort of weird ways of getting the stone in without having we couldn't really use power machinery. We had to use hoists. And then the idea around performance. So we ended up with a double glazed facade. We could have gone with triple glaze, but in the context of retail, it was just decided it was too expensive. That being said, this was a huge jump in performance. This was basically just a single pane tempered facade before. The algorithmic qualities of the surface were worked out together in Grasshopper. We're super keen about the potential for Grasshopper to not just be an organizational and geometric modeling tool, but a surface generation tool as well. It's fascinating to see what the possibilities are also of AI and the integrations within Grasshopper to control surface textures and qualities so that you can actually invent a surface. So the accuracy of this with respect to lining up the existing facade with the new facade was kind of interesting. The old facade, as much as it looks repetitive, is off by about a half an inch to an inch from each panel. So our point cloud analysis in advance and our surveys basically gave us this information. We fed that into our model, and then each panel was milled so that it perfectly aligned with the existing facade. And then the weather flashing between the existing curtain wall was coordinated with the edge of our stone. The inside of the glass actually has a ventilation system all around the glass, not just in the bottom. So the air is forced across the glass on the inside in 360 degrees around the entire system. So it's basically like, instead of it just being a vent at the bottom, it's blowing all the way around. And we think that that's going to enhance the performance and make these panels last a lot longer. In Toronto, we have a really big issue with salt. A lot of the buildings in Toronto deteriorate at grade for the first like 6 inches to 10 inches because of salt in the winter. So we chose about 10 inches of Quebec granite for this. Turns out cutting granite is really hard. It took about 6 months for them to mill these. It's about 80 pieces in granite, and it took 6 months for the actual CNC guys in Quebec to actually cut these. Again, another logistical issue around CNC and stone is the timing and staging of the stone in production in advance of installation. We found that the lead time for stone needs to be at least 6 to 10 months. something in that range in order to really deliver just in time. And then this is the outcome. We're super satisfied with it. Integrated lighting. And that's it. And I have 5 minutes left. Do we have questions? What are we doing? Thank you, guys.
Quick show of hands. How many of you know what EPDs are and have done life cycle analysis of embodied carbon on your facade products or designs? Okay, that needs to change. If you make products and you don't have EPDs, you're behind the times. If you're an architect and you don't know the embodied carbon of the things you are specifying and designing, you are not in a leadership position. We need to do better. We've tackled operational carbon. We're doing great, especially in Toronto. We need to tackle embodied carbon next. So that's your challenge, that's your homework. Next time you come here next year, I want to see way more hands, okay? Okay, the third presentation, we've got Ravneet Saini from Saint-Gobain. Come on up, please. Oh, and the title, Advancing Sustainability. Perfect topic. I love that segue. It's like I planned this.
This is working? Okay. Thank you, Luka. Good morning, everyone. Are you all able to hear me well? Okay, perfect. We start from there. Thank you very much for joining me today. My name is Ravneet Saini, and I want to say what a great start to the Zak. We are all talking about glass, so we're very happy about that, and we have to see what more we can do to make it a more sustainable future for all of us together. So today I will talk about the world's first low-carbon glass that is available now in the market, and we will delve into how this was invented and what went into the making of this glass. So I am from Saint-Gobain. At Saint-Gobain, the purpose is to make the world a better home. Our core is that, our principle is that, to develop a lot of research into producing products which are more sustainable. And there are a lot of possibilities that are available today. So before I get into how we prepared the world's first low-carbon glass ORI, let's watch a quick video on what is available and what is possible today.
Build. Build to make dreams come true. Build to provide shelter, to protect the ones you love. Transforming materials, shaping them, giving them form. Build. Build with care. Build for the long term. Build for change. For over 3 centuries, Saint-Gobain Glass has been bringing extraordinary dreams to life, constantly innovating to offer the products you deserve for your project. Now present all around the world with 13 manufacturing sites and a strong international collaboration. Wherever you are, our experts work with you to facilitate the shift towards sustainable construction with glass solutions that deliver sustainability and performance. A solar and heat control range allowing the perfect combination of temperature and daylight. The world's first low-carbon glass with a verified environmental product declaration. A temporary surface protection on to-be-tempered coatings that eases its processing and increases productivity, reducing the environmental impact. A full range of exclusive solutions to meet the growing demand for bird-friendly glass and glazing. Saint-Gobain Glass supports you and your customers all throughout the project, even from the start when it's just a drawing. Our digital solutions help you find the right product and bring your dreams closer to reality. Dream. Transform. Impact. Saint-Gobain Glass cares about building better for people and the planet.
So we've taken some really ambitious goals. By 2025, the idea is to reduce the carbon emissions by 20%, and eventually leading on to being a nearly zero carbon emissions by 2050, which means we have to act now. We have to have our solutions and products which will lead us to a net zero carbon emission manufacturing. So if you look at the full manufacturing of a particular product, in this case, I will take the example of glass. So the different stages involved, starting from the raw material extraction to the end of life. And at each stage, there are carbon emissions. Either these carbon emissions are categorized as embodied carbon, or these carbon emissions are categorized as operational carbon. Now, operational carbon takes place during the utilization of the building. Let's take the example of glass. When you use a particular IGU, it goes onto the facade and then the building runs. So that carbon emissions they are called operational carbon. Everything else is embodied carbon. Now, because we are developing so much, and I speak not only for glass or all the manufacturers, but in the building construction, we are putting in efforts to make products more energy efficient. So thanks to that, what's happening today is the operational carbon is reducing for the buildings. Now, this presents us with the challenge and opportunity to work on the embodied carbon and bring the embodied carbon down. So this is where we stand right now. The buildings contribute to 39% of the global greenhouse gas emissions. In 2020, presently, the situation is that out of the total carbon emissions, operational carbon take up 72% and the remaining is embodied carbon. However, because we are developing really highly energy efficient products, by 2050, we anticipate that this is going to be an even split. Now, let's just consider the facade of the building. So if I just consider the outer shell, the facade, it contributes anywhere between 10 to 20% of the embodied carbon of the whole building. So what Saint-Gobain did together with Arup in partnership, we said, let's do a study to understand what are the carbon footprints of a facade, and specifically, what is the significance of glass in contributing towards this carbon footprints. Once we are able to understand that, as glass manufacturers, we'll be able to see what actions we can take to considerably reduce the embodied carbon emissions of the building. So the first step was to understand what are the different types of facade systems that are available. So from one being 100% double glazed unit to a steel frame system with small windows or a brick system. So we took length and breadths of different types of typical facade type systems that you would use. Now the next step was, now that we have identified the facade types, let's do a material breakdown. Let's see for each facade what materials go onto the facade, and that you can see in the chart here. So on the top of the chart, you can read what are the different kind of materials that are going into the different facade types. So once the materials were identified, the next step was, now let's do a breakdown that how much is each material contributing to the carbon emissions of the total building. So we did a whole study, and I invite all of you that this full study is available online on Saint-Gobain Glass to read the full analysis and the report of how this was done. So once this was done, and we split into carbon emissions of each product on the facade type, then as a glass manufacturer, it becomes important for us that glass is ranges anywhere between 24% to 60%. So it's a huge portion of the facade that it takes up, and hence it is our responsibility to produce products, to produce solutions which have lower environmental impact for the future than to build better. So now, these were our findings in summary, in a nutshell. First, glass contributes anywhere between 4 to 12% of the total carbon emissions of the building. When I say carbon emissions, I'm talking about embodied carbon. Facade contributes anywhere between 10 to 20% of the total embodied carbon emissions of the building. Today, though operational carbon is high at 72% of the total carbon emissions, tomorrow it is going to be an even split. So our mission is very clear. The goal was very, very clear that you need to develop a product with lower carbon emissions. However, now the challenge is, now this has to be produced on an industrial scale. There's so many buildings that we're doing worldwide, not only one manufacturer, but everybody. So this huge volumes we have to produce, keeping the aesthetic same, keeping the quality same, keeping the performance same, but you need to come up with a solution which has lower carbon impact. So you have to change your manufacturing process altogether. That has been going for years and years now. Saint-Gobain has been producing glass for over 365, 370 years. So you have to make changes in that production so that now the glass that you produce has all the performance, aesthetics, and quality, but it has lower embodied carbon. And today, as I stand here with all of you, I'm really proud to be associated with Saint-Gobain and present to you the world's first low-carbon glass. That is, the good news is, it's not just in the presentation, it's there. It exists on projects, which I'll just talk about in the coming slides. Now, a quick, short story time here. So Saint-Gobain, it's a French manufacturer. We are here in Canada. So what inspired the name? So for a low-carbon glass, why would you name it Wright? And that was my question as well when they presented Wright to me. So Wright is derived from a word called Horai. That was a Greek goddess, and this signifies the change of time or change of season. And we say that change is needed right now. If we need to build better, if we need to be more sustainable, we have to change. We cannot be in the same situation and expect different results. So we have to change our manufacturing. And Wright, the low-carbon glass, it opened doors for the market for decarbonization so that we produce better and we produce glasses with lower impact on the environment. So now what exactly changed? What is low-carbon glass about? So there are two essential things that we need to see here. The first one is recycled content. We all, so typically if you see, a glass has anywhere between 20% or upwards of recycled content, but a low carbon glass has close to 64% of the external color of the recycled content. So because of this recycled content, the carbon emissions are reducing. And as Lisa was mentioning in her presentation, in Saint-Gobain, we've done this whole channel. We've prepared the channel where we collect the colored, the broken glasses so that we are able to feed into our manufacturing process, and we have the cullet available. If we don't have broken glass available, we won't be able to produce low carbon glass. So that is one initiative that we've been taking. The second one is glass there are a lot of raw materials in glass, but do you know the key raw material, the major raw material? It's sand. It's the same sand that you find at your beaches. So sand is one of the biggest raw materials, and the first step that you need to do when you produce glass is to melt sand. Now you can't melt sand at lower temperatures. You need to go as high as 1800 degrees Celsius. Now if you need to have such higher temperatures, you need fuel to burn. Fuel to burn to reach these higher temperatures. So the second step was, let's switch to renewable energy sources and considerably reduce the carbon emissions during especially the melting process during the production. So these two steps that we are implementing today, what it has resulted in is considerable reduction in the carbon emissions. And as you can see, if you compare a 4 mm regular glass to a low carbon glass or Wright, it will give you 42% lower carbon emissions. So what is an ideal world? In an ideal world, you would want a solution which will have one, low embodied carbon, and second, low operational carbon. And that is what looks possible to us today. So you are able to get low embodied carbon by using a substrate which is low carbon or Wright, and you can get low operational carbon by using a really high energy efficient coating. So you put a high energy, high performance coating which reduces your U value, which has lower solar coefficient. So in that So when you merge both of these together, you're able to get a glass which is not only performing, which is not only aesthetically beautiful, but also is sustainable for the future. And of course, when you have a product like this, which is low on embodied carbon, it will help and it will contribute towards green building certifications, be it LEED certification. And this is just an example of what all factors where it can help, it contributes and can help you to gain points when you're designing your buildings. So this is what's possible today. Anything that you imagine with the regular glass is possible with the low carbon glass. You can put it in a DGU, you can put a coating on top of it, you can laminate it. So the possibilities are huge. The only difference is it's the exact same thing. The only difference is it's low carbon. It's better for everyone. I am available during the day here, and I have with me the physical sample, and we can do a small game where we can put two glasses next to each other, and you will see they're exactly the same, be it in an IGU or just a single pane of glass. So just to summarize everything together, if you compare a single glass regular to a low carbon glass, you have approximately 42% lower carbon emissions. And if you look at the facade, if you look at the overall facade footprints, a glass which is low carbon or I will have 30 to 40% lesser carbon impact, lesser embodied carbon compared to if you have done the whole building with the regular facade. And again, as Luka was mentioning, it's all verified. So we have the Environment Product Declaration, which means it's not just what we are claiming it to be, it is what has been verified and tested and validated these numbers. And this is the path which we want to take, not only for glass, but for all the other building materials that Sangoma produces. And as I was mentioning, the good news is that it's not just only in presentations or theoretically or in books, it's available today. So these are some of the examples that we have done. And I highly encourage and motivate everyone in the room today that we need to bring such projects, such products in Canada and do our projects with more sustainable products. Thank you very much once again, everyone. If you have any questions, I'm available throughout the day. Thanks a lot.
Thank you, Ravneet. That was great. So in Toronto, we're ahead of the regulations, as many of you might know. So that 70-30, 50-50 split is actually a lot sooner. If you're an institutional investor, if you're working for universities, real estate leaders, low carbon or all electric operational buildings are basically table stakes. And by 2028, the Toronto Green Standard, the minimum or the worst building you can build in Toronto in 2028 will have an operational carbon limit of 5 kilograms per year. Over a 60-year life cycle, which is the amount of time we look at for embodied carbon, that's 300. Most of our embodied carbon numbers for new buildings are somewhere in the 350 to 400 range. So we're already at that 50-50 mark, which is why I said earlier, embodied carbon is the next frontier, the next problem we have to solve. And I love that there's products now available with EPDs, verified performance. That's where we need to go as an industry. Okay, we've got one more presentation, and then you get to have a break. I'd like to welcome Joe Baz from the Flynn Group of Companies to talk about factory-controlled modular wall systems. Thanks, Joe.
Thank you. Can everyone hear me okay? Perfect. So I'm here to talk about factory-controlled modular wall systems. I'm Joe Baz. I'm a product manager at the Flynn Group of Companies. And I want to start off by just going over some learning objectives for this presentation. We want to understand the current challenges faced by construction from a labor and performance standpoint. We want to understand the benefits and challenges faced when building and designing with modular construction. And we want to do a brief overview of thermal energy demand intensity and how modular construction can affect this. So before I dive into modular construction, I just want to talk about challenges faced by construction. Number one, the most important thing is safety. We want to make sure everyone goes home safe at the end of the day. That is a core principle within Flynn. And we want to make sure we avoid any potential injuries on sites or worst case death. Some code changes, I'm sure you're all very aware of the Toronto Green Standard, but there's also Passive House, the BC Energy Step Code, where they're all moving towards climate resilient construction, and they were trying to meet net zero ready buildings in the near future. Labor shortage is another challenge by construction. This is a quote by Ellis Dawn. By 2029, we will be short of about 100,000 tradespeople if we don't do anything. So again, that's another challenge faced by construction. Increased material costs, maintaining quality control, challenging climates and locations, especially since we live in Canada where we do have very extreme weather, and project delays are all things that we want to keep in mind. So what is modular construction? It's when you're basically building these walls in the controlled factory environments, meeting the same standards and codes and the design intent of a building. Now, the most obvious benefit of modular construction is the installation process. You close up your building faster, which has a lot of implications on construction. You get to reduce your project schedule. Depending on the occupation of the building, you could be generating revenue sooner by bringing people into the building sooner. You get other trades in sooner as well if you're closing that building envelope as quickly as possible. You get weather tight sooner. This project right here is the British Columbia Institute of Technology, where the GC's led core architects Perkins and Will, and they are actually using mass timber for this project. It is essential in mass timber projects because you want to limit the exposure of that mass timber to the environment. So you want to close that building quickly. So it typically goes hand in hand, having mass timber and modular construction on the same project. You also save on winter conditioning costs. One thing I noticed when I actually went to this BCIT site is how quiet that job site is. So when you're surrounded by residential buildings, you want to make sure that that construction zone does not affect the occupants of the people around it and does not disturb the day-to-day lives of the families living next to that construction site. So that's another benefit of going with modular construction. Here's just an example of how quickly a building envelope can go in. You can see there's about 3 modules that are going in less than 2 hours in this specific example. Another time lapse over here, where in an afternoon after lunch, they're enclosing that entire length of wall, where in this project example, about 2,500 to 4,000 square feet of installed exterior wall a day, including your framing, your insulation, your cladding, your windows, all done in a factory and shipped to site. So talking about factory control and performance and liability, within a factory, you can really control that tolerance compared to on-site construction, where it might be minus 20 degrees Celsius, and those workers on site are going to be trying to get through the project as quickly as possible. They're not going to be focusing on those interface details as well as you would within a conditioned factory environment. The details between your windows and your wall are really crucial points within your building where you do have a lot of loss from thermal, water, and air tightness. I know we talked a lot about today, glazing ratios and all that, but honestly, the biggest focus should be on those interface details because that's where you have a lot of those thermal loss. Just focusing on that detail makes a huge difference and allows you to have higher window to wall ratio without actually changing anything besides aligning, let's say, the window within the insulation plane as an example. With modular construction, you can also focus on building integrated modeling if you get into the project a bit early, where you can identify a clash detection and really resolve a lot of issues that you would have on site, but early stages in a 3D modeling space. Now, some of the challenges faced with modular construction is really the logistics and transportation. You want to make sure that you can actually ship these modules to site, which typically is the limitation of the size of the modules. Now, depending on the system used, there might be other limitations, but you have to keep in mind overhead passes, you got overhead wires throughout the route of transportation from the manufacturing facility to the site. There's also potential concerns about lost days to weather. So you might have a very windy day. You have these big modules. Imagine craning that. It's essentially a big kite in the sky. You might have some lost days due to weather. And typically, you're going to want to use an overhead crane if you have very large modules. Now, you can actually see the photo on the bottom right there. We actually have this very impressive spreader bar, which has these fan fans operating on it to stabilize the module, which allows you to then actually install these in higher wind conditions. So there are ways to actually mitigate some of these challenges, especially if you're working with a company that is thinking about every aspect behind these challenges, such as that module in the bottom right. And the last point here is storage of modules and preparation of on-site work. The installation, as we saw in that time lapse, is very quick. We're not going to be able to install these fabricate these modules at the same pace of installation. So having a good logistics plan and storing these modules ahead of time definitely helps with executing the project smoothly without there being any hiccups. Again, going back to the most important points, safety, and then also green building, which is what we're talking a lot about today. With less labor and time on site means a safer work environment. A lot of times you're working fully within the inside of the building, so you're reducing the leading edge of work. If you have the appropriate PPE, you're going to reduce the fall rates. And talking about green building, in a factory environment, you can really control the materials that you use a lot better than on sites, and you can really focus on recycling that material and dealing with the waste compared to on-site construction, where a lot of times that material ends up in a waste bin and doesn't necessarily go to the appropriate locations for recycling. So just to recap on the challenges faced by construction, we talked about safety. So less labor, less cutting, less time on site creates a safer working environment. Whoops. Labor shortage, less labor required to put together the modules, increased material cost. There's no surprise cost when the project gets going, because a lot of times you're securing the material early on and securing that cost. Maintaining quality control. In a factory setting, you do have a lot better quality control processes, and you're within a conditioned space. Challenging climates and locations, and project delays. With the modular construction being in conditioned space, you can really work through things without having any issues with the weather. And meeting the code, you have tighter joints, better quality control, more attention to detail. With these modules, you have less joints within the modules, so therefore you have less opportunity for leaks as well. So let's talk about designing with modular. Now, the earlier you get in, this is a graph that I'm sure you've seen before. If you haven't, I've just took it from Google and put the reference in the bottom there. The earlier you get into the design stage, the lower the cost impact will be. The earlier you involve all the appropriate parties that you need for the design of that building, the more cost-effective your overall solution is. The further you get into the design, the more costly any changes are going to be. So it is important to have those conversations early. Another thing to keep in mind with designing with modular is the energy codes. So Toronto Green Standard version 4 is the current standard, where you need to meet a TEDI target of 50. But we're moving very quickly towards a TEDI target of 15 by 2030. Does have a very clear path towards getting to that net zero construction. TEDI of 50, for reference, is very close to, if not equal to, passive house construction. So that will soon become our standard practice in Toronto. For those that are not aware, TEDI, which is the thermal energy demand intensity, is essentially the difference between your losses and your gains. So your losses are related to typically your building envelope, your window losses, your wall losses, and then your gains are your heat recovery gains, solar gains, other gains, and then that difference, which is marked here as your heating output, is your TEDI, or your thermal energy demand intensity, which needs to be made up with your HVAC system, heating and cooling your building to basically make your losses and your gains equal to maintain the temperature within the building. So a way to reduce that heating output is by reducing the amount of losses and therefore reducing the amount of energy required to heat and cool your building. So what's involved with TEDI? It really is your building shape, your window-wall ratio, your window performance, building envelope thermal performance, building air tightness, heat recovery. And from these 6 points that I've just mentioned, 5 of them are related to your building envelope and, in this case, your modular wall system. So it's very key for the modular wall manufacturer to be familiar with every aspect within the building, those interface details between your window and your wall, the types of materials that you use. All of that has an impact on your TEDI targets, your construction schedule, and the overall execution of your project. So I just want to give a little bit of an overview of what we do within Flynn and our approach towards modular construction. It is not the only approach. It is not necessarily the best approach depending on the application, but we believe it is a really good solution towards modular construction. We're essentially utilizing our unitized curtain wall framing, and the reason why we want to use that is it has very high good tolerances. It's very airtight, very watertight with the dry gaskets between the joints. It just snaps together. We really like the benefits of unitized curtain wall. The issue with unitized curtain wall is that frame is typically exposed to the environment, so you have a lot of thermal loss through that. So we thought, why not insulate the outside of that frame with an insulated metal panel, which has two benefits. First of all, you're now thermally breaking that frame. The only thing attaching that insulation to the frame is long screws. But the other benefit with the insulated metal panel is actually adds to the structural integrity of the system, which allows us to create these very large modules without adding any additional stiffeners. We have a punch window approach where we frame around window and we can put any type of window system that you want in there. And then we clad the outside with whatever architectural finish you want, depending on the project requirements. Now, being able to span such large widths because of the insulated metal panel, we actually like to span column to column and floor to floor, typically. The benefit of going column to column is there's very little slab deflection at the column lines, which allows us to tighten up that stack joint and therefore improve the thermal performance of the system and also make the building look less modular because we can reduce those joints and therefore reduce the reveal lines between the modules. Just some upcoming projects or projects that are currently underway. The British Columbia Institute of Technology is a 12-story student housing building. The developer is BCIT, architect is Perkins-Will, general contractor is Ledcor. I know one of the sponsors here is actually Rainers. They are the window system used in this. I know EOT's also one of the sponsors. We use their fasteners to attach the IMP to the framing. And we're currently 8 stories into a 12-story building. It's going very well. Those were a lot of the photos throughout this presentation were related to this. A bit more local, 525 Markham. We're going to be on site in February of this year. That's in Scarborough. Developers Wigwam Incorporated, who focus on low-income housing for the Aboriginal community. The architects, Hilditch Architects, and the general contractor, Harbridge and Cross. And finally, talking about something even more local is the Toronto Western Hospital, which Alice Don is the general contractor, and I believe they're going to be talking a little bit about that later on today. Developers UHN, and the architect is Dialog. And we're expected to be on site in Q1 of 2026. So these are just some examples of projects that you can utilize in your modular construction. There's a lot of benefits with using that type of system for each one of these projects, whether it's mass timber and you have to enclose that building quickly, whether it's a hospital project and you have to maintain a certain schedule while also keeping in mind high performance, maintaining the relative humidity within the building, and keeping everyone safe within the building. These are all benefits within modular construction. That concludes my presentation. Again, I'm Joe Baz. I'm the product manager at Flynn. I'll be at the Northern Facades booth today through the breaks. You can get my contact information there as well, or have a conversation about our system at any point today. Thank you.
Thanks, Joe. When I first started looking at facades, I couldn't believe how much of what we build was predicated only on what 2 people can bring up an elevator hoist with their bare hands. And so those kinds of systems, they won't meet code anymore. If you're doing a double glazed conventional window wall with 3 or 4 inches of insulation in the back pan, that cannot meet TGS. So we need to do something different. You saw one example. There's lots of other examples to consider. Okay, we're going to take a break, 15 minutes, bio break, refreshments, coffee, and I'd like to ask the speakers from the first session to please join me back on stage. Thank you very much, everybody. We'll see you in 15. Okay, folks. We're going to get started again. Hopefully everybody has re-upped on the caffeine, got a little bit of sugar. So, session 2 is officially going to kick off. We're going to get started. Oh, one small bit of housekeeping. After this session, we're going to have lunch. Please do not bring food back into this room. So there's lots of seating outside. So the the event hosts have asked us to keep this room food-free. Lunch will be provided outside. So let's get right into it. I'd like to welcome to the stage Tyler Bowie, who is with Ellis Don, and he's going to be talking about the contractor's perspective on delivering complex prefabricated facades. So good segue from the previous presentation and continuing right along.
Thanks.
Thanks.
Yeah, appreciate it. Thanks, everyone, for having me. Admittedly, this was a little last minute. The original speaker was Vince Davenport, who's the director of our group, Building and Material Sciences. Where is it, sir?
It's up on the podium?
No, it's not up here. You got the clicker? There you go. All right, good to go. That's Vince and I. We built this presentation about a year ago for the building show, and it's gone through a few iterations since. The focus at the time was on general trends in the facade industry from a general contractor's perspective. I've kind of zoned more in the topic of prefabrication, which follows Joe's presentation a little bit better, I think. It's a great intro for what I'm going to talk about. But just to get ahead of it, there's my role description in the corner there. But what you might not know about me is that I also moonlight as a right-winger for the Leafs. I'm just getting ahead of that because I know I'm going to get the question later. I know, first-round exit, that's all I'll say. It's brutal. I won't get into much Ellis Don propaganda today, but a lot of people don't know what the Construction Sciences Group is. It's a pretty niche group in terms of a general contractor, especially in the North American market. We're a cradle-to-grave service that specializes in all these different areas. I sit in the Building and Material Sciences Group with a focus on envelope systems. A quick agenda today: why prefabricate in general? Why is this a driver? Why are people talking about it? Going to talk about prefabrication complexities and use some project examples that we're working on right now. So in general, why prefabricate? I want to stress that prefabrication is a means and methods to achieving a certain facade, and that's with regard to schedule, logistical constraints, labor, and quality. And these are all valid reasons to prefabricate. Us as a GC, Ellis Don has had good and bad experiences with prefabrication. The big driver for us is that schedule weather tight factor that Joe was talking about earlier. Getting to a point where we can start interior finishes, mechanical and electrical earlier on in a project is the big appeal to a GC, and it should be to ownership. Why not prefabricate? There's an argument that it can become more expensive, and we've seen that on some of our projects. I think that's because it's relatively new, especially with regard to these large format wall panels that we're seeing emerge in the market. So really quick, what's that weather tight factor I was talking about? This is high level critical path. We can start interior finishes and mechanical electrical on level 1 as soon as we're weather tight, meaning that the facade is wrapped 2 to 3 floors above level 1. So if we can theoretically push that date back, our occupancy gets pushed back, everyone's happy, ownership's more happy. I should note that if you're going to go with prefabricated wall systems, the design and planning for implementing this system has to happen a lot earlier in the project, like Joe said as well. So we as a GC have to get involved earlier, and we have to get our subcontractors involved earlier so that the design can be tailored towards whatever system that we're using. We as Ellis Don have been prefabricating facades for a long time. Back in 1989, we built the Sky Dome. Admittedly, it was before I was born, so I say we generously. But more recent than that, we've been building with window wall for a long time. We, with the increase in thermal performance targets, that's kind of evolved within the last 10 years to precast and window wall buildings for resi towers. This is a nightmare for quality control on site because you have two system interfaces at basically every single one of these junctures that we have to deal with and make sure they're not leaking from an air and water perspective. And then, of course, we've been doing unitized curtain wall for a long time on commercial and resi towers. That's a job from out west. And this is actually 141 Bay, which is the picture at the top left here. Last week I was on site and curtain walls flying for install there. But I alluded to what the industry trend is, and that's what Joe was talking about with Flynn's speedwall system, and a lot of other suppliers are coming up with their variations of this, which we've given the term large format wall panels. And that's because we want to address two things. We want to address that schedule constraint I talked about earlier, getting weather tight quicker. We have tighter schedule projects to deal with in general now, especially with hospitals. And then number two is addressing performance criteria, reducing the glazing ratio of our buildings. And this has kind of been the response that we've been seeing as a GC. Now, the complexity with these systems is that they're not all equal. You can have all these different panel characteristics that are kind of contingent on the project drivers, which are cost, architectural intent, procurement strategy, site logistics strategy, schedule strategy, and then, of course, performance. I'm going to zone in on each of these different elements and some of the systems that we've been seeing out there and how they address these project constraints. I'm going to riddle in some kind of case examples from these three projects here. I know a lot of people are probably familiar with them or have worked on them. On the right there is Toronto Western Hospital. Joe touched on it. I know there's DIALOG representatives here today. A beautiful building which we are tackling with a prefabricated approach. Top left is Burnaby Hospital out in BC. This one we took a slightly different approach to prefabrication, which I'll get into. And then bottom left is the notorious King West, which I will touch on and how we tackled that. That one could be an hour-long presentation in itself. It's crazy. So if you want to learn more about that one, come talk to me after. Starting with finish, when you look at your architectural intent, your conceptual design of your building, here's some of the questions you have to be asking yourself. Is there 3D geometry incorporated into the cladding system? What type of materials are being used in the cladding? Are there lightweight material alternatives that can be switched out? And then thermal performance and cost, again, are big considerations. We've distilled the types into three categories: cladding systems, and then precast and EIFS. And the reason we do that is, sorry, I should go back. The reason we do that is that if your architectural intent is precast, if you're designing the building with precast in mind, the supply chain that's out there has been around for a long time. There's a lot of precasters in the GTA market who have those products off the shelf that are available to you. On jobs like this, where there's more flexibility in the way that you approach the facade, so for metal panel cladding, for stone cladding, for composite metal, whatever it is, we look at these buildings at the start of a job, and they have a good potential to approach these jobs with large format wall systems because of that flexibility in the cladding options. Now, King West, obviously looking at this, Bjarke Ingels Group had huge visions for this job, and right off the bat, when this design was brought to the table, I think the project team realized that this could not be stick-built in the field. It would just be such a complete nightmare. We'd be chasing leaks. We'd be getting callbacks for 30 years from now, right? So we knew it had to be unitized in some way, but we started doing case studies and constructability studies on what the best way to do that was. What system should we use? And what was arrived on was a unitized curtain wall system. And basically, it encompasses as much of the geometric complexity of the building into the facade system as possible, as well as the material complexity. So this glass block that you see riddled across the building is fabricated into cassette systems and then structurally siliconed to the curtain wall framing. itself, and as you can see, it includes parapets and corner conditions, and as much as we possibly can off-site. So King is a great example of addressing architectural complexity with prefabrication as a solution. Next is the chassis system type, and this is along the same lines. If you are designing with a precast system in mind, this is basically an off-the-shelf system. You're going to go to a precaster, they're going to have all of their anchorage details figured out basically already, and you're pretty constrained to what systems they have. If you're going the other route and leaving your flexibility of cladding options open, there's two options that you can use for large format wall systems, and that's cold form stud-based systems and then aluminum extrusions. And if we break these three system types down, they have the same overall layout. They have a frame, they have a diaphragm, they have an air and vapor barrier membrane, or air and vapor barrier system, I should say, some insulation layer, and then the cladding on top. And you can see in that visual representation on the right, it's finished concrete. You designed with precast in mind. That's kind of what you're getting. And with the two other, there's more flexibilities in the finish options, the window configurations, everything else. I should say, though, that one of the things that we're looking into in the market is alternatives for precast, so lighter weight concrete solutions that can be put onto these panels that you see on the left. That's a new thing that's emerging, lightweight alternatives, and we're doing some in-house R&D on what those might look like. If you go with the cold form stud option for the large format panel, what we've seen is that it's not always most beneficial to fully prefabricate the panels. The first question you have to ask is are there legitimate schedule savings if the air and vapor barrier, the windows, the insulation, and the cladding are installed off-site, or can a partial approach to prefabricating solve whatever driver that you're trying to accomplish, usually schedule? Also, key consideration is panel joint type, which I'll get into next. And then do you have exterior access after the panels are installed? Because if you're going to go the partial panel route, then you have to have that access to button up the building, finish your cladding after the panels are installed. And then how are the panels being transported to site, which I'll touch on in detail. So for Burnaby Hospital, we partnered with Thermal Systems out in Calgary, and they actually approached us eager to try out a prefabricated cold form stud-based system. And what they were comfortable in doing in their plant was basically everything from exterior studs, sheathing, air and vapor barrier, window install, which they got from Deso Windows out there and installed in their own plant, and then insulation and girts as well. So those are the two variations of the finished product. This one's still missing insulation, but those are the two variations, and then those are those on them being installed on site, and you can see kind of our layout, the way we achieve the layout on the top right with a nested C-channel approach. But this is the panels before they've been buttoned up, so what's left to do here is return and do the AVB seaming on all the panel joints at the slab edge, and then infill the insulation and finish the cladding. What's key with this approach is trade partners, right? You need to have someone who's comfortable on taking on the liability of owning the air and vapor barrier membrane and making sure that these systems aren't going to leak at the end of the day. The driver here is to get us to a point where we're weather tight on L1 and we can start interior finishes and mechanical and electrical earlier on in the process. And it was able to do that on this job for us with a little bit additional temporary waterproofing from the inside. This picture is actually from Royal Columbian Hospital, where we did a similar approach, except we were partnered with an interior drywall trade. And they weren't as comfortable on taking on the liability of the air and vapor barrier membrane and warranting for leakages. So what they did was just the studs to exterior sheathing, and then the rest of the building was done in a conventional approach. But what I want to stress is that it depends on the comfortability of your trade and what they're willing to take on, and it has to be an everyone buy-in situation from architect to general contractor to your trades. Joint types. So joint types are heavily tied to our pool of subcontractors. Once you commit to a certain chassis system type, whether it's precast, cold form stud, or aluminum extrusions, that kind of dictates what your joints are going to look like on the building. So with precast, it's a system that we all know and use. It's a two-stage sealant joint, which everyone seems to be comfortable with in the industry over time. On the right is with a curtain wall extrusion, like the Flynn speed wall system. It's basically an iteration of their already existing curtain wall, unitized curtain wall. So all your stack joints and vertical mullions will be identical to unitized curtain wall. Very high performing. Again, everyone's comfortable. In the cold form stud approach, there seems to be a lot of debate in the industry about what the best approach is, and we've seen different panelization companies take different approaches, and building envelope consultants having problems with the approach that they're taking because they're hybrid between the one you see on the left and the one you see on the right oftentimes, and they're not as true and tried as the other two have been. So we often see a combination of sealant joints, membrane joints, gaskets being used that haven't really proven out their durability over time. So this one's still an unknown in the industry, and it's also tied to that exterior access I was talking about earlier. If you don't have exterior access, you have to come up with a solution more on the curtain wall side where everything's gasketed together once panels are dropped. Finally is panel size, and like Joe said, this is closely tied towards our logistics plan, right? So first thing we ask as a GC when we're either proposing a large format wall system or one of our trades proposes it, or it's designed, the building is designed with a large format wall system in mind, is will the installer have access to tower crane time? This is make or break for our schedule, right? If the envelope trade wants to use the tower crane, oftentimes we're getting into a shift schedule where the structural trade is working in the morning up to the afternoon and the envelope trade takes over in the afternoon. And that means we have to go for a bylaw exemption in a lot of areas of Toronto. I will throw caution to the wind here and just say that if you get into a shift schedule and your structural trade starts lagging, they always take priority. So where these kind of jobs have gone to crap is where we start losing time on our schedule with structure. They take over that afternoon shift schedule, and then the benefits of going with the large format and installing off of the tower crane is kind of thrown out the door. Toronto Western was a good example of kind of how we analyzed our logistics in conjunction with looking at Flynn's speedwall proposal. They originally came to us with the proposal on the left, which is a landscape large format panel, quite large. Everything had to be installed by tower crane. And then after further optimization, because of their anchoring strategy, simplifying their anchors, they switched towards more of a portrait perspective, a little bit smaller panels, but not sacrificing the benefits that you get from schedule savings with the large format approach. And this was key because it allowed us to switch to spider crane and loading platform install without sacrificing that schedule, that increase in schedule performance as well. Finally, the crating and transporting and hoisting. You are often limited by your truck size. I won't go into detail here, but what I'll say about the portrait perspective is what's a little tricky with unloading crates is that, or unloading frames, once these are picked off the frame, they have to be switched to the vertical orientation if they're loaded in this way. And we've seen on a few projects that this really slows down the process. So we're looking at ways to improve that process and make sure we're not sacrificing panel install time on the unloading of the frames themselves. So just something to note. And then finally, hoisting, just to compare with a large format panel installed by tower crane, this is kind of what it would look like. And then really grainy photo, but this is at Royal Columbian Hospital in Toronto, or in Vancouver, where the cold form stud-based panels were installed from the slab condition on the inside with a mini crane, so a kind of tilt-up method. Before I just want to summarize that if you're going to take one takeaway from this presentation, know what's available to you out there in the market. Half of this is familiarizing yourself with what trades are coming up with, like Flynn's system, like the other suppliers in the market, and making sure that the systems work for your project. We don't want to try and fit square pegs in round holes with systems that don't necessarily fit. And if you don't want to do any of that, just come talk to our team. We can tell you a little about what's out there. That's part of our role at Elliston is knowing about new and emerging technologies. And just to plug our research and development team, part of what we do is develop new systems to implement to the market and partner with professionals like you in the industry who have good ideas, and we can help with the execution. On the right is that hybrid timber floor panel system that our team developed. We've also been working on mass timber volumetric modular systems. We did a cold form stud prefab wall system prototype a while back as a experimentation. And then in the pipeline, I touched on it earlier, but we have a low carbon lightweight panel in the works. And if you have any other ideas, reach out to me or my group. We'd be happy to spitball with you and toss ideas around. Thank you, everyone. I appreciate it. Enjoy the rest of the speakers and enjoy the rest of the conference.
Thanks, Tyler. So for me, that takeaway, time is money. And where interest rates still are today, every little bit of schedule compression is going to help. And all the architects, all the folks that are engaging with developers and owners, I think we're not having enough conversations about that schedule and what early design decisions can do about that. So lots of different ways to deliver high performance, lots of different procurement methods, but one of the advantages of something like a design assist is that you get that early insight into constructability, into schedule. And so you can really change the way a pro forma and afford certain things that you may not be thought possible because you're servicing that project debt for a short amount of time. So thanks, Tyler. Next up, we've got Ken Wright from Raynars. Coming up, Ken.
Hello, good morning, everyone. My name is Ken Wright. I'm working for Raynars Aluminium. And I'm very happy to meet you. It's my first time in Canada, actually, so a great place to be, especially Toronto. And I'm working as a sustainability, on the sustainability topic. Until now, I think in my career, the most complex job I ever did. Besides that, I tried to raise 2 little children. Maybe it's more challenging than that as well. But that's what sustainability is about, right? We have to act now to have an impact in the future so that the future generations can have the same opportunities as we are. Maybe a few slides about Raynars Aluminium, who we are. So we are an engineering company. So we are a system house in aluminium joinery, where we focus a lot on facades, so window systems and facade systems itself. I want to start with the mission statement we have, because it has a direct link to its sustainability. Our mission statement is, together we improve the living and work environment of people now and for generations to come. I think there are 2 very important things in this sentence, is together. We are all part of a value chain in the construction industry, and everyone has his own job to do when it comes to sustainability. But this is the major challenge as well, because we have to understand what are the challenges in every chain, or part of the chain. So we have to really work together in order to understand each other and to act in a positive way. Generations to come, as Raynars, we are a family-owned company. So our directors now, they really think that the children of their grandchildren will be at some point the directors of Reiners Aluminium, so they really put sustainability forward as well, centrally in their DNA, because they want to stay ahead of the curve and stay relevant in this industry where sustainability will be a major part of. Again, we are focusing on the residential market and the project market, but there are a lot of stakeholders involved. And again, that's about together for better. It's like we have to understand each other in order to see what we can do, how we can help each other to maximize our impact. So, yeah, we are situated, our HQ in Belgium. It's the country the size of a post stamp, I think, compared to Canada. But we are internationally active, especially now since more than 10 years in North America. But we really believe like we have to localize ourselves. We have to get familiar with local legislation, what are your needs, and adapt. Just some projects where we are involved with. I think, sustainability is becoming really a differentiator as well in the construction industry, and you see a lot of labels coming up. They prove what they are doing, right? Because there is a lot of greenwashing as well. This is, I think, one of the previous speakers talked about this project. It's a passive house, so really focused on keeping the operational carbon down. The previous one was in Vancouver, so it's especially to keep the cold out. I think now the different thing is to keep the heat out. This is a project we did, or we collaborated with in San Francisco, which has a LEED label. I think LEED, passive house is more about operational carbon, where LEED looks from a 360-degree to sustainability. This is closer to my home. This is one in Brussels. I like this building because they really started in their design, okay, we have to achieve something, which is a BREEAM certificate. But just how they integrated, for example, sustainability for operational carbon, it's not that clear in the picture, but I think on the leaflet in front of you, there is a better picture. They were working with, wings in order to have some solar shading, but they integrated solar panels on them, on the south, in order to get like free green energy on site. So you see that architects are putting sustainability more and more centrally in their design as well. They want to achieve something, but it has to start in their design. Okay, to be honest, this is the best picture of my presentation. From now on, it will go downwards, just that you are prepared, so enjoy it. But this is really a metaphor I always want to use when it comes to sustainability. It's the biggest tidal wave ever coming our way. It's forced or pushed by legislation. I think the construction industry is one of the industry with the most regulation, and sustainability is becoming on top on that regulation. At the other hand side, we also see that a lot of customers are demanding things on sustainability. They say regulation is my Olympic minimum, but I want to go beyond. So these are really two major forces pushing this tidal wave. And this poor guy, that is you as a company, and you have two choices. You do nothing, you'll be swallowed by the sustainability wave. I'm not sure if you will still be relevant in 10 years then, or you take the energy of the wave in order to get forward. So I think that's a nice metaphor, what we are facing now. Where did the wave start? I think with the Climate Paris Agreement in 2015. All member states, they said, and this has a direct impact on buildings as well. We have to decarbonize by 2030 by 50% and become net zero by 2050. But imagine tomorrow a miracle happens and we all stop emitting CO2. Check, check. I'm back? Okay. So if we stop tomorrow with emitting CO2, the world will still get worse for a few decades because nature needs time to heal. So we are facing more extreme heats, more cold, more storms, more floodings. So we need to adapt now. So if you design a building today, we have to think about the future because it will only get worse, unfortunately. And the second, or the last part of the Paris Agreement was, okay, let's push the financial world to sustainable investments. I'm going to throw around some numbers just to give an impression on what we are facing. But I want to start with this one. Buildings are great. If you think about it, around 90% of our time we live indoors. I hope you are born in a building. You fall in love in a building. You raise a family in a building. And some genius whiz-kid is now inventing a new medicine against a horrible disease. All is happening in a building. So buildings are great, but they come at a certain price. Around 40% of all emissions worldwide are related to our buildings. Heating and cooling of the buildings and the embodied carbon. So this is a major challenge. And this will become even the biggest challenge. In order to cope with the growing population and urbanization, I'm gone again, I think, okay. The floor space will need to double by 2060. I think a lot of you now see the dollar signs because we still have to build a lot, which is a positive thing. But maybe to put it more in, or to give a better example, this means every month, starting from now, a city the size of New York needs to be built. Every month from now to 2050. That's a mind-blowing figure, if you ask me. And if we do not do this in a sustainable way, we will face horrible consequences. So one thing, we have to build more and more and more, but we have to do it in a sustainable way. But this comes to the question, and I think that's the most important question of my presentation, what makes a building sustainable? I think if I would ask you to write it down, I get around 150 different answers. I think indeed operational carbon efficiency, always part of a sustainable building. Next thing is embodied carbon. Yeah, for sure. But I think a third one, what I think is the most important, or one of the most important aspects of sustainability, it should stay affordable. Like sustainability cannot be for the happy few of this earth. And maybe that's now a thing, what is happening in the construction industry, that it's only for the luxurious apartments that have like the labels and whatnot. But we have to keep it affordable as well. We cannot not leave anyone behind. So this is an example. This is in the Netherlands, in an old industrial town. They are revamping it. And the architect, he said like, okay, this is for social housing to start with. So he had a major challenge. He had to keep the operational carbon extremely low, because that was one of the demands of the city as well. But with prefabrication, modular design, they achieved that. And they could use high quality materials to keep the operational carbon down. But he said, okay, I want to integrate something about local biodiversity as well. So you see, again, architects are starting from their design, or from a sustainable design, within their plans. And I think that's something we have to do more and more, not like when everything is designed, oh shit, it has to be sustainable as well. No, you have to start from the beginning in your design thinking on what do I want to achieve. And this is the pathway, more or less. I think we're already good on operational design nowadays. We have the technology, we have the heat pumps, we have good materials, we know how to design a low operational building. So I think that's something we have covered. But focusing only on operational carbon meant that the embodied carbon was going up, because we used more and more materials in order to have a good insulated building. So indeed, the next challenge will be about, okay, how can we deal with the blue block? So that will be the challenge of the future. Just to give, to make it more detailed, or to give it more meat to the bone, we ordered like a research study. These are like 25 office buildings in Brussels, so it's Belgian related. But yesterday we had a meeting with a professor of the University of Toronto, and they did like a similar benchmarking exercise, and we're more or less in the same ballpark. So I think these numbers are can give a good image of Toronto as well. So for every building, they did an LCA, so they really measured or calculated the impact on operational and embodied carbon. And on average, the carbon emissions were 500 kilos per square meter. But this is operational and embodied. If you look at the embodied part of it, so the dark green, it's around 300. So you see, operational carbon we have under control, but in this, or in these examples, the the embodied carbon is now the major challenge. It's even bigger or larger than the operational carbon. When we drill it further down, okay, where is this embodied carbon coming from? On average, 20% comes from facades. This is not only windows, so it's windows, bricks, cladding, insulation material, whatever. If we drill it further down, around 6% accounts for the windows. In our case, you know, a window consists out of glass and aluminum joinery. The biggest contributor is then aluminum. So to calculate everything back, on average, the aluminum accounts for 5% of the total embodied carbon. You maybe can say, okay, whatever, 5% is 5%. It's maybe not a thing we should focus on because there are no just marginal gains. Actually, I don't think that's the case. Every material has to decarbonize. So I think in the building industry, every chain, every part of the value chain has to push. Okay, every material has to decarbonize. I'm gonna put it in my tender like, okay, it has to be lower, lower, lower. So even if we can go as arenas from 5 to, for example, on average 3 or 2%, we have done our job. We have made the biggest impact on aluminium. And this is something every material should do now, starting from now. Just to give it a little background on numbers, so aluminium is not good on carbon intensity. So the production process of aluminium asks a lot of energy to start with. So when we look at the global average, for 1 kilo of aluminium, you have 17 kilos of CO2, which is crazy. I couldn't find the North American numbers, but I think they will be in the same ballpark as the European. So in Europe, on average, 7 kilos. Today, as Reinas, because we really put this forward in our sourcing strategy as well, we're around 5 kilos, but we want to go up to 3 kilos, or down to 3 kilos. Because, as a family-owned company, we are now part of the Science Based Targets Initiative. Maybe for those who do not know the Science Based Targets Initiative, remember Paris Agreement, member states, but at the same time, the United Nations, they were like, okay, if we have to put our faith in all governments, maybe it's not the best idea. So let's put in a framework as well where a company can, it's voluntary, can say, okay, I want to commit to science-based targets. I want to decarbonize by 50% by 2030 in a science-based way. So it's really proving project by project or initiative what will be the decarbonization impact. So this will have definitely a commercial impact, but it's in our DNA as well. So it's an end-to-end story for us. And guys, it's a pathway. I think we should take this challenge one step by one step. Going to net zero today, I think it's impossible because you will have an enormous push on price. And again, we shouldn't leave anyone behind. So science-based target for the construction industry, they said, okay, in 2025, on average, we should land around 590 CO2, operational and embodied carbon. As you saw in the example before, we are already in that ballpark figure. But from now on, we have to decarbonize together, all together, step by step. So I think that's the biggest challenge right now, how to do this, and for this we all need to work together. Just to show a few products, how we see it, how we are designing sustainable products, is like, okay, we want to focus on different aspects of sustainability. We want to achieve passive house standard, so focusing on operational carbon. They need to be equipped for the future, so on airtightness, wind load and things like that, because it will become mandatory, because it will get worse, unfortunately. Another big topic is we have to design for the circular economy and low in embodied carbon. So I think Luka already mentioned it, like ask for EPDs. You have to calculate the impact of your building, and the only way to do that is by asking for EPDs. Sustainability shouldn't be a gut feeling anymore. It should be based on hard facts, so use EPDs. The same for our window system, the same for Master Patio, which is a sliding system we offer. It's not Passive House component certified because Passive House doesn't like sliding doors. That's the base fact, actually. So I want to end. I hope now it's more clear in our mission statement. Together, we all have to work together, and we have to start acting now in order to have a same or a better place, at least for the next generation. So I want to thank you for your attention.
Thank you, Ken. That was fantastic. That SBTI curve, we've been spending a lot of time focusing on that. There are a lot of Canadian real estate organizations that have now committed to SBTI. We've done the math on the 40 or so life cycle analyses we've done on real projects. And based on currently available technologies that are available in the market today, our best our best concrete and our best timber buildings get us to about 2030 on that curve. We don't have solutions beyond that. So there's lots of great innovations, but we need way more because that curve is basically our budget for the real estate industry. It's our share that we have to work with, and we need to dip below it, and we don't have a lot of time. So thanks, Ken. That was really great. Next up, Giles Robinson from Foster & Partners. And we're going to learn a little bit about the one.
That's great. You can hear me? Is that good? Yep. Put that there. Ooh. Good. Okay, well, it's a pleasure to be here today to present to you our project at the One, and it's lovely to be here on a warm, sunny day. I've been here on very, very cold days, so it's really, really lovely to be here. I think before I start, and it's been touched on earlier in presentations, I think developing a project and delivering a project, it really is a team effort. And I think as we've developed and evolved the design for the One over many, many years, we've been very fortunate to have, in particular, two local partners here, Core Architects and RJC, on both the structural and facades design, and they have been really instrumental in us delivering, or in the process of delivering this project. So I really would stress that importance. I think Foster & Partners, I think we're known internationally for a whole range of projects. We work really on some of the largest structures in the world through to some of the smallest components of building, from door handles and tables. And I think that process and the process that we go through in the office assists with how we consider and develop our projects, in particular high-rise structures that I'll talk about today. And as Lisa mentioned earlier on in her presentation, we have worked with Apple and with Lisa and her firm extensively on the development of glass systems. And all of those aspects of design really inform the process that we go through. But I'm here today to talk about high-rise buildings, and we were very fortunate in 1986 to complete, you can see that there, the Hong Kong-Shanghai Bank, and that was, for many, one of the high points of high-tech architecture, as it was dubbed in those days, and it gave us our first opportunity to really look at how we could take a high-rise structure, explore spatially within that building different volumes and massing, And very importantly, is to look at the opportunities of expressing the structure and the servicing of that building, and creating a very distinctive design that really became a landmark for the city. That approach was developed further in 1991 with the completion of the Century Tower project in Tokyo, the second building here. Sorry, you can see there. Second building there, and you can see the very distinctive K-frame that we introduced on the facade that takes the seismic loads. And again, we felt important to express that within the design. And then more recently, two projects here in North America, the Bowie in Calgary and the Hearst Tower. And those two projects are really ones that have evolved out of those early projects in the 90s. And I think very importantly, this is a cross-section through the Hearst Tower. We really saw that particular project where we had an existing Art Deco building 5 stories high with a facade that needed to be retained, and we needed to insert a structure within that. And we evolved the structural system and the modulation of the building related to it, and really were able to kind of celebrate that space. And I think in terms of the design, utilizing that for public activity, expressing the frame through the full height of the building is really kind of a key characteristic of how we've really developed and evolved our approach to high-rise buildings and their interrelationship with the ground plane, and in this case, a historic structure. And then externally, we saw the opportunity of carrying the structural diagrid that runs through the building through its full height, and then to express the edges of the building with a sawtooth arrangement that creates a very distinctive profile. And then in Calgary for Encana, the Bowie, completed in 2013. I think when we're designing the projects, Norman Foster often says, you know, what about the city scale? And he always talks about city scale, and sometimes we kind of wonder what he meant, and this is a good example, this image, of what he means. And I think when you look at a lot of the more utilitarian buildings in downtown Calgary, there's no real distinction in their forms, their structures, and you know, in terms of responding to the city and creating a really strong focal point, the introduction here of a curved form. This is in plan a semicircular form with the express diagrid really creates a distinctive profile within the city, and that runs up from the ground plane up in a series of faceted elements that contain triple height volumes that relate to the workplaces inside, and then that's just a view from the top. And then more recently, a project in New York for JP Morgan. This is a tower that is due for completion in 2025. And again, you can see, maybe it's a signature of ours, an expressed diagrid on the outside that takes the wind loads. But I think what's interesting about the building is the ground plane and how the structure has had to respond to what's underneath. There's railway tracks and platforms, so the structure comes down on 4 nodal points and then transfers through into the station below. But that gives an opportunity, and in terms of the design evolution, to really express that frame in a really dramatic way. And that project is due for completion in 2025. And this is its current state in New York at the moment. So that will top out at 420 meters. We very much hope we'll be able to present that at Zak World of Façades in more detail in future presentations. So turning to one, we were commissioned in 2013, over 11 years ago, to develop this project. And I'm sure most of you know it's a site located about 4 kilometers from the downtown on the intersection of Bloor and Young Street. Obviously a critical junction, Bloor Street, the primary shopping street, and Young Street, as you all know, the longest street in the world, I think over 84, 85 kilometers long. And I think what's interesting about it is it's becoming a nodal point and a reference point for the city. The construction of one Bloor to the east of our site, over 75 stories in height, so a building of real significance, and then the two structures to the north, really kind of creating a focal point. And then a view looking back towards the city, and you can see the context and what we were dealing with, the site in question. This is rather sticky. Okay, I won't do that again. You can see the site and the towers that surround it, fairly utilitarian in terms of their design and construction. And then just the four here, the Four Seasons Hotel, obviously a fully glazed structure to the north. So in terms of design process, and I'll talk fairly extensively about design process here today, I think this just gives you a kind of a feel for when we were first approached and the design evolution. I think the project from its outset, obviously being such a key location in the city, we looked to develop a multi-leveled retail accommodation over the first 8 floors originally of the site, and they were across the entire extent of the site. And then above that to locate residential accommodation. And these are a series of studies that we produce, where you can see that we're looking at how we can begin to articulate the building with the introduction of winter gardens in the image on the left, and then looking at how that evolved and developed to express the structural frame and the diagrid. And really the culmination of that initial study was a design solution that looked at putting all of the structure on the outside, exoskeletal frame that would enable all of the floor plates to be fully flexible. And that was obviously highly desirable for the retail accommodation. And also at this stage, you can see we started to look at the potential of transferring the core from the main tower itself across to the west and into a secondary core, creating a sky garden to maintain that flexibility through the lower levels of the tower. And that was a view of that scheme looking down from Bloor Street, and you can see the frame expressed, and also midway up an acknowledgement that we needed to be looking at interstitial mechanical floors through the height of the building, and that was kind of a question mark about how we could integrate those into the design. And then at this stage, we always run the city views and look at that in the context of both the nodal point at Young and Bloor, obviously the wonderful CN Tower, which I always think is a really iconic structure for the city, and then you can see one Bloor East that's in its photo montage mode, but it's now being completed. So as part of the design evolution and looking at the costing of the scheme, we had developed a linear building that ran along Young Street, a rectilinear form. But as part of that value engineering process, we needed to reduce the footprint for both cost reasons and structural reasons. So we focused our energies on the very corner site. Importantly, an adjacent residential tower on Balmudo, which we were very keen to minimize, if at all possible, overlooking from the structure. And then the desire to create Canada's tallest building, and we originally looked at a building of over 90 stories. that building obviously with a central core, and then very importantly, the strategy of transferring through a sky lobby at the 6th floor level, which was included within the design, and that really to create that uninterrupted space at the base of the tower. We then looked to break the building into 12-story modules, 18-story modules, so there are 5 blocks of 16-story modules containing the accommodation, and then between that there are intermittent mechanical floors, 2 stories in height. And I think what was interesting as we really began to kind of get into the detail and analyze the structure is the benefit they gave us in terms of vortex shedding. Obviously, as you well know, a flat facade creates potentially quite extreme wind pressure down on the ground plane. And by introducing those breaks, we found there's real benefit on the streetscape, particularly on Bloor and Young, and obviously very important given that they're heavily trafficked. We then developed with RJC the structural frame for the building, and as part of that strategy of keeping the ground plane really free from structure within the footprint of the site, we developed a scheme with 8 structural mega columns that run the full height of the building. And then, and what is now a very distinctive feature of the tower, a series of hangars that take the load of the corner of the tower, and that enables the mechanical floors to be fully expressed without the need for structures, particularly on the corner. And again, a very distinctive characteristic of the building. And this is kind of part of our design process, and we're all now very familiar with it, but we work very extensively with 3D printing, and you can see here this evolution from the initial tower design through to the final design took about 18 months to complete, and during that process, obviously, we were working with the city to develop a response that they were comfortable with. Now, in terms of the detailed consideration of the tower, I think what's interesting is flexibility is the name of the game. And when we started, there was a desire to have the lower levels for retail activity. And so we developed a strategy of having the upper floors containing the residential in a much simpler, more restrained fashion. And then at the lower level where the accommodation is located, sorry, is that okay? Yeah. The retail accommodation is located. We looked at introducing a screening system around the base of the tower. And here are some of the studies that we did very early on in that iteration, looking at how we could introduce a veiling system. So really a system that would enable retailers to potentially utilize daylight, but also control the lighting into the space. And then some of the visualizations from that point, you can see now that large clear span space at the base of the tower for a single retailer. Apologies, jumping forward there. And this is a view along Bloor Street. And then at this point, brief changed again. The concept of developing retail over 8 floors was considered to be not viable. So we were then asked to look at introducing a hotel into the base of the building. And that necessitated looking at particularly the access and the entry sequence into the building. And this is the ground plane as constructed with that central space on Young and Bloor, a really grand urban room. You can see to the south of that car parking, really challenging to get access down into the subterranean parking areas and obviously delivery bays. And then just on the west of the site, what was a relatively tight core, but important to differentiate between the residential core and the hotel core. And that was something that provided access to the hotel and also to extensive areas of food and beverage on the first floor level. And then above, beginning to explore the possibilities of for the hotel layouts, and that really informs the final programmatic arrangement of the building, which is set out here with a connection to the pass system that was never ultimately realized, through to the flagship retail and the restaurant accommodation on the 3rd floor, the hotel in that first module, that first 18-story module, and then above that, 4 modules of residential accommodation and the crown at the very top of the building. And that's the final spatial distribution of the scheme. And these were the images that we produced and submitted to the city, which really pulls together all of those component parts. And then views up Young Street with some of the heritage structures that we were required to retain as part of the design. And then setting that in the context of those city views, and I think very importantly, really looking at how those expressed expressed mechanical floors are working in the context of the adjacent structures in the city, and really creating a strong statement on this nodal location. Then getting into the detailed design of the facades, obviously, kind of very interesting aspect of the design, and one which, for us, Foster & Partners, is really important that we look at both the frame of the building and actually what's going on inside. And this is a typical level in the hotel, and you can see the major shear walls that have a real impact on how one space plans the building. And then on the typical residential levels, we looked at the layouts. And I think we always have a saying about designing the building from inside out. I think quite often with high-rise buildings, people are kind of just thinking about the external skin of the building, but we really want to analyze and look at what's going on inside the building to see how that can inform the expression of the building and how we treat elements of the design. And for internally, we produce these renders, and these are kind of a conceptual stage, really to kind of begin to create a feeling and a sense of those interior spaces and their relationship to the facade. And I think importantly, as part of that process, it's important to look at kind of the opportunities. And in this image, you can see the introduction of a bench seat, which we felt would be interesting within the residential units for people and places for people to sit, but also that gave us an opportunity within the spandrel that's developed on the outside of the facade to create a zone to bring fresh air in and exhaust air out, which is, you can see in the diagram there. We then got into the detail and really spent a considerable amount of time looking at how one integrates the various components of the frame with those interior spaces and the servicing requirements of the structure. And I think at this point, it's really important to get input from contractors and contracting, particularly looking at panel sizes, the mega columns. We wanted to express those really as a component with real scale and grandeur. And so we're looking at the kind of maximum panel sizes that could be delivered for those components. And then also looking at how all of the component parts were brought together in the design. And I think this is something that as architects we spend a lot of time doing, and we can only go so far with this process, but it's critically important just to understand those connections. And here, integrating in, I'll go to the next slide, integrating in the requirements for ventilation, and you can see here the challenge of supply and extract located within the spandrel. The ribbed spandrel panels was something that was of particular interest because we didn't want that to be seen or expressed externally, so we needed to try and integrate that in a really controlled way within the design. And then on the mechanical floors, I think very importantly, obviously the functional requirements for supply and extract, but again, looking at the design from the city scale, we wanted to introduce what is effectively a jumbo louvre on the outside, which really has a much stronger resonance and relationship to the external cladding of the building. Producing models really important for us in terms of design process, and in this case it was very instrumental in how we developed the color palette. These are models at a scale of 1 to 200, and we use these really to, and we photograph them externally to look at how different materials and colors can come together. And in this case we were selecting a champagne silver color for the frame, so that was distinct and separate. And then the glazing, apologies for the low quality pictures of the glass, but this is a bronze tinted glass that you can see on site now. Here again, model views showing that expression. And I think, you know, and interestingly, all the visualizations you do, it's really, really informative when you actually build a model and you put it outside. And it's only at that point you really begin to understand whether the building and the framing and the detailing is working for you or not, as the case may be. We then moved over and you know, with the design team, working with contractors to develop mock-ups. And I think this afternoon, I think this will be covered as well. As architects, mock-ups are all important. We're not magicians, and we can't really understand what's going on in a design until we see it in the flesh. These were some visual mock-ups produced in Buffalo. And they were used to test really how all the component parts of the structure were coming together. And interestingly here we had a lighting design which we carried through to quite a late stage to light all of the structural components of the design. But as part of this mock-up we realized that actually it was really very challenging in terms of the service distribution to these points, difficult in terms of maintenance, and I think for us as architects it was unfortunate to see the facades kind of peppered with these fixtures. So they were omitted, and we have an alternative lighting strategy for the building. And then again testing these the jumbo louvers on the outside and how those component parts come together was really informative at that stage. And then the details of that secondary core to the west of the site, which is now fully constructed. As I said, the working on the project, always a challenge, made even more challenging by the fact that we hit COVID halfway through all the mock-up stage. So it was kind of really critical that we had our eyes and ears on the ground. That's Earl Mark from Core Architects, who could video the panels that were produced here by Riverside, a fantastic contractor. Local contractor, and we could really begin to explore the colours and the materiality of the frame in particular, and that was something that was, I mean, really very important to us as we took the project forward. And again, just looking at the technical aspects of it, and you saw this in the details, you can see here the integration of the mechanical vents and supply and extract vents and how they're integrated into the design in a really kind of minimal way, so they're not something that's highly visible when viewing the tower. And then really again, following on from visual mock-ups, performance mock-ups, again, critically important. This one produced in Shanghai, and again in the height of COVID, so this was all tested semi-remotely. Fortunately, we have a firm out in, or one of our, an office out in Singapore who could assist with this. But this process and it's an iterative process looking at the different systems and how they come together, really important to ensure that we're getting the visual detailing right and the technical performance right. And of course, at this point, you always you come up with little challenges of how to resolve panels. You can see here on the right-hand image, and you know we wanted it all to come to a point, but of course you can't fold the metal. So these are all things that one works through in considerable detail, and then the integration of the operable vents to make those as part of the seamless design of the facade. And some more views of that. And then in terms of progress on site, as you know, we are We started construction on sites 2021. We are moving up slowly. We're up at level 58 now, pouring concrete. The external cladding is following on behind. And you'll see BM Windows, who are producing that, are outside, and you'll see the details of the facade system on their stand. But you can see here, these are shots taken about 4 weeks ago on Bloor, where you can see the frame really clearly expressed. I think all the elements are kind of coming together as we had envisaged them. Yeah, we're looking forward to this hopefully topping out and structurally 2025 and becoming a really exciting new addition to the skyline of Toronto. So I'd like to thank you for your time and hand over to him.
Thank you, Giles. That was quite a presentation and a beautiful looking project. Thanks. So we're actually, we've got one more session, and it's going to be our first of 2 panels. So as we get that set up, just maybe a quick sneak peek of the next session, one of my favorite topics. Any guesses as to where Toronto's climate is heading? Any comparable cities? We know it's going to get warmer. Do we know how warm, ballpark, in the next 30 years? Miami? Washington, D.C. Okay, somebody. Oh, that's one of our panelists. Well, of course you know that one, sir. I did not plan that setup, I promise. So a follow-up question to the architects in the room. What temperature are your mechanical engineers designing and sizing your equipment? Have you asked them? You probably should. It's OBC, they have to. But what happens in the next 30 years? Are those cooling systems adequately sized? I don't know. But what I do know is that we're not asking enough of those kinds of questions. So with that in mind, I'm going to introduce Satya Ramachandran, and he's going to introduce the rest of our esteemed panel. Take it away, gentlemen.
Thank you, Luka. Can everybody hear me? All right. Thank you for the organizers to arrange this wonderful session with wonderful set of panelists here. I'm Satya Ramachandran. Today we're going to be talking about the, maybe pun intended, overheating issue, the climate change, and the adaptation measures. I'm Satya Ramachandran, Director of Building Science with eXp Services, Inc. I'm an architect by background, and I also have an advanced education in building science, and I've been providing building science consulting for the last 20 years. Maybe some of you know me, some of you don't, but that's okay. I have a good excuse. I've been vagabonding between cities. I've lived in West Coast for about 8 years, the cities of Seattle and Vancouver, 8 years in Calgary, dealing with lots of issues in terms of freeze-thaw cycles, hail and such, in addition to the normal control of heat, air, and moisture issues. And now, since 2001, I've been in GTA. I'm sure you may question, like, my allegiance with any particular hockey team. Is it the Canadiens, where I started my schooling, like in Montreal at Concordia University, or is it Canucks, or is it Flames, or is it Maple Leafs? I'm still trying to figure that out. For now, let's say go Leafs go, and let's start the panel. So today's discussion is going to be on climate adaptation. And just as an observation that I should say, in today's sessions, this is the only session that's going to be talking about climate adaptation. I've noticed several of the discussions that we are having today is about climate mitigation, but here we are, this particular session will be focusing more on the climate adaptation. As I was talking with the panelists, they're all in agreement to say that, like, in a couple of years, we're going to be seeing the reverse. We're going to be looking at more climate adaptation. at least for quite some time until we can reverse and reduce the and bring the global warming under control. Today's discussion, the way that I'm approaching this is like I'm going to take 2 minutes to give a kickstart with few slides to set a tone, followed by introducing our panelists and then questions. I'll try to get 5 to 10 minutes of time for you to, if you have any questions, but I certainly don't want to be the person standing in between you and your lunch. So with that said, sorry. So this is a slide that shows on the left side a graph from the Financial Times in May 2023 that talks about exceeding the critical 1.5 degrees Celsius above the annual mean temperature above the pre-industry era. Within 6 months, or almost 6 months, in February 2024, the same Financial Times had reported that we have already crossed, the annual mean temperature has already crossed 1.5 degrees Celsius. What this tells us is that the projected trajectory, we are surpassing the projected trajectory in terms of climate change. This particular graph captures how, in spite of us putting all the efforts in terms of climate mitigation, and even if we were to achieve net zero carbon in a certain number of years, the reality is that like our implemented policies are going towards the 3 to 3.5 degrees Celsius. So what this tells us is that like the momentum has started already. We are in the right path of trying to do the climate mitigation to reduce and to reverse the global warming, but there's going to be a period of time when we are going to experience the climate severities, and thus we'll have to be dealing with climate severities, and thus we'll have to be dealing with climate adaptation. This is an excerpt from a report published in 2020 by NRCC, and it is an assessment of the impact of climate change on their public infrastructure. It's a good snapshot of what's happening, especially in Canada. As you can see on the left, it's the overheating issues or a rise in temperature due to the change in global warming. And the next one is the rain and precipitation, and the last one is the wind. In summary, what it tells us is that the most affected areas are the north of Canada and the coastal areas, and more importantly, the order of significance is overheating, rain and precipitation, and then the wind. So that's basically how I would like to set the tone for this panel, and I would like to introduce my panelists here. So we have Michael Lacasse, who is a senior research officer at NRCC and is widely recognized expert in the durability of building signs and building elements. One important item to note about him is he's also a fellow Concordian.
Thank you very much.
Oh, you're welcome. He's an alumni of Concordia, and I really cherish about that. He has written several articles and technical reports over his 30-year career. Next, we have David Altenhoven from RWGI. He's a senior technical director from East Coast for their building enclosure practice. He's a highly experienced building enclosure specialist with a portfolio that encompasses projects of all scales and complexities. He also sits on standards organizations, and he provides his knowledge to the industry. Then we have Craig Applegath, from DIALOG, an award-winning architect, urban designer, and biologist, practicing at the intersection of the built environment and natural ecosystems. Craig plans and designs buildings, campuses, and communities that are zero carbon and climate adaptive, and is an international expert on climate mitigation and an adaptation through sustainable and resilient design strategies. And he's an excellent speaker. I've seen you, Craig, in several of your presentations, and we're really happy to have him here. With that said, the first question to you, Michael. You're at the forefront of research, setting standards, codifying some of these standards. How do you see the bad effects of climate change? What are the climate severities that you're concerned about? What are the things that you're working at NRCC that are going to help the practitioners like us?
Yeah, okay. So, well, I think in the introduction, you gave an overview of how it's going to get warmer, it's going to rain a little more in certain areas of the country, and it may or may not get windy, all depending on where you happen to be located. We've been working on that at the National Research Council for the past 7 or 8 years, and we will continue to do so for at least another 6 or 7. And the whole process is to get some idea of what are the climate change, what do we anticipate in terms of climate change in regards to buildings? What can we project in terms of the types of climate loads that buildings will need to respond to in the years ahead, given the different climate scenarios that may exist? I mean, you're mentioning it's getting warmer, fair enough, but are we likely to exceed the 1.5 degrees scenario? I would say that's a given, and we need to project more severe. We need to really design for more severe situations, as it's more than likely that that's what's going to occur, given the fact that the issue of mitigation is a real challenge around the globe. And even though, for example, in certain countries they have managed to mitigate a lot of their carbon emissions, that is not everyone around the globe. And really it's a global issue, isn't it? So in regards to what else have we been doing, we've been looking at how greenhouse gases affect the climate, and in turn, how the climate itself, as it changes, as you can see here, what types of effects does it have on the building in terms of the thermal response of the building? What about precipitation and wind? And what is the likelihood of degradation, premature degradation of building assets going forward? Certainly in an overheating situation, you have the consideration of overheating within a home, of existing homes. And so that means that the existing homes are, in certain instances and certain locations in Canada, are going to get warmer. We've already had experience of that. We've had some warming situations, extreme heat events, for example, in British Columbia, where in that instance, just over a year ago, 600 people perished because of that. Who are the vulnerable people in all of that? It's the elderly and the younger people. And so those are the populations, I can say, that are vulnerable to extreme heat events. So one needs to think in terms of making changes to the way in which current buildings are put together, and as well offer opportunities for mitigating those effects for the elderly and for the young as well, in schools and in homes where the elderly are housed and so on. So those are the types of things that we've been focusing on at the National Research Council. There's also a question of the effects of wind-driven rain. Wind-driven rain, moisture is the most damaging effect for buildings. And so everyone wants to ensure that the assets that they've put money into, a lot of us perhaps have purchased a home. It's a wood frame home. Increased precipitation increases the risk to premature deterioration of those assets. So what have we done in that respect? We've looked at the climate. We've projected climate loads according to different scenarios, the warming scenarios, and we get an idea of how current buildings would respond to those heightened loads. We know that the loads are going to be more extreme. What does that mean? They'll be more intense, of longer duration, and these extreme events will occur more frequently. So these are the types of things that one needs to think about and do something about. So those types of that precipitation as well leads to events such as flooding. people who are in areas that may be prone to flooding need to take that into consideration. In particular, if it's a question of being able to maintain their insurance situation, right? So people might be disadvantaged from that. So certainly the flood maps are being changed in that respect. And we've developed guides and guidelines in respect to flooding, in respect to other calamities that people in Canada are facing, such as wildfires. So there's elements with regards to how to arrange communities to reduce the risk of being affected by wildfires. We've looked at elements regarding roofing and how roofing design can be changed to accommodate changing climate loads. We're developing as well a guide for building envelope design to adapt building envelope to changing climate loads. We've affected changes to standards related to the durability in buildings as well. We've increased the amount of information that's provided in those standards going forward in regards to climate change or the effects of climate change on buildings. And we continue to focus on developing other standards and methods, be it fenestration, be it cladding, and so on, to help building practitioners have the types of tools necessary for them to make useful decisions going forward in respect to a changing climate.
Thank you, Michael. Seems like lots going on. And I'll follow up with another question about specifically the guidelines that you mentioned and possibly the standards and codes as well. Thank you for that introduction on the severities that are having an impact and that NRCC is actually putting themselves ahead of us to help us. With that question, I would like to go to David. David, as a building enclosure specialist on the field, what are the challenges you're anticipating and you're actually experiencing in terms of climate adaptation? And also, what are the pitfalls that you normally see in the industry? If you can give a brief about
Certainly.
that.
A very big question. I'm going to dial down to maybe some pretty basic issues on day-to-day efforts, right? We've already talked about increased temperatures, increased precipitation, increased wind speeds, everything happening more frequently. A lot of the way we like to think about building enclosure design is that you have this kind of scale of the drawing potential of the building enclosure versus the loads that are introducing moisture. So with climate change, we're seeing the loads that introduce moisture becoming larger and larger. And so we see systems that building enclosure assemblies and systems that used to perform perfectly fine in a variety of climates. As the climate changes, they reach a tipping point, borrowing from famous books, they reach a tipping point and maybe a system that used to work very, very well doesn't work as well any longer, or maybe it tips into failure. And this applies to existing buildings that may or may not be being considered for updates, for renovations by the owner, and new construction. And I think the most classic one are older mass masonry buildings, which resist moisture penetration. There's many issues we brought up about, there's due tornadoes and high wind events and things like that. But just the basic performance. Yeah, they're good for that too. But just the basic keeping the water out, right? The masonry absorbs the rain or the snow, absorbs the moisture, and it has a huge capacity to do that. And then when the rain stops, it evaporates that moisture back out. It dries back out. When we're already seeing buildings where maybe the masonry isn't in really great condition, maybe the mortar joints are a little loose, and now we're seeing things tipping over. And that building that used to perform perfectly fine for an owner of a campus, a university, a hospital, now they're seeing that building maybe starts to have moisture showing up on the inside of the building when it hadn't for years. And that's because it's getting wetter, longer. There's more heat on the outside, driving the moisture deeper in. And so we're seeing buildings hit that tipping point for some existing buildings. And if you put insulation, the yellow bar, if you insulate the inside of the building as part of a renovation because we're trying to hit energy targets, now you completely cut off the drawing to the interior, which was an expensive way to maintain your masonry wall, but it worked. And now it only dries to the outside, and you might start to see deterioration of the masonry. The brick spalls, the stone starts to fail from having too much moisture in it for too long, and then it gets into more freeze-thaw cycles. So we're seeing this at a very fundamental level, just the climate going from a heating-dominated climate to a mixed climate, wetter, more heat, existing buildings having some issues. So, for newer buildings, a very, very basic assembly. Common, I've got a metal cladding on this one, but the cladding doesn't matter. Metal studs with bad insulation, sheathing, some sort of air barrier, that's probably most of the time, vapor permeable, insulation outboard, and on the warm side of that insulation, there's in heating dominated climates, there's traditionally been vapor barriers, or a very highly performing vapor retarder. As the conditions start to shift, that dominant load, that it is most of the time a heating load, cold on the outside, warm on the inside, vapor drive to the exterior, that shifts. And now we're starting to see, oh wait, there's a longer summer period where there's a vapor drive from the exterior pushing in. And depending on what the mix of all these materials are, there's condensation beginning to happen. And maybe it's in the cavity where it's controlled. Okay, a little extra condensation in the insulation layer, no problem. On the other hand, if it gets to be severe enough, and particularly like if this was masonry cladding, so that masonry is absorbing the moisture, then it gets warm from when the sun comes back out and really creates a big inward vapor drive. Now you might see that wall start to have condensation on the face of the vapor barrier inside of the building in a location where you really don't want that to happen. So again, an assembly that probably has been used commonly for years, performs very, very well. Maybe as the climate changes a bit, it tips over into a failure mode. And so maybe the ideas of where are the vapor control lines needs to be adjusted. Where is the insulation? And it gets compounded by the fact that we're adding more and more and more insulation to these walls all the time, so we're getting less and less drying potential. And so we're seeing these relatively modest changes, you would think, and they can take an assembly and push it over the edge into a failure mode. So I think more analysis. We can't take it for granted that business as usual, we've always built it that way for the last 20 years, that's fine. So maybe on a wall assembly like this, maybe the vapor barrier has to be reduced or eliminated, and all of the insulation is moved outboard, or it becomes a variable perm vapor retarder or something like that. But there's an analysis that's probably going to have to come. And the question about what's the climate going to be in Toronto today, what's it going to be in 20 years? You expect this wall to last a lot longer than 20 years. We're probably going to have to think about that a bit more.
Thank you, David. I'll come to you, Greig. As an architect, I'm sure you're dealing much more than the facades, in terms of climate adaptation on projects that you're designing. Do you have a strategy? Do you have an approach that you're using to approach them? And is there a way that we can scale it down from that approach towards building envelope facades and such? If you can give us your thoughts on that.
Sure. Do you want to click the slide there?
Yep. Oh, there's the solution. With the insulation up.
So
Sorry, I have the
That's
control.
that's okay. So first of all, get a sense of the audience. How many here, hands up, are architects? Most of you. Engineers? Okay, so architect dominated. So I'm an architect and biologist. Mark my words, this presentation is sort of the start of what you're going to be hearing again and again and again, is what are we going to do about the impacts of climate change? Not how we mitigate. Yes, we have to mitigate, but what are we going to do to actually adapt our building designs, our campus designs, our site designs to those impacts? And David's slide, extreme temperatures, extreme precipitation, extreme winds, coming not as an average you see on that graph from Michael, but all at once sometimes, right? And blasting through. Looking at the one building, beautiful building, isn't it? Well, what happens when something like Hurricane Hazel comes through Toronto? I mean, all of the things we're designing now assume a very, very, very benign climate. We just won't have that in the future. So what are we doing? We, being RWDI, Alex Lukashko Consulting, ourselves, and one of our clients, Guelph University, have been looking at a protocol so that this won't be branded Dialog or anyone. It's going to be open source, so all you folks can use it. It's a climate adaptation protocol called REACH. And it's called REACH so you can remember it. It's also aspirational REACH. And it's about researching, defining what the challenges are for your particular site or building. Okay, defining the extent of the impacts. What are the big impacts that are going to be happening on the site? So the NRC, all their information interpreted by someone like David here, will be able to be telling you what kinds of impacts are you going to have to design for that have a high probability of happening. Is it going to be winds? Is it going to be flooding? Is it going to be temperature? Is it going to be snow events? Those are the kind of things that you're going to have to start thinking about as you design. And then, what do you do about those? I mean, RWDI can tell you about what the extent is and probabilities and start to give you ideas about the building, but what are the big picture strategies you're going to have for adaptation? And you as an architects and engineering group are going to come up with those, but they're not going to go anywhere unless you can get to the community or your client group or whomever it is that are the stakeholders that make the decisions. You're going to have to work with them to figure out which adaptation strategies they can afford, what they want to do. And then you've got to harmonize that with all of the stuff that goes in behind that, like their budget and their schedule and building code and zoning, and all those things are going to have to be figured into the kind of strategies. So this is our world going forward. Like, we do not live in a benign climate anymore. 1.5, we've blown past it. We're heading towards 2 and maybe 3. The world is totally, I can't use the word, but we've got big challenges. So this is what we're doing right now, and I urge you, we're just in the process of prototyping this, but it will be out public. Use it. It's a protocol for just working with your clients. It's not like LEED with checklist. It just helps you think through what you need to do. A lot of the clients I'm working with now, I say, well, what are you going to do about climate adaptation? And they say, well, we've got a zero carbon action plan. No, that's mitigation. Adaptation is about the impacts. Well, we haven't really thought about it yet. What should we do? So that's what we're doing. And in drilling down into the building envelope, facades, well, this can be a campus-wide, but it can also be what materials can you use? What kind of systems can you use? Are we in Ontario going to have to start using the same kind of glass systems they're using in Miami? In Miami, they have hurricanes all the time, so they have a 2x4 gun that they fire at the windows to test them to make sure that flying debris won't go through the windows. We don't do that here. Will we have to do that here? I don't know. That's something that when we design facades in the future, we'll have to think about. So this is just to give you an idea of what this workbook looks like. It's a sort of a help everyone you and your clients work through these questions.
Thank you, Craig. Yeah, that's a very good point about how we have to also adapt from the other areas where those extremities, those severities are already in place. One example that I can also point out is Calgary, for instance, experiences the most number of freeze-thaw cycles. Is that going to happen here? Yes. I mean, is there a lesson that needs to be learned from there? Yes, right? So it's not just about inventing, it's also about reinventing from the already learned lessons as well. With that said, I would like to go back to Michael about...
freeze-thaw cycles?
No. Well, I know you can go for hours talking about freeze-thaw cycle. But let's talk about what are the core changes that we are anticipating? I mean, you're right in the forefront of seeing what's happening behind, in that area. So what are the core changes that we are anticipating? What are the standards and what are the guidelines that you're working on? You did mention on some of the guidelines, but like maybe if you can be more specific about the facades.
Well, let's start from the basic National Building Code. So what's happening in the National Building Code? So the National Building Code is being changed to take into consideration the effects of climate change. So for those of you who are familiar with the Building Code, in Table C2, Table C2 gives you all of the basic climate information, the moisture index, the 5-minute rainfall, the 20-minute rainfall, all of the different wind loads and so on. All of that is being changed. And one will be able to see on the basis of different climate scenarios what those values now are. And that'll be in the 2025 code. And we'll go beyond that for the 2030 code, and that'll be changed every 5 years as the code is updated as it is every 5 years or so. So that's the type of information that we'll be providing building practitioners going forward. So they'll have something to use as a basis for undertaking adaptation and design. And so that's really where we're going, is how do I retrofit buildings to ensure that the retrofit is adapted to the effects of climate change? What do I need to take into consideration? You know, how much warmer is it going to get? And so on. And so those are the first elements. The other issue, of course, is how long are things going to last, given that the climate loads are all that much more severe and occur more extreme heat and wind-driven rain events occur more frequently. Are we expecting that our assets are going to last as long? So the Canadian Standards Association CSA S478 durability in buildings has been updated once. There's a new edition has been developed from a guideline to a standard. And that will be referenced into the Part 5 of the National Building Code, Part 5 being environmental separation. So those are the types of things that have been taken into consideration. And there's other series of other guidelines that have been put into place as standards related to roofing and how to adapt roofing to the effects of climate change. There will be a guideline on how to adapt the building envelope to the effects of climate change. There's been changes to standards related to the installation of windows, CSA A440.4. And how should the installation of windows be undertaken to ensure that one doesn't get premature deterioration in the building and so on. So there's any number of different elements. We've also, as well, to help building practitioners perhaps model buildings if they have that capability. We also have all climate data for the, 564 locations that are in Table C2. We have hourly climate data for all of the different warming scenarios that people can download and use as a basis for undertaking modeling of moisture effects on buildings. So those are the types of elements that we're putting together. And all sorts of other tools that we feel building practitioners might find useful in informing their designs going forward and taking climate change into consideration.
Thank you, Michael.
Yeah.
I just wanted to highlight a few things that Michael mentioned. about the roofing standard, the CSA 440.6, and also there is a tool, Climate RCI and Roof RCI, that can help. And of course, the durability standard, which if you are familiar with, and you have seen that like some 5 years ago, I mean, this one that you have developed, like the committee that has developed is complete revamp. It's quite extensive, and it's very resourceful. So for those who are trying to digest this climate adaptation needs and how to adapt and such, they are really good starting points. And I'm really happy to say that, EXP, our firm, is involved with NRCC on some of those standards as well. And so they're really good resources. With that said, the next question, David, new buildings as is, or even though they are challenging, to some extent you have a better control of doing climate adaptation on those buildings. But we do have tons and tons of existing buildings, that are aging. And how do you see those, in terms of strategies approaching those existing buildings?
Yes, a big challenge. The presentation about, we need to build a new city, whatever, a day or a month, it seemed was incredible. But I assume part of that equation is there's a huge stock of existing buildings that we need to continue to use or find ways to bring back into use. Of course, those old buildings don't understand all of the changes that that Michael is talking about being put into the codes. And so how do you, we see this question come up quite a lot, often in context of a campus-wide decarbonization plan. What about adaptation of your existing building stock? And of course, there's heritage buildings, beautiful old stone buildings, slate roofs, wonderful. There's also the large number of 1960s, 70s, 80s buildings that probably performed pretty poorly when they were built and perform very poorly now in comparison. So we see a lot of conversation about the effort that it would take to bring a building like that up to a energy performance level suitable for the new climate conditions. The conversations become very challenging. What if it is a beloved building with historic significance, and we find a variety of buildings that are nearly impossible to bring up, say, to a passive house standard, or prohibitively expensive to bring up to a passive house standard? What if it's what if it's a 1980s building with glass and aluminum poor quality curtain wall? Do you just frequently, it's like strip it, reskin it, we'll just throw all that into the trash. So now you get a pretty good question about the carbon, embodied carbon that you're dealing with. So I think the existing building challenge, or the challenge of what to do with our existing building stock to deal with making them suitable for these new climatic conditions and getting them to last. Maybe they've serviced for 100 years already. Can we make them service for another 50 or 100 years? We're going to have to make them service for a different climate than they were designed for, radically different climate from what they were designed for. And I don't think there's any easy answers. There's going to be a lot of investigation and analysis based on a lot of good building science in order to make that happen.
Lots of effort needs to go in.
Yeah.
And it's quite subjective from building to building. With that said, Craig, your undergraduation is in biology. You feel happy about it, and you did mention about the nature-based solutions that you are, that you are interested in and you work with. So, do you want to tell us something about it?
I've got a couple of slides here, and I want to start by making that a bigger question and talking about what kind of solutions have we seen in the past that make sense now, and in fact may make more sense now, given what we're facing. And everyone knows this is a street in Paris, just this classic Haussmann Paris. And what we've got going on here is a very, very climate adaptive design. It's solid masonry, so it's very resilient to wind and force, and if you have a big storm come through and bash out all the windows, they're all wood frames. So you just get a carpenter or a cabinet maker to rebuild them. It's not that difficult. We want to flip to the next slide there. So if you want to see this in terms of what's really going on, first of all, the trees down the LA, down the Rue, are going to be taking the temperature down and also reducing the wind speeds to a certain extent. And what often happens in a severe heat event or storm event is the power grid goes down. Either the transformers overheat and blow, or they're taken out, or the lines go down. And so what happens in a really tall building? Well, the really tall buildings have pumps that pump the water up to the building, and so you're stuck on that 100th floor, wherever, 90th floor, and you don't have any water, and you don't have any air conditioning, and you don't have access to an elevator. The generators may kick in, but they may not last very long. And so this is actually a building design that is designed for that kind of resilience. What happens when the power goes out? You walk up and down the stairs. What happens when the power goes out? Well, mostly the main water pressure, like in Toronto, for example, many cities, will pump up to 10 stories. So you don't need a pump. And for that matter, if the pumps go down in the city you're in, well, you store water in the roof. Like, think of all those wonderful water towers on the top of New York buildings to supply. So I think we've got to be looking at the past to give us a sense of some of the things we can do in the future. We make our buildings very, very, very complicated. Watching the presentations this morning, I was very impressed, but also daunted by how complex our building facades are now. Like, they're just hundreds and hundreds of parts all connected together with various sorts of sealants and glues and connectors and gaskets and stuff. How long does that last, and what happens when you've got a huge windstorm event? So this is a sort of old-fashioned view that we may have to become new-fashioned. Next slide. And so a little bit more high-tech version of this, about 10 years ago when we started thinking about what we do for adaptation, we wanted to look at how biology might help us adapt for heat events. And this is a building that's a tall building that's covered in green screen. Where the screens are covered with ivy and evapotranspiration. That's where the plants suck water up through their stems into the leaves, and they evaporate cooling is about 5 degrees. So all of a sudden, you've got a building that's cooling itself with nature. But the green screens are stainless steel mesh. Guess what? You've got flying debris from wind, and they actually will dampen that down. So you've got a protection against flying debris, you've got some protection against heat, and the building's covered in green. So, I mean, this is not something that 10 years ago people said, no one's ever going to pay for that. That's just way too expensive. Well, let's see what happens in the next few years.
Perfect. Thanks, Greg. Yeah, that's a beautiful looking building. With that said, we're almost there to the end of this panel discussion. So I would like to summarize by showing a few slides. I know that we are in an unprecedented times dealing with climate mitigation and climate adaptation. I know, like, as professionals, we have lots of responsibilities having to juggle between all of these, especially with the current focus on embodied carbon and such. Our professional organizations are trying to support us in some way or the other. For example, like OAA, it's currently mandating the need for professional development training that you got to go through on some of the climate change related items, whether it's climate mitigation or climate adaptation. It's mandated for their professionals. Engineers Canada has published a set of principles that specifically talks about the climate mitigation and climate adaptation. Some of them are really pretty straightforward, including the legal liabilities action, items that they have mentioned, and also, like and they're emphasizing on innovation in terms of mitigation adaptation, working with specialists and stakeholders and such. So it's really on us as professionals to take it upon ourselves to guide, to build better for our communities and so on. With that said, we wanted to leave you with some links. We could always share this at a later time as well. I mean, as much as I can say that, like, you know, we're in the early stages of dealing with climate adaptation, there are already resources available that we can have as a starting guidelines. And of course, there are organizations that are working on, dealing with this on a day-to-day basis. So there is help and there is resources available. With that said, I would like to just get few comments, last round of closing remarks from our panelists, and then I don't have much time. Like I said, I don't want to be between you and the lunch, but with that said, I'll just have the closing remarks, and we'll hang out on the stage so that you can come and see us after this panel session. So with that, Michael, do you have any closing remarks?
Well, I was going to say, expect that there will be changes to the building code with regards to climate change, but over and above that, talking about, how shall I say, low carbon design, there will also be changes to the building code with regards to low carbon design. And the NRC has engaged itself to ensure that construction design or building construction, according to the National Building Code, is going to be take carbon into consideration, the carbon footprints of buildings into consideration going forward. So the entire way in which design it will be done, it will be changed in the next decade or so. So I wish you all well. Well, you can attend my course on climate adaptation that I give at Concordia University. So I'm having a good time with that, and the first set of students have thoroughly enjoyed the offering that I provided. So lots of fun.
Thank you, Michael.
Challenging.
I'm going to echo that and just say that the NRC is a huge resource. Like, it's got a wonderful, deep research, and research that's really gone down the road further than most other countries have gone.
Yes.
And has resources there. So all of the things you need to know about what you're going to have to adapt to, it's covered here. And the new building code will be also codified.
That's a starting point. If you have things that you'd like to get done, tools that you'd like to see, let us know.
Yeah, you need to get to know this guy.
and you're welcome to come and visit anytime, Craig.
Thank you. David, do you have any closing remarks?
I would just say that as an architect in practice for 40 years, things are changing faster than they ever have. Yeah. Step codes that change every 2 years. You have to, and that's for architects, engineers, the entire design community, the construction community. It's going to be very challenging to keep up with the requirements that we just have to meet. Sometimes codified, sometimes just best practice. Yep. But it's going to be, I think, a very challenging time for everyone involved in design and construction because of climate change forces on us.
And lots of opportunities.
And lots of opportunities.
For design, for thoughtful, imaginative, creative
Absolutely.
design.
Absolutely.
Like, this is a time of crisis, but in crises, there are opportunities.
Yeah.
Thank you, gentlemen. Thank you so much.
Thank you very much, gentlemen. That was fantastic. I can't stop thinking about the 2x4 gun and whether it sounds like almost like a design team motivational tool, maybe in addition to a tester. So lunch is coming up. Reminder, please don't bring the food back in here. I'd like to invite all the speakers from the second session back up, and also would like to invite the Zak team to the stage as well. Thank you very much, and we'll be back in about an hour or so. Welcome back, everybody. Looks like lunch has claimed our attrition quite a bit. So hopefully you stick around, because we've got a phenomenal second half to the program. That was delicious food, by the way. Thanks to the MCC for organizing that. So we're going to get right into it, and to kick us off, we've got Amaury Greig from Renzo Piano Architects and David Clusiau from NOR.
come up to the stage, gentlemen, and they're going to be talking to you about the Ontario Court of Justice.
Good afternoon, everybody. So of the two, I'm David Clusiau, and my colleague Amaury Greig. We're working together on this project in partnership, NOR and RPPW. And the project was a P3 process run by Infrastructure Ontario for the Ministry of the Attorney General. And of course, the success, as anybody who's done a P3 know, it's important contribution for all team members in a value for money balance, which is an interesting part of trying to do something bespoke. And in particular, just call attention to Elliston, the contractor, Nippers Helbig, the facade engineering group, BVDA Group Limited, the envelope consultant, Morrison Hirschfield for energy and sustainability, Thiessen Environmental for microclimate, Thornton Tomasetti for blast and threat risk, and Two-Row Architect, our Indigenous consultant, who all made contributions as part of the team specifically to the envelope portion of the project. This P3 pursuit started in 2016 and construction concluded in 2023. At 72,000 square meters, the project is the largest courthouse in Ontario. The pursuit program called for 56 courtrooms, but in the end, given the cost effectiveness of our solution, it was expanded to 63 courtrooms, including numerous specialty courts for youth, mental health, drug, GLADU proceedings, as well as enriched accessibility initiatives, cultural and historic display features, and numerous administrative and specialty support agencies. The project is sited right in the center of downtown Toronto. It's embedded in the northern portion of the main civic block. It's the sort of sandy, empty site in the middle of the upper middle of the slide here, before obviously the building was built. It's bounded by University, Queen Bay, and Dundas. It's adjacent to the Toronto City Hall and the Superior Court of Justice and other significant public institutions. It's got a prominent diagonal corridor relationship to Nathan Phillips Square to the southeast. It's positioned at the north end of an existing judicial precinct, and so it'll be the third component in that arrangement. It's also interestingly, it's not apparent immediately, but it is actually the northern, potentially an extension of the northern terminus of York Street, which presently is terminated by the 1832 Osgoode Hall, the sort of eastern wing of Osgoode Hall. And it's not just an opportunity for a landmark building, it's also an opportunity to knit the mid-block fabric of the city and connect it into the rest of the surrounding fabric. But of course, kind of towering over all of this is its relationship to the new City Hall. This particular aspect of it drove some very specific urban design guidelines. And for the most part, we were in line with that and followed them. There were a few that were distinctly a challenge, though, and we successfully modified them in the pursuit phase. In the fine print there, you can see the reference to a minimum 12-meter height difference between the east and west, and also a desire for a material palette change between those two halves, and in fact, even a requirement that if there's an antenna on the project, it must be located such that its visual impact is minimized. And as you'll see through the design, we kind of ignored those particular requirements of the urban design. This slide really shows the first polemical massing inspiration for the project as a pure cube floating above a more open podium. It's a concept based on creating a building that was, kind of dense, low, and deferential to the City Hall, but at the same time one that has a presence and dignity appropriate to an important justice institution. This split also aligns with the division of the building into a lower public-oriented program of entry, atrium, high-volume courts, and public services, and then a higher tower of main courts and associated support spaces. This this cubic concept, it's initially defined by this sort of main street edges on the slide on portion diagram on the left illustrates that. And it's modified with more detailed articulation, pulling the western side of the building south to respond to the angle of Armory Street, and reinforcing the York Street alignment to the south with a sort of split facade, and modulating the corners to reinforce diagonal relationships to Nathan Phillips Square, breaking down the east and west facades to match the scale of the south entry facade by indents and things like that. This process is really illustrated in these models with the original urban design massing envelope on the left and the final submission on the right, and all of the various iterations in between. While the hand sketches really illustrate the sort of polemical ideas that were behind it, the idea of a grounding of the project and an open podium that reaches out to the urban realm, the York Street axis, which in the end, and this idea of a mast you can see in some of the early sketches, the simple diagrams as you follow along, and then this floating courtroom mass. And then, you know, a fundamental approach to the roof, a refined roof facade on the top, which is treated in a way like another elevation. And, you know, these are the elevational diagrams here that really capture the larger site. The one on the top is showing that axis up York Street. You can barely see behind a bunch of trees at the bottom that portico that represents Osgood Hall. And then stepping up over it, you can see the split in the facade that is the alignment with that facade. And then the lower one is just showing that stepping up of the volumes as it goes from basically Queen Street on the right up through the sites to the left with the tall tower at the top. Marking, but also how they fit into the surrounding context as a kind of, and also I should say the little red dotted line represents the possible building envelope, which we obviously did something quite a bit more dense and smaller than expected. And this diagram shows this the program pushed as far north on the site in order to create a generous plaza, while the section really illustrates this public realm extending into the atrium, while the 13-story tower hovers above. Really, these next two diagrams are the renderings. They really probably more effectively illustrate this, all of these polemical concepts I've just talked about, and also start to illustrate the character of these facades and how they support the reading. And with that, I'm going to turn it over to Amaury.
Thank you, David. So on that, this was the end of the competition. So I'll talk a little bit about a few of the key elements that would be of interest in terms of facade design. Obviously, there's the volume that we refer to as the cube, which isn't completely cubic anymore, but conceptually, anyways, is that way. And so that floats above and houses the bulk of the courtrooms. The atrium space down below, which is essentially a void that's about 20 meters wide by 20 meters deep by 20 meters high. And then one of the more visible elements in the project, the mast that comes and sort of completes that overall. Just very briefly, the project deploys a certain number of different facade typologies. We use a unitized system primarily on the tower. And there are a few feature spaces where we deployed a stick system that you see in turquoise there. And on the north facade, we're using a precast concrete system. The podium in pink is primarily a stick system as well. And then an atrium, at the atrium facade, we used a cable tension system. And we selected these different systems, as David mentioned, specifically to respond to the architectural intent of each of these components. The facade of the tower, the element up above that houses, again, the bulk of the courtrooms, is unique in a way. And it was a unique challenge specifically because it's a huge volume. The facade width is 60 meters, and it's about 80 meters tall and 60 meters deep. So it's a very, very big footprint. And the challenge we had was how do you design a building that's that big without it being completely overwhelming in the city. And so what we wanted to develop was a facade that was quite dynamic in the way it responded to different weather conditions, different times of the day, different lighting conditions. And so we developed a layered system that's composed of corrugated, embossed steel panels, and then a layer in front of that of glass, which is an IGU that completely wraps the facade. At times, the glass is interrupted and the steel appears on the outside, and those are the articulations that you start to see on the outside of the building. This was our submission at the competition stage, and we escaped the PowerPoint for a few minutes and actually brought our one-to-one mock-ups for the presentation and put them outside. And you can see that there is different versions of those embossed panels, because at the stage of the submission we weren't quite sure exactly which one was the right one. We knew that the system was the right way forward. We designed the project to that. We found a cost-effective solution to fabricate that. And with regards to colors, with regards to the density of the pattern, we still knew we had a lot of work to do. And again, the objective being to come as close to be true to the representation that we provided at the competition in the rendering. To the left is a project while it was on site. Again, realized to the left and to the right at the top a rendering, renderings to the bottom, and then a one-to-one mock-up there that was the first mock-up that we made in our office in Paris. Of course, part of the issue was to really understand the scale of the project, to understand the density of the corrugation, the scale of the corrugation. So conveniently, not far from our office, we have another building with walkways, and we sent 2 of our architects up to the top there with different samples. I think for a week we sent them up and down regularly, and every time on the phone, and we'd say, no, turn to the left, turn to the right, and lots of image testing there to be sure that the scale of what we were drawing and producing really corresponded to reality. And as we progressed, we found a fabricator in Germany that could create these embossed panels through a method of hydroforming, which was very interesting because you only need one mold, one face of a mold for the hydroforming, and the rest is a hydraulic pressure rather than a more traditional form of embossing that requires 2 molds. And given that we had a certain number of different formats and types, this was a very advantageous solution. And so this was the first mock-up that we did there in Germany, just outside of Munich. And then the second element, obviously, of the layering is the question of the glass. We spent a lot of time trying to understand which glass product to use. What we did know is that we wanted a glass that was low iron. We wanted a flat glass. We wanted the buildup of the IGU to be extremely flat and consistent on the outside. So we have a laminated face on the outside of the IGU and a monolithic on the inside. The outside face of the 2 laminated sheets of panes of glass on the outside are also annealed. This is something we do very regularly in Europe, and maybe is a little less common here. It helps to reduce the amount of the effect of roller waves or anisotropy. And then, of course, there's a whole bunch of different suppliers, and every supplier has a different quality of glass, a different type of glass. Some will be more adapted to different types of situations. And so we took samples from the variety of suppliers and buildups that we were looking at, and then ended up through these selecting the one that seemed to make the most sense for us. And you see effectively that when you even look at this image, you see very substantial difference between the different panes of glass buildups that we had there. And so number 3 was the one that seemed the best, and that's the one we selected for the project. And of course, then we spent a lot of time on site. So this is the glass assembly plant in Poland. verifying the first samples. These are all oversized formats. They're about 3 meters 50 tall by 96 centimeters wide. And again, using a spectrometer to verify the quality of the glass, and therefore selecting it. And once we'd done that, we built an architectural mock-up. So this is a visual mock-up. This element here was done at the facade contractor's facility just outside of Toronto. The elements are not the real profiles, but it gives us an architectural vision of what the product will be. And so that's not the real steel yet. That's just foam that's been painted, but it is the real glass. And what it enabled us to do was to test the concept. We had both client and the City of Toronto planning department come here to really verify and confirm with us that what we had been showing throughout the competition stage was really what we were going to build. And a little later on, we were able to get to the performance testing. Of course, this is a completely bespoke system, so we had to go through a performance testing phase. And so this is in Montreal, the performance testing, and this is with the real, or the final versions of the embossed steel panels. And you can see the corner elements there are double curved and curved off to the edge with a wing wall glass system that protrudes. And part of the interesting thing about this project, but largely the way we run most of our projects, is that we try to be very present from the very beginning, building one-to-one models in our workshops very early, sharing those with client and then with contractor later on, and then spending a lot of time in the assembly shop as that was being produced. Unfortunately, we were able to do a couple visits, and then COVID struck, and that was no longer possible, so we spent a lot of time with someone walking around with an iPad and everyone else feeling extremely nauseous for hours afterwards, once a week, which was much less effective than being there in person, but I think in the end we got there. And then of course there's the following of the installation. The facade unit there that you see is over 6 meters long by 1.50 meters wide. So we're working on a 1.50 meter wide grid with some very tall spans, and some of the corner pieces are even bigger than that. And again, all this to arrive at a scenario or an architectural expression that is very variable through different climatic conditions. That's articulated and contrasts with the volume below, which is the atrium. Now, the atrium is a very different logic to the tower volume above that houses all the courtrooms, and therefore traditionally tends to be quite opaque. So the tower is only about 40% vision glass, which makes it fairly high performance. So there's 60% of insulated spandrel, 40% of vision glass. Whereas down below, in connection with the city and the urban realm, we wanted the completely opposite effect, which was high transparency. And so that you see on this southwest corner, you see the atrium that's 20 meters tall. And for this corner here, this space, we developed a tension facade system. And so from the early sketches that roughly describe what the initial idea was of a cable system, and then fairly early, we were building one-to-one models in our office that we developed jointly with, of course, working closely with the facade consultant Knippers Helbig, based in Stuttgart and New York, and arriving at developing exactly the glass specification and the combination of elements that enabled us to achieve this highly transparent condition where we have cables every 3 meters and vertical spans of up to 5 meters. Of course, one of the challenges is with the cable tension system is that it moves a lot, which on one hand is very effective based on the performance issues that you face in a courtroom, namely security. But what it means is that one facade component could be moving a huge amount. So there's about a 50 centimeter variation in position of the facade on one side that has to articulate at the outside corner with the other facade that could be going 50 centimeters in the other direction. So the whole facade system, in order to make this corner work, is designed to move in 3 directions at every point of connection, whether it be the hard points of connection on the perimeters or the connection at the corner. Just some of the images of how that was developed. And we integrate a lighting system in the cable wall as well, and on the inside a roller blind system as well to reduce glare. And so the integration of all these elements, including the design right there for the cable support, for the roller blind system, and the integration of the roller blind system, the connection of the cables, was a huge amount of work, but in the end enabled us to achieve this highly transparent condition that we see today. Lastly, as David mentioned, there's the view up York Street looking north, and of course the portico of Osgood Hall that framed that in 1832, yeah. Something like that. And a few decades later came the Superior Court, which is right behind, and this courthouse was the last element in that sequence of the judicial precinct. And so what we wanted to do was find a building that not only framed the sequence of those 3 buildings, but also framed the conclusion of York Street without it being a large, opaque, and dark element at the end of York Street. We wanted something quite bright. And that again spoke to the idea of wrapping the whole envelope in glass and creating a shadow box system rather than an opaque volume with punched windows. And on center of that element is a mast, an architectural mast, and that element speaks to the specificity of a courthouse building as a civic building rather than as a commercial building or as any other typology of building around there. There's a unique importance to the building. The client required, that the Ministry of the Attorney General required, and it has a unique function in society, and so there was an intention to create an element there that would distinguish it from the rest, and at the same time associate it with the 2 buildings in front of it. And so that's an 89-meter mast fabricated in steel in 6 pieces so that it could fit and be compiled into a container. And there are 3 brackets on the facade, but only one of them is actually supporting the mast. So the whole mast rests on the top support bracket, and the others are just there stabilizing that element. And there are 2 knife plates that extend through 2 of the mullions, and they just bolt on there, something you see quite clearly in the model we made in our office, and in the smaller urban scale model there as well. The assembly, of course, was an event also. And again, it's this idea of a glass volume that doesn't impose itself on the heritage-listed Toronto City Hall, nor on Osgood Hall, but at the same time has its own unique presence within the urban context. And I should say lastly, just there is that question of the 6th facade that you can see very clearly if you go up CN Tower. And a courtyard on the top. There's a typology change when we get to the top of the building, and requiring a smaller footprint. And the most effective way to manage that was to carve out the center of the volume and bring natural light in and plant it. There are about 3,600 square meters of photovoltaic cells on the roof as well. Thank you very much.
Thank you very much, gentlemen. our office actually happens to be right next to that building. So I've been seeing it go up for 5 years or so, and it was really nice to see, you know, the whole thing and finished. And that plaza, if you are ever in the neighborhood and want to grab a lunch and just sit there, it is bathed in sunlight. It's just a great civic space, so job well done. Round of applause for the gentleman, and thanks David, thanks Amaury. Next up we've got Ken Maschke, Vice President of Thornton Tomasetti, and he's going to be talking about overcladding mid-century architectural buildings. So come on up.
Great. Hey, thank you. Thank you for the introduction. My name's Ken Maschke, and I'm with Thornton Tomasetti. You may be familiar with some of the super tall buildings and the stadiums and really elaborate facades that our company does around the world and in the States. But don't worry, I'm not going to talk about any of that. Here I'm with our renewal practice. We focus really on existing buildings. So you may call it building science, or you might call it special projects, or you might call it those damn projects with all the existing conditions that we didn't expect. So I thought, though, I would start with an image of the future, a city of the future. I volunteer a lot, or I used to, with the American Society of Civil Engineers, because if you can't tell from my accent, I'm from the States. And I participated in a call where they had pulled together, they had hired some television directors to come up with a city that kids could explore to get inspired about doing civil engineering. And this is what they came up with. Now, they really just went and found all the free models floating around on the internet because they didn't want to generate any new architecture, and they just slapped it into one area. But I don't know about you, but this really didn't inspire me too much as a city, and I thought it was missing some key components of what any city of the future will have, namely the old buildings. You know, we'll talk a little bit more about that. But it has swoopy buildings, it has twisty buildings, it has two different, completely separate architectures stacked one on top of each other, but it doesn't have existing construction. And I guess if our current bylaws are an indication, the city's decided that we really like old 100-year-old masonry facades if we're putting new facade on top or behind it. And we won't talk about it today, but I'm missing the green in this vision, the PV, the wind turbines, right? Everything we need to get to net zero. And possibly, is there too much glass in this future? We can talk about that another day. This, I think, is a city of today. You see a lot more, range of the eras of building construction here. Of course, this is New York City. And some of my colleagues recently participated in a panel with a New York State Commission to look at how to achieve zero carbon objectives for 2060. And the first thing that they realized is that about half of the leasable office space in Manhattan is already 100 years old and will still be in use in 2050. So the path towards greening our cities certainly involves restoring the existing buildings. But you might be saying to me, okay, that's New York. I mean, that's an older city. It's been developed, you know, in a different time frame than Toronto did. Well, I found this map that the city of Toronto put together some years ago that kind of maps out the various eras of construction within our city. The yellow is pre-1900, then the orange and the red are pre-war, and then that pinkish to teal, and then going into light green. That's our mid-century modern time frame. And I think if you balance that, you know, by era, you'll find that there's a lot of work to be done in those buildings that were built post-war in the mid-century era. And that's really what I want to focus on talking about today, overcladding mid-century modern buildings. I plan to do this by speaking to a few different case studies from my experience. We'll go a little deeper in some than others, but basically we'll be focusing on two main different types of typologies, one being a steel office building that we completely overclad with a new curtain wall system on the outside of the building. And then we'll focus on residential buildings, particularly those here in Toronto, where we're doing some type of energy retrofit and renovation to bring them to contemporary standards and keep them viable into the future. The first example is at 1 Indiana Square. So you might ask, when do you decide when to overclad an existing building? One reason might be is if the existing facade was literally blown off the building. And so this was the first overclad that I worked on when I was working out of our Chicago office. And a few different things. We heard about climate change changing the environment. You know, also the construction of buildings in that environment also has an effect on the environment, and we think that's maybe one of the reasons that this building was subjected to something different at this point in its history than previously before. A similar type building we did, speaking of courthouse buildings, is the A.J. Celebrezzi building in Cleveland, which is a federal courthouse building. It was slated to undergo a major retrofit for strengthening of the facade anyway, but then this happened at that downturn in the economy around 2008, and so with a bunch of federal money, they decided to use this as an opportunity to explore overcladding and even more specifically retrofitting with a double skin to have a much more thermally efficient facade. Then, maybe on a slightly lower scale but closer to home, I'm going to talk about two buildings that we're looking at retrofits. One is for Toronto Community Housing to try to do an energy improvement and a facelift on an existing building. And then a separate privately owned brutalist building where we did a form of overcladding and window replacement to reposition that building as well. So what is mid-century modern? Why do we care? That's that period, that post-war period. There's a lot of innovation going on in building materials and systems and types, and some consistency from building to building, and then a whole lot of miscellaneous products in between. You do see a lot more expressed structure, less ornamentation. I think these are some of the prettier examples locally, although some others get a bad rap. Regardless, they're here to stay. And unfortunately, they tend to perform very poorly. I would guess that the intent when they were sizing mechanical systems was to assume that the mechanical systems could overcome any lack of thermal efficiency in the envelopes themselves. I took the pictures away to focus in maybe on some of those problematic aspects of the envelope, like single pane glazing, non-thermally broken window frames, a big bugaboo of mine, which are the thermally broken slab edges, which come to mind, I guess we're still doing on a lot of the towers I see being built around town. You know, masonry assemblies that don't drain, and okay, we've been through it before. What does one of these buildings look like prior to renovation? Here's an example of our Sherbourne Estates project before we started touching it. A lot of damage up at the parapet, throughout on the masonry knee walls. If you look closely enough, you'll find that some of the slab edges deflect in a challenging manner for the window installers, as they would find out later on in construction. We zoom in a little bit more to those knee walls. There's a lot of masonry distress. Don't be fooled in the picture with the blue skin. That's not original 1965 era blue skin. We're just seeing that brick facade fail for a second or maybe third time, right? The concrete's not faring too terribly good either. The beautiful fluting that the contractor spent lots of time forming in the original construction has reduced the amount of cover on the rebar, leading that to spall off and cause the structural concern. The problems aren't limited just to the exterior material failures. I actually started showing this picture to people I was trying to hire as a test of their building science ability. Does anybody want to guess, based on this thermal image, or have a theory of what's happening at that juncture between the wall and the slab? Why it's colder there? That's our thermal bridge again. Although the wall has insulation on the inside, the slab is continuous to the wall, and on the outside of that shear wall, there's nothing protecting it. So that dark band is all the heat loss at the slab edge to the exterior. Our windows on a lot of these buildings, I jumped buildings here, but we might have found the same type of conditions all around the city of Toronto. The knee wall assemblies, this inch of styrofoam is about as good as you're going to get on those knee walls anywhere in Toronto. You might even find that you've got metal lath in the assembly that's starting to corrode and deteriorate. This image is taken from one of those office tower buildings, the A.J. Celebrezzi building, showing a beautifully continuous stainless steel window frame and a single pane window. So there's a lot to consider, and so now I'm going to step through some of the design methodology and how we approach retrofitting these types of buildings. I kind of break this down into three components to shield the existing structure. So one idea is, that masonry deterioration, everything that's happening there. Let's take an approach that protects the existing facade. Let's obviously insulate the building, make it perform better, increase the R value, reduce the EUI. And then importantly, and we've heard about this earlier today too, we need to make sure that we manage the moisture, both that from the driving rain and the hydrothermal effects. You could further explode this into a whole matrix of different ideas and thoughts that we'd want to talk about. Thermal performance maybe being the one today that brings these types of projects to our desk. At the St. Clair project that I was telling you about, we tried to break down where we thought the heat transfer, where the heat loss was happening, and we pegged most of it on the windows, but a surprisingly large amount on those exposed slab edges, despite the fact that they make up about 8 inches versus 10 feet of a typical floor. And then, of course, the exposed shear walls and everything else, and the knee walls have a smaller effect. Here's more thermal images on a different building, but same idea. This looking from the outside at night, and you can see the warmer bands where the slab edges are. Not all of the balconies are continuous, so you're certainly losing there, but we're also losing at the facades where they're exposed. So as we pick up these projects and start evaluating it, one thing we do is build some therm models to see the effects of different types of insulation. Of course, we've learned early on that we need to wrap the whole slab edge to really make any effect. If we're just protecting and insulating up at the top level, or if we're just adding insulation on the inside of these types of assemblies, we're not doing as much good as we think because so much loss, again, is going through the slab. Hydrothermal performance is very important. We've heard so many times before, how when you improve the windows, you actually reduce your heating demands, that you get less internal heating, less airflow through the facade, and all of a sudden it's a little harder to manage the moisture that's coming in, migrating in through your wall or in the ambient. And I could tell you some amazing examples of in some of the projects we've done of the humidity levels that people have managed to create their own little rainforests in their units to a really fantastic scale. The image here is not from one of these projects, but it is meant to demonstrate increasing moisture in the assembly over time. Another concern, of course, is the structural performance. At a project like 1 Indiana Square, where a microburst of wind literally rips the facade out, it's easy to understand what your structural requirements would be. But the good news is that there are options. I mean, new materials are generally lighter than the older materials that were used. A lot of those structures are also quite robustly engineered, and if you core your concrete, you're going to find that the concrete strength is generally greater than it was, or than what was specified on the drawings. So there are opportunities here to do structural strengthening to actually facilitate improvements. Another aspect to the structural design of overclads is to pay particular attention to what you are connecting to. Maybe the most common type of overcladding we see is putting some type of ephes on top of an existing brick assembly. But that the connection, the structural connection there is only as good as how deep your connectors go. So you have to know whether you need to anchor through the existing veneer back to structure, or whether your existing veneer is well tied to the backup itself. Here are some examples where we found we needed some supplemental tiebacks to strengthen. The one on the left, there was a shear wall abutting up, a little bit of infill, and while some parts of the building had adequate tiebacks, here we had none because of a unique intersection in the construction where it just wasn't practical for them to have had the original ties installed. They could have come up with something. The second case is a fire station up in Vaughan, where in this pier they just decided to put whatever they had laying around on site as opposed to making an extra trip to the dump. And then finally, and most importantly in these design considerations for existing buildings, has to be constructability. I know it's important in new construction as well, but for the existing, you have to assume that many of these projects that I'm talking about, the building will remain occupied throughout the entire construction sequence. Now, you might be able to move tenants in and out of their space, or if it's an office building, in and out of spaces at a time, but most of this work, most owners don't have the luxury to completely evacuate a large building while this happens and then bring it on. But the good news is there are strategies we can do it. The main strategy we took on the towers was to build outriggers that connected to the structural columns and then poked out through the existing facade. We built a series of tube girts all around the existing building, and then the new facade was constructed on those girts, enclosed, and then whatever needed to happen on the inside happened on a secondary phase. So throughout, the building was able to stay occupied. Here's what one of those details looks like of the outrigger coming out and connecting. Now, you also need to do a lot of investigation to understand what else you might encounter, like mechanical systems that were designed in chases that would run down the columns. We had to work around that. We had to make sure that all the welding was accessible and could be properly performed and tested. So, a lot to think about, but it can be done. Okay, so on to some retrofit strategies. Whoop, I'm going forward still. Okay. Most of the time, I think, your envelope repair or overclad is going to happen in the context of a more holistic renovation. In the case of the Sherborne project, there was a whole changing of the heating and cooling system from one that's gas-powered to electric, and that's probably the main mode that we're going to be working in to electrify our buildings. But with that in mind, we might also break down what our options are into some specific typologies. And I categorize this as option one being to the repair and refresh, where we're going to replace windows and add some insulation on the inside and do a little bit of a touch, but save some of that exterior cost. Number two would be the opposite of that, which would be a complete curtain wall overclad. It could be it could be at a residential building like what's depicted, or more like those larger towers that I talked about. And then the third is some kind of hybrid between those things. We're going to use we're going to replace fixed windows, but then maybe we use some different type of metal panel or eaves on the knee walls. We're going to combine these together in the most cost-efficient and constructible method available. Breaking out that hybrid option a little bit more, you've got the whole world of options that you want to design with, from eaves to any type of rain screen. And then on our Sherborne project, we actually put curtain wall in front of that existing knee wall, and that protected the brick. We didn't have to go and do very detailed repairs to the brick. We could protect it, leave it in place, but then build a new envelope in front of it. And for those who like looking at the particular details, this was that main typical detail, and many thanks to our friends at Zeidler Architecture, who were the design architects on this project, for helping me with this slide. And this identifies some of the main components there, but identifying between A, which is the glazing replacement, and item C, which is the curtain wall. And then, of course, you know the magic and the pain in this project is going to be the transitions between all of those main primary overcladding types. This mock-up puts the transformation of the building into context, where you see in the bottom middle of the page the renovated suite versus the existing above. Every time we do one of these projects, of course, we learn a whole lot more about the existing substrate we're trying to connect to. I shouldn't have picked pictures that made it look so easy and consistent, but oftentimes you pull out that existing window and you wonder how the wall stood up for the last 50 years. It's always something you have to deal with. Here's windows going in, coming out. You can disregard the arrows on this because this is pulled straight from a site report. I'm not trying to show on the right the ideal way to do the transition. In fact, those are my markups for things that they did wrong in the mock-up, including putting sealant over top of the weeps, using an exposed tapcon, and not anchoring the bottom side. So it has a lot to do to coordinate these transitions between different parts of your facade if you're trying to mix and match a hybrid system. Another aspect of this mix and match transition is being able to design for flexibility in the non-conforming existing conditions. You'll note that that flashing is composed of two different pieces. That's because we found, as we started along the project, we needed to accommodate both vertical and horizontal differences in the planes of the window and the curtain wall because of the way that the existing construction was built. And then here's a beautiful overview of the sites now. So if you're down on Sherborne Street, you will have the opportunity to enjoy what look like new, bright white towers that are actually quite old. And I'm going to leave it there, skip these other two. We could talk EIFs until we're blue in the face, but I think my time is up. Thank you.
Thanks a lot, Ken. I actually started my career in restoration engineering, so those kinds of site visits, photos are near and dear to my heart. So for new buildings get all the shiny press, right? But for every one new building we build, there's 49 ones that we have to retrofit. There is no path to 1.5 degrees, 2 degrees, 3 degrees that doesn't go directly through deep retrofit. So one thing to take away today is whenever there's another need for a reclad, whether it's performance issues or modernization, please, please, please consider it as an opportunity to decarbonize. One of the challenges we often face are high hot water temperatures. We can't satisfy those with current heat pumps, so we try to bring that load down. So don't do like for like, please. Thanks, Ken. That was fantastic. Okay, next we've got Dean White from Cosentino. Thanks. Come on up, Dean.
Thanks. Everybody hear me fine? Oh, I stepped in front of the speaker, so that does work. Thank you very much for spending time with me this afternoon. I'm honored to get in front of you and talk about Cosentino, talk about our product Decton, talk about our sustainability, approach to sustainability, what is Decton ultra compact stone, how can you get on the wall some design considerations we'll talk about, and basically roll from there. So it's a short presentation, and I welcome you to come and visit us over at our tabletop afterwards, ask any questions, and get familiar with us. So Cosentino is a company that is a Spanish company, started in the late 1940s as a marble manufacturer. We're still the third largest exporter of natural stone on the planet. We branched into quartz in the 80s and brought that to market in 1990. Very large part of our business. But what I'm talking to you about today is a product called Decton Ultra Compact Stone, and we'll talk about it in a bit more detail. So we're in, I think, 150 different countries now, 6,000 plus employees. We distribute our own product. We're in control of our own destiny. We have a lot of different system partners across the globe that we're very thankful for, that work to get our product on the wall into the different designs and the projects we're involved in all over the country. We have 3 production lines of Decton in Spain. They're about 1 kilometer long each, and we produce approximately 250,000 square foot a day of Decton. And it's not only used for facades, so luckily I don't have all that pressure to sell 250,000 square feet a day, which would be pretty tough. But we have a lot of capacity, and we're growing that capacity as well. Sustainability is very important to Cosentino, and we take a 3-pillared approach: the environmental, the social, and the governance. And I'll talk about social and governance first, and circle back to the environmental and the physical side. So on the social side, it's our commitment to be having a long-lasting, positive, sustainable impact on the communities that we're in. So we're still manufacturing in the same place that we started in late 1940s and near Almeria, Spain. We're the largest employer in that area. We give back to the community that we're in there. We also give back to the communities that we're in across the globe. For instance, our headquarters in North America is in Miami. We do clean up the ocean type projects and so forth. Our people physically go there and do this type of work. So it's really important for us to be a sustainable partner in the communities that we're in. Governance means that we're transparent about all our efforts around sustainability. We produce regular reports talking about our efforts, what the impact is that we're having, and it's third-party verified. That's really important. When we talk about the environmental or the physical side, this is where we've moved to a model and looking at our business as part of a circular economy. So the products we bring to market live in this ecosystem, and we work to minimize our carbon footprint and things like this. So, 25 years ago, this would not be a focus for a manufacturer. They'd have a product that they design, and then they'd sell it, but we weren't thinking about buying raw material from someone else that has a sustainable approach and so forth. So the first step is we procure raw materials from partners that also have sustainable approaches. If we have 2 vendors, one is sustainable, one's not, even if there's a price variance, we're going to choose the one that's sustainable because it's more aligned with our philosophy and the long-term goals that we have. Innovation and design from the start to be environmentally innovative, essentially. So we design to be sustainable from the start. And that means, are we using recycled content? How are we going to manufacture that product? What kind of energy we're going to use, et cetera. That's thought about at the start, not at the end. Best available technology is really important on the production side. So a Decton production line is about 1 kilometer long, and the last 200 meters are ovens. Our ovens currently run on natural gas, and we offset those emissions with carbon credits or projects we invest in around the globe to get to a carbon neutral status. But we're actually changing those ovens from natural gas to hydrogen. So that'll bring our emissions down considerably once we do that. It's somewhat of a phased approach because you can run both at the same time, and the goal is to get to completely hydrogen. So that's important. Energy efficiency is really important, also the energy sources you're using. If I jump back one here, or a couple, you can see our facility here, and in the foreground, you can see the largest self-consuming solar farm in Europe. And that only provides us with about 15% of the power we use. This is a bit of an older picture, so you don't see a lot of rooftop solar yet. There's more buildings now, and they're all covered in rooftop solar. So we're managing to get to about 20% of our consumption, and all the other consumption we have is certified renewable from wind or solar. So the entire factory runs on renewable electricity, and we use the equivalent of about 400,000 homes worth of electricity. So it's very important. You can also see that picture, there's quite a bit of greenery. This is about an hour from where they used to film all those Clint Eastwood westerns, very dry desert type conditions, this is for a couple weeks of the year. The rest of the time it looks like you're in a desert, very, very dry and brown. And that means water is a very valuable resource in that environment. We bring water into our production systems, we recycle 99%, and we don't have any discharge of water. So we recycle, we lose through evaporation, we lose some through a green belt that we feed around the facility. And we've even gone to the point where we've built a treatment facility to recycle the water from the communities around us. So we try and make sure to use as much as we can and keep it in there without drawing from more outside source. Waste, very important in a manufacturing environment. Not only how do you handle waste, how much waste you have, but our goal is zero waste. So if we bring raw materials in, we want to use all of the raw materials we use either in our own product or it gets used for a secondary source. So for instance, we're recycling product that's falling off during production, and we got some colors in Decton that are 100% recycled content. That's an important part of it. But what we can't currently reintegrate, we stockpile in our waste management system, and our R&D department is constantly working on finding ways that we use every bit of the raw material that comes into the facility. Of course, emissions is important. We talked about that already. One of the ways we reduce our emissions is not only with our furnaces, but also how we move product around the facilities. So we've got robots that move our product around. We don't have a lot of forklifts. We don't have a lot of human drivers moving slabs around the facility, because if you're like me, you stop, you talk to your buddy who might be 50 feet off the path, you have a quick little 2-minute conversation, you go back on your way, you keep adding emissions all day long. Robots have no friends. They just go from point to point, and they keep that. They might in the future, you know, AIA might develop that way, but right now they don't have any friends. And they keep the emissions down by doing that. We also work to partner with, getting our product around the globe. At any given time, you know, we've probably got $100 million worth of inventory that's on boats and containers moving across the globe. So we really try and find partners and we try and move that material as efficient as possible to try and keep the emissions down. The other thing about Decton is quite unique is it has a very long life cycle and a very low maintenance. So that means that the amount of energy that's going to go into maintaining the product over its life cycle is quite low, and it brings its life cycle cost down some as well. So that's important. And the end-of-life recycling, Decton is end-of-life recycling, even though it's got a 50, 60, 70-year lifespan or more. We calculate our carbon neutrality from cradle to grave. That means the emissions to get it to any point on the planet, and from any point in the planet back to our facility in Spain. And that's how we calculate in our carbon neutrality. So what is ultra-compact stone? You're going to hear terms about this material. You might hear ultra-compact stone, ultra-compact surface, sintered compact surface, sintered stone. Those are a bunch of names for products that are in the same family. They all have slight differences, but they have a lot of similar characteristics. They are a product where an all-natural inorganic product where we mine 20 plus different minerals out of the earth. We pulverize them down, we mix them in water to get the right particulate size, and store them in silos where we dry them out and leave just enough humidity in there to form a slab. So this is a slab product. It's not an extruded product, which is important from a design aspect because you're not going to have curved surfaces. It's a dead flat product. So it's a slab product, comes out, moves down the production line, and the first big station it hits is a 25,000-ton press. And that press is the equivalent of about 2.5 Eiffel Towers. Presses the material for 10 seconds and makes it ultra-compact. That's where that terminology comes from, and very dense. And then it moves down and it hits the 3 different decorating stations where we drop mineral pigments, again, inorganic mineral pigments, natural pigments, onto the material to create patterns and depth and so forth. And then once it leaves there, it continues down, and the last major station it hits are the ovens. And in these ovens, what we do is we heat it up to just about 2,300 degrees Fahrenheit, and we get it to a liquid state. So it's not running like water, but it's back to a liquid state. And then when it cools, everything bonds at the molecular level and gives it some other very good physical properties. So some of these properties that we have there, it's UV stable. So the colors on it will look the same 40 years down the road. If it happens to be an environment where it's taken on dust or grease, you can just wash it off and it'll look just like new. So it's not going to degrade or fade over time, at least not to the human eye. Okay, there might be some minute changes, but nothing we're going to pick up with our human eye. It's non-combustible. We tested it to the Canuel C S135 test, not the S114. S135 gets used for composite products a bit more. And the reason we tested at that standard is that when we do a ventilated rain screen or we do a curtain wall application, we put a fiberglass mesh on the back of the material, and that mesh is adhered with an epoxy. So we've got three materials. We've got the Dectin, the epoxy, and the mesh. And that mesh is added as fall protection. So if it's up at height, gets hit by a crane, you don't have shards falling down on people's heads. That's the purpose, and that's why we use that test. And the end result is it's non-combustible. It's also very non-porous based on the way it's manufactured with that compaction and also going through the ovens. Has a very low water absorption rate. It means that that non-porosity makes it graffiti and stain proof. So if graffiti goes on it, you can wash it off the same day or 10 years down the road using soap and water or a pressure washer. You don't have to recoat or do anything like that. It'll come off and you'll have your material looking like new. It has a low coefficient of thermal expansion. It's relatively inert, so you still have to leave gaps between panels because everything else in the building is going to be moving. But the Dectin itself is one of the elements that is relatively inert. Large format, we'll talk about in a minute. Very dimensional, consistent. This type of material is manufactured in highly automated facilities. It's the same gauge all the way across the slab. It's the same density through the product, which makes it different than most porcelains, where a porcelain might be denser on the surface, softer behind, different gauge across its sheet or slab size. So very, very consistent product. It's dead flat. Designs mean when you're doing a panel, it's going to have a flat plane, no curved surfaces. You can do segmented curves, etc., but the surface of the material itself, you cannot curve. We are experimenting with reheating it like you do with glass. Down the road, you might see Dectin with curved surface. That's our R&D department at work, and we'll see how they do. Very durable. It's 7 on the Mohs scale, so diamonds or topaz will scratch it or itself. Highly impact resistant. Many of you in the room are familiar with Miami-Dade NOA. So when you do that test, one part of that test, other than just staying on the wall for the whole wall assembly performing, is a missile test where they fire a missile at it and they see what kind of damage is going to happen because a lot of the injuries come from flying debris. So if you used a 4mm, 8mm Dectin, that missile is going to go through it. But when you use a 12mm half-inch Dectin, when the missile hits it, the missile shatters. So it has high impact resistance. Of course, from a design element, that means depending on where you put it on the building, how much contact there's going to be, you might look at using thicker rather than thinner Dectin at that place, like say emergency entrance into a hospital, etc. It's easy to clean and maintain, like I said, low life cycle costs, carbon neutrality, and it's got a 25-year material and finish warranty. So the format, we have 3 production lines now. Up until the fall of 2022, we had 2, and they did a 1440 by 3200 millimeter size panel, or 56 by 126 for us people that didn't convert properly in 1976. 664 by 130 off our 3rd production line. This is really key because we got past that 5 foot width to help us with unitized type projects, for instance. 4 primary thicknesses, 4, 8, 12, and 20. 12 and 8 are most commonly used in ventilated rain screens. And curtain wall. You do see 20mm used often when it's a mason or you've got a place that has extremely high impact, you'll go and use the thicker material. 70 plus different standard colors, many of them very conducive to facades, a lot of stone-like colors, very good value engineered option for natural limestone. And we have a new wood collection coming this summer. We have wood before, but that's coming in July. 20% to 100% recycled content in the colors. This is an old slide, I should update it. Customization is something we do very well, and we do it for less minimum square footage than other companies in the same space. So we'll do a completely from scratch custom color for 25,000 square feet. If we take existing color and existing texture and bring them together in a new combination, then it's anywhere from a 10 to 15,000 square foot minimum. The job you're looking at here is in the West Coast, originally designed with an ultra high performance concrete with a terracotta color. Curtain wall contractor came to us and says, we want to use Dectin. Do you have, first of all, a terracotta type color? We said, yes, we do. Then the architect said, I'd like to have more texture. We took texture we already had added to it. And now we've got a 94,000 square foot project that it's in Seattle, so it's on hold, but hopefully we'll see it sometime in the next future years. One thing unique about this is you all know that when you're working on a facade, the waste of the material you're using impacts the cost. So this was not designed with us in mind initially. We had 49% waste driving up the cost. I knew that we had the larger sizes coming later on that year, so I said price it with that new size material, and that brought the waste down to 25%, which was really key. Another example of that is we also have on line 3, we can do custom slab sizes, and this is very huge. So we've got a list of widths and lengths that we can bring into different combinations to make a custom slab size that will bring the waste down even more. I had a job that was 38%. We used a custom slab size. We brought it down to 10% waste. That flexibility that we've built in to our newest production line is really key. What you see in the bottom left are solid colors that we have developed that we don't actually stock or really advertise much. We use it to go after specific facade projects where we compete against high-pressure laminates, fiber cements, terracottas that use those solid colors. We supply in full slabs. We have partners that do fabrication with full slabs. We provide cut to size with no holes or grooves. A good example would be a curtain wall company that might be glazing into a spandrel. We cut it to size and they put it into their mullions. We also supply cut to size with holes for undercut anchors or grooves for perimeter kerf type systems, always with a mesh. Lead time to the east here is about 10 to 12 weeks from the time the shops are signed off on till we deliver to the customer. I want to talk a little bit more about our third production line that we brought in. It doubled our capacity, which was really important. It's more flexible. We can change the plates on the press to make custom textures or other textures much easier and for less money, so we can do a custom texture for a large project. We do the custom slab sizes, and we're able to do through body colors. If you know something about ultra compact materials, they usually have a solid base color, and then they have different patterns on the surface. We can actually do through body colors now. It took a little bit to figure out. Unlike, say, a quartz product where you can run the veining through very easily, with a product that's compacted, you got to be able to put that so that when you compact it, you don't flatten it out like a 7-layer dip, and you can actually see the pattern running through. So we figured that out. So we have more of those coming. Facade applications, ventilated range screens, curtain wall, and old directed adhered vertical tiling. We have a lot of different attachment methods for ventilated range screens and for curtain walls as a matter of fact as well. From pressure equalized systems, undercut anchors, honeycomb partners. A lot of the partners that work with Decton are here in the room next to us today. We're very proud to work with these people that provide quality systems and service to the market, to kerf, groove, etc. And we've got a bunch of different suppliers of subsystems all the way across North America to hit different budget points. For curtain wall integration, we did some typical details that nobody will ever use because they have their own, but we just wanted to visually show how easy it is to glaze it in. So in a captured system, you see a little job here that's actually on Avenue Road where it's glazed into the spandrels in a captured system. Here we've got it with SSG type install. And in a unitized wall, what we have here is a Cap West project in Germany where they provided us with their anchors. We put them on the deck, then they hung them on their walls, stacked them on the site, put the panels at grade after they had the measurements at grade. And one more case study here. This is Toha in Tel Aviv. And this project is a building that's flipped on its head. The mechanical's all down below. The top is a restaurant. The rest is offices. And you can see in the second picture from the left, the panels are coming in together in an X shape so they can provide ventilation to the mechanical area. 11 different colors, 6 of them custom on there. Decton's unique and universal. You can use it everywhere. There's a hard surface, interior, exterior, facades, hardscaping, etc. Come by and see us. We'd love to talk to you. Thank you.
Thanks, Dean. Next up, we've got Alison Modl from Diamond Schmidt, and BIPV, I think, is going to be the topic, so stay tuned for more.
Oh, okay, great. Awesome. Okay. I'm Alison Modl, an associate with Diamond Schmidt Architects, and thank you, Zak, for having me. And I'll be speaking about the Scarborough Academy of Medicine and Integrated Health, which is a new building going to be found on the U of T Scarborough campus. This project was developed with Diamond Schmidt Architects in association with MVRDV, under the contract of a design build with Ellis Don. So yes, we are proud to showcase how facade supported the design statement for Sam IH. And what is that statement? Sam IH is a place for healing, learning, and bringing community together. So this origin story started with U of T wanting to bring their medical program to the Scarborough campus. This was before COVID, and as you know, COVID hit, and unfortunately the community of Scarborough was hit with some of the highest death rates and the highest rates of retiring medical professionals, meaning that community was dearly in need. So the goal is that there's a statistic that medical professionals will stay to serve in the area where they went to school. So meaning if they were to bring a school to the university, they will eventually be serving the larger campus abroad and the community members. So we believe that this mission statement is well aligned with the university's goals. Developing a concept. So the design team really did just start at the pursuit phase where we began our story. And the idea was that we needed to find design ideas and statements to support that of what we're trying to conclude for the bringing community together. So we began our research. It started off with the medical program brought to us from U of T and what had to be brought into the building. Here you see research of the site where it was clear at the intersection of Morningside, right across from TPAS. I'll highlight this. TPAS being the larger building, the Toronto Pan Am Centre, was the intersection of two major urban fabrics. Those urban fabrics being a residential to the left and the institutional on the right. Again, being separated by the Morningside, becoming a gateway to enter into the campus. We also had a plan for the future condition of a secondary plan with an LRT coming across in front of the Toronto Pan Am Centre. Here as well as a future pedestrian mews to the south. So we knew that where this site will be located, there'll be a junction of local residents, future practitioners, and established academics, as well as visiting athletes. Ecologically, we looked at the site as being part of the Highland Creek Ravine that sprawls across the entire Scarborough campus. And looking at this image, it was very clear that where our site will be at the northern tip of this ravine. But there was already motifs being found on the U of T campus, already being immersed in nature, starting in 1964 with the John Andrews building, with its unique offset levels mimicking the topography of the ravine. And also apparent that the ravine has already overcome some of the building with its greenery and really made Scarborough unique to other U of T campuses. But not only ecological values, but Indigenous values found with the lands of the Huron, Wendat, the Seneca, and the Mississauga the Credit for storytelling and plants with medicinal properties. So we knew that there's going to be opportunities that we can give Indigenous user groups to tell their story and how they would like to collaborate with the space. For this site, it was apparent that there was tons of opportunities for soil gain on the site, but we still had to be cautious about future massing and how those shadows played into effect. So we had all this site research, and we wanted to compile it into a few design objectives to get our massing design and pitch our idea to the pursuit. One was creating a beacon to the campus, 2, spaces for interaction with public and academic, 3, transparencies to welcome guests seamlessly from inside to outside, and 4, sustainability targets in a way that would give back to the landscape. So although obviously there was tons of different design iterations, I'll just go through of how the current design came through this massing diagram. So first we started off by just illustrating the future context with the TPAS building across and the future pedestrian mews. We maxed out our zoning envelope right on the site. Then we started cutting back to propose programmatical elements. For example, at the tip, cutting back to allow a public square. Cutting off the back of the massing to limit shadows on future developments. Articulating further the tip of the gateway, offering coverage and a focal point of that public square. splitting the massing in locations that was intended to be part of the public realm in both the present and the future context. Overlaying that academic program and seeing where it made fit and finding efficiencies while adjusting the massing as required. Looking for opportunities within the massing to find those visual connections to the exterior, as well opening up to the public realm at that square at the ground level. And where do we denote entrances? What made sense for future and present trails? And altogether tying together with biophilic materiality as the extension of the ravine to the south, transforming the building as an extension of the landscape. And there you have it. That final massing concluded, and it came with the task of how do we transcribe that? How do we transcribe the facade in supporting this design? And how do, as architects, become storytellers and clearly articulating through this pursuit process how we're sending that message? So I'll bring up that message again, reflecting on that, of it being a place for healing, learning, and bringing community together. Because again, this is a pursuit. There could be the same mission statement for other team members, but how does our design team effectively communicate this to the client, to the university? So we articulated our design ideas by using the 4 criteria of bringing in the ravine, building community, soaking in the sun, and working together. First being bringing in the ravine, and using diagrams that were used to illustrate the ravine becoming part of the building, and therefore the major crossroad of the campus. Even through visual renderings, it was clear that the building was becoming the part of that tip of the ravine. And looking closer into the facade, how we wanted the larger curtain wall to show transparency between the inside and the outside, showing plans continuing into the interior. Just a few more renders there, showing materiality of how it comes through into the interior space. The atrium itself in that volume is a 3D representation and pays homage to the deeper valleys found in the topography adjacent to the site. 2, building community, which is encouraging future practitioners, visitors, academics, and the community to collaborate organically. Hold on 1 second. So here we're found splitting the massing program and how it was organized through the stacking of offices to the west and the research labs to the east, and allowing that middle zone to be the interaction zones for the cross-pollination of ideas. But when we look at it in plan, it really becomes a metaphor of 2 rocks being split with water and the flow of people becoming that and connecting energy through the 2 floor plates. So here you can see cutting through the atrium space and how the flow of people really livens up that 3D volume, which we hope to see from the exterior as well. And that cross-pollination between people discussing with other people and people interacting with nature. Shown also from the exterior, and also those social spaces becoming an extension of the exterior space. Just a few more of the interior. 3rd, soaking in the sun, and where I'll get into our BIPVs, which was really inspired by the health professionals healing patients within the building, while the building itself heals our planet, gathering energy from the sun. Going back to our site study, we understood where the sun was going to be exposed. We knew this immense value of sun that will be captured if we were to integrate it through solar panels. And typically we see solar panels just on angled frames on rooftops. However, there's now a new technology, most of you know, BIPVs, known as building integrated photovoltaics, which are simply put as solar cells being integrated as part of your exterior wall cladding. So this is actually Diamond Schmidt's first stab at it back in 2014, where it's literally solar cells on the building. Very simple, and found in London back in 2014, as mentioned. But since then, we've grown a lot. Now you can see it integrated into rain screens here at Red River College, where that gold facade panel are actually solar cells, as well as Fanshawe College back in 2019. So I'd like to just take a moment to appreciate not how designers and architects have been using these products, but to also the manufacturers and suppliers that you've come a long way back since 2014, and you can now see how far design has developed and what opportunities we might have in the future. So how does this apply to SAM IH? So back to our product, involved through a facade performance tool, quantifying the amount of energy we could capture through the site. Meanwhile, at the same time, we're looking at opportunities how the cladding could be supported to mimic the natural reflections found in rocks, and taking advantage how that facade could really support our design narrative. As well, to capture more energy. We did put some on the roof, so we didn't just use the BIPB within the panels. But while you look at this image, even though you can't see the solar cells, it's important to know that these renders do support the larger integration of renewable energy and harvesting that didn't compromise on the aesthetics or the design message. And goes to a cladding design that's more than a skin deep. It surpasses a skin deep design intent. The last narrative is working together, demonstrating how the design is informed by a collaborative of expertise. So with our team of consultants working together, it was critical for integrating sustainable and smart design features. Looking just at the structural framing and optimizing how grid spacing allowed for the more prescriptive lab layout to be more flexible with retrofitting. Working together with mechanical and electrical engineers to develop a heat exchange loop within the atrium, but was also hidden with architectural features. Looking at the building facade and not just the photovoltaics, but ensuring high energy performance windows or high performance windows to lower the energy usage of the building. And biophilic principles working together to improve the wellness of the occupants. So all this coming together, these sustainable integrations that were developed with the team were tested through multiple iterations through energy models. So here you see throughout the design process where we constantly tested, and even though they're on the interior, it hugely impacts what's going to happen on the exterior with the BIPVs. So it's always important whenever you have a design decision, especially with a high energy usage of that of a lab, to always test your ideas and run that through the team, especially if you have a mandate. So even though we might hit a milestone, again, we want to articulate to the university that we're constantly testing those ideas. And it was critical to communicate this as the University of Toronto has a 20% energy consumption to come from on-site renewable energy. So in perspective, that of a typical lab is about 250 to 300 kilowatts squared meters annually. U of T actually, or the Scarborough Academy of Medicine of Health has marginally hit lower than that of a typical lab, and we've successfully hit our 20% target. So there you have it. We have 4 design principles and where the facade started to support our design ideas. One being to build community through that of Scarborough, welcoming current community members. 2, to welcome the future of community members of coming through with a secondary plan. While bringing in the ravine, celebrating what makes Scarborough campus unique. Working together to provide a well-integrated building form while academia can continue to collaborate to the advancement of medical research. And lastly, to the support of facades, all while soaking in the sun, a building that lessens its strain on the environment by integrating solar capture as that of the facade, a facade that truly supports its design intention. SAM IH will be a shining example at the gateway of the ravine, so it becomes really the future campus that provides opportunities to heal, learn, and bring community together. And that's it.
Thank you, Alison. That was great. Those of you that have done these kinds of models, 20% is a really challenging number to meet. So that didn't just happen, I'm sure. You had to bring the load of that building down through a lot of other sustainability measures to make that 20% work. So it feels like kind of a passé statement, but for those that have done this kind of stuff, Usually we're happy if we get 5% of renewable generation on these buildings. So 20, that's fantastic. I'd like to bring Jeff Kerr up to the stage with Engineered Assemblies for our next presentation. Thanks.
Thank you very much. And here's the clicker. Look at that, it works. Okay. Good afternoon, everybody. Welcome to this presentation on maximizing sustainability through building facades. I'm Jeff Kerr. I'm the Technical Director of Engineered Assemblies. For those of you who are familiar, you know plenty about Engineered Assemblies. For those of you who do not, we are a national organization, 18 years old. We specialize in bringing high-performance facade systems to the Canadian market, ocean to ocean to ocean. We are also creators of the famed Engineered Assemblies Design Guide, which covers details on just about every condition on a building as it pertains to high-performance facades. And we have a vested interest in making sure that facade systems, anybody's facade system, achieves its justifiable lifespan. And that's going to be sort of the root of our conversation today vis-a-vis sustainability in facades. But looking at that, let's say our agenda to achieve a sustainable future through building facades, we have two key challenges that we're going to focus on today, and those key challenges are going to be hurdles in the form of installation and design. So when we look at that, I guess first thing we need to do is realize what do we mean when we say sustainability, because there's probably as many definitions for sustainability as there is for free-range chicken. So with respect to this, meeting our own current needs without compromising future generations to meet theirs, that's what I mean when I say sustainability. And we need sustainability to live in harmony with the environment. Now, the amazing thing about the environment is that environment is a substantial dictator. See the picture, cut that off. But ultimately, climate change challenging our materials like never before. And environment, as much as we talk about environment, is very relevant to facade systems because we need to talk about what systems, materials we're using. And we have a very complex relationship with the environment as it pertains to facades because there's sort of a bite the hand that feeds you thing that goes on where we have to make sure we build and choose materials in a manner that don't hurt the environment, but yet it's the environment which is constantly hammering our facade systems, challenging them like nothing else. So, with respect to that, where do our facades stand on any building? Well, materials, that's a good start. I don't think it's our main focus, though. We've got some great materials out there. We've got things like ceramics, which some people refer to as terracotta. It's more than terracotta. Ceramics are different composition fired at a different temperature. So ceramic systems, we've got high density fiber reinforced cements. We've got phenolic core, high pressure laminates. There is lightweight natural stone, maybe in the form of slate, and we've got porcelain, extruded porcelain perhaps. All these systems, they all have great environmental product declarations, so we can do that easily enough, achieve, I'd say, succeed in the search for some decent materials. What do all these materials have in common? They all work with a high-performance rain screen system. Now, when we talk about rain screen system, and this is a model that Engineered Assemblies has used for years, and being founding members of RENA, it's a model that RENA embraces as well. We're looking at a system where we've got an outboard skin, and we've got that vertical, unobstructed active plenum behind it. Ventilation, ventilation, ventilation. Always good. Behind that, we've got a membrane, which is a weather membrane, and it protects in a lot of respects, it protects things behind that, and the things behind that very commonly are outboard insulation through a thermally broken substructure. So there's not magic going on here, but it is a complex system, and when it's designed properly, it works really well. Do rain screens belong everywhere? Yes. There's never a place where a rain screen doesn't belong, okay? Can all residential, commercial, and recreational spaces benefit from a great rain screen system from a passive thermal integrity standpoint, et cetera? Yes, they can. So, facades, what's the big deal? What's their job? Why am I talking to you about this? Well, I'm gonna go back to that environment thing. Facades are the front lines of the infantry of the building. They get it first, and they need to work. And they need to work for a long time. It's the only it's the only defense for environmental influences. So when we look at this, we're looking at moisture management and passive thermal integrity. It's all wrapped up in that. So are we looking at a facade anymore? Or are we looking at the primary passive environmental control system? That's a mouthful, but that's really what we're looking at when we look up at a high-performance facade system nowadays. So when we take that into consideration, is this the only face of sustainability? I don't think so, because as most of you in this room know, function and form. There's aesthetic considerations. We have to build things that work really well, and work really well means they need to address the relationship between physical space and social consequences. So things have to look good, okay? Sociological implications, sustainability of mental health. So design does matter. In every way it's employed. So we just broaden the definition of sustainability, and facades are the face of the building, and they have a big job to do from a physical standpoint and from a mental standpoint, it seems. And when we look at all this stuff, we have to look at embodied energy, and we could call it carbon footprint. But there's initial and reoccurring, and we have a tendency to focus very much on the initial, and we're going to focus today a little bit on the recurring, because the initial embodied energy is the energy it takes to manufacture a product system, get it on a building. But the recurring embodied energy is the energy it takes to replace, maintain it, dispose of it when, if and when, it fails. And they can fail. So we need to be looking at justifiable lifespan. What do I mean by that when I say justifiable lifespan? Well, durability of buildings. Durability is not an objective reality, okay? It's a function of a material and its relationship to its environment. So how are we designing things in? How are they installed in? But how are we designing things in? A material's installation maintenance is also going to determine the definition of it as a, say, durable system or not. So Ted Keswick, years ago at Facade Tectonics, said to me, underwear or purlins, cotton or steel? They're not great for both. So are we using material in the right way? And are we ensuring that it's installed properly? Application. So sustainability through design and construction. I emphasize this to a great degree as an expert in the industry who's been here for a long time doing this. Installation training. Are the trades who have been named to install the product the people who are actually doing the installation? Are we training the right people? The people named as awarded are often not the ones installing. So we need to make sure that we train those people properly. And part of training them to put together the primary passive environmental control system means they have to have great shop drawings. I mentioned great shop drawings, not good, certainly not bad. I know you've seen a lot of those. But great shop drawings. I speak for probably a lot of people in this room. We can't assemble IKEA furniture properly without instructions. How do we install the primary passive control system without great shop drawings? Because we've got live buildings that are having to do the push and pull. They can't arm wrestle Mother Nature. That never turns out well. So there's a lot of things going on there, a lot of dynamics. So great shop drawings start with, for example, a great system page. So any person in the trade can open up the first page and go, oh, this is how the system goes together. We can go on to elevations and all that stuff and details of particular areas later, but how does the system work? This, obviously hard to read, but a great system page, and this is something that needs to be explained to them, walk them through the shop drawings, make sure they understand them, because it's going to cover things like crossing over traditional points of deflection. This is not information that occurs in the architectural set. It doesn't belong there. It belongs in the shop drawings, which should be great. And it's going to address things like, oh, those vertical hat bars that we talked about in the rain screen system that were going to determine the unobstructive active plenum that was so crucial. Well, those vertical hat bars, they have to stop and start at concrete slab, for example, traditional point of deflection. And if we're going to stop and start them and we have a gap, material cannot cross the gap because those things could move in opposite directions and tear the material apart. So these are little items, okay? When we're looking at a rain screen system, which isn't magic, these are little items which can prevent this from happening and our system failing, okay, which is protecting our building and determining to a large degree, its chances through the pathway of sustainability. So just to recap, we've got suitable materials, a relevant design of high-performance system, we've got good installation, we've got training, shops. Are current industry systems sufficient? Do we need a quality control system for the facade system? Is it important enough? I think facade systems in general, of any supplier done in this country, given the crazy weather and challenges we have environmentally, need to be done properly. So that primary passive environmental control system, that facade just became a lot more important after today's presentation. And we have great standards. We're not alone in this. We've got great standards like CSA S478. It's in the national code. We can draw on it if we want. And it talks about serviceability and serviceable lifespan. What a novel idea. UBC actually employs something like this, and I believe they request 75 years. Is the system that we're designing in and having installed, is it serviceable? I'm not talking about an antiquated version of window wall, which is not serviceable. I'm talking about systems. Is it serviceable, and for how long can we service it until it goes to landfill? So, that was another Ted Keswick gift. So this is an important part. Are we looking at systems that are demountable, that can be serviced and updated, okay? But that quality control process that we looked at for a facade, a pathway to sustainability through compliance, okay? We need transparency, we need due diligence, we need skill. Where would we start with something like that? Well, we could have, a program could have a contract between an architect, GC, installer, and system provider. System provider should be a part of this because they should know the most about this system than anybody. We'll have a software program to manage the conversations and the information and the data. Could be something like Procore. I don't have stock in Procore, just something that we see common through the industry. We're going to have great drafting, shop drawings, maybe by the system provider who knows the most about their system. We're going to have a comprehensive review of drafting with the installer and good training, and we're going to have site inspections, and conveniently, maybe on those shop drawings, we're going to have little icons of cameras on them. And the little cameras would have a number beside them to be a 1 or a 2. And one would say, I want a picture of that detail before the facade skin goes on, and you need to upload it to our software program, and everybody can see it and comment on it. And the number 2 would signify, I need a picture of that detail after the facade skin goes on, because are you closing off my ventilation gap? And we could have things like that. It would be transparency, and we'd all be working together to make sure that this primary passive control system gets done properly to protect the building against the most fierce adversary, the environment, which we're ultimately trying to protect. Specification could occur in section 1, so nobody will miss it. And through all this, we probably stand a chance at having a system where things get designed in properly with good materials that are relevant. Installation happens properly. There's a pathway to compliance of a proper method of installing the system so it has a fighting chance in terms of lifespan, and we'll get the most lifespan out of it. And before we leave lifespan too early, I want to be really clear with all my experience in the industry, warranties are not something to choose, a basis to choose a product on. 99.9% of the time, when I see failures on facade systems, it's because of a misdesign application or an installation error. Often can be an installation error, but could be rooted in design. When you have a problem like that, you have no warranty. No manufacturer is going to stand up for that. They're going to say, wasn't used properly, no warranty. So let's stop choosing products based on warranty and start looking at products and their integrity, and then finding out what is the best way to use these materials and make sure that they're installed properly. So if we do that together, uniting the house of design with the field of construction, something Engineer Assemblies has always been very proud of. We have a holistic relationship between, well, environmental responsibility, design, what have you, all of us working together, we probably stand a chance at creating some fantastic high-performance facade systems that can protect the building and do its due diligence. So my 15 minutes are up. Thank you very much for listening to me speak at you. And I'm Jeff Kerr.
Thank you, Jeff. That was, I don't know if that was passionate enough. Like, I don't know that you care that much about this topic. That was great. Thanks a lot. Fantastic. I just realized this issue of waste on site versus what's in a drawing, like how much material is actually there, and then durability. It's kind of like energy models missing the mark on operational performance. All of our LCAs are assuming perfect quantities, and they're assuming that the buildings and the materials last over that specified time frame. But premature failures, I think we're under-predicting embodied carbon as well. So something to think about. Okay, one more presentation separates you from coffee and snacks, so we're gonna get right to that. Chengde Huang, please, from CSG. Could you come up to the stage?
So good afternoon, everybody. I'm Chengde from China Southern Glass. So today I'll talk about some applications of glass in several projects we have done here in Canada and Vancouver. Yeah, the three sections: project brief and glass makeup and performance, the effect. The first project is the Vancouver House. You could see this project won several awards: the 2021 City BUH Awards, the best tall buildings worldwide, the best tall buildings 100 to 199 meters. The best tall residential of the hotel buildings, or structural engineering award. The second project is the Benton 6, 1090 West, Benton, Vancouver. It's a 31-story office buildings, including 3-story retail podium with the blue gray parking, etc. This third one is this project's form house and the so the glass makeup and performance. For the Vancouver house, we increases this triple glazing with low E coating on the second surface. This is a low air glass with argon filling. The maximum size is 1615 by 2279. So it's still performance 2 ways, but 49. And the U value is 1.1. It's international units, not the English units. English units should be divided by 5.68. The shading coefficient is 0.32. However, this is the GIR values. The GIR values, so we defined in China, GIR value is count for the solar IR, how much solar IR transmit inside. Because solar IR is the energy constantly increase, especially in the summer. Could precisely calculate the energy comes inside constantly increase. That is G values. When we do projects, we always specify G values, or shading coefficient. Actually, it's not precise because G values include the visible light. visible light does not cause heat, much heat. So the GIR value is the precise term to use to describe how much heat comes inside, especially in summer times to calculate the cooling load for the air conditioning systems. So that's the way in China we do that. It's better than the G values. With G value, when the projects probably you always get some misleading. The lower the G values does not mean the lower the temperatures inside. It's depends on how much the GR, the solar heat air comes inside. That's the precise one. The second project is the Bentel 6. The social triple glazing. This one you can see with triple cell low coating on the second surface, and another low coating on the number 4 surface. The double glazing, I think, the double glazing is for the spandrel area, I think. The triple glazing, you could see that TV is 49%, and the U value is about 0.7. 0.7. That means if you English unit, that means about 0.12, I think, because for English unit, you have divided by 5.68. The shading coefficient is 0.27. The GR, you can see the GR is about 0.02. That means very little heat, especially in summer. Especially in summertime, it's little heat comes inside. The glass used for the number 3, the third project, also triple glazing. You can see that we use 3 coatings. The double silver coating on the second surface, and the single silver lowy on the number 4 surface. And on the interior surface is the coating we call BW88. Is that to lower the U values. The U values is 0.7, similar to the project, the previous project. Because in the previous projects on the second surface, the triple silver lowy. This one's the double silver lowy. We use 3 coatings to get the U values about 0.7. Just here for the color coordinates for the Vancouver house. You can see that the reflective color, the A coordinates about minus 1.79, and the B coordinates about 0.89. That means the reflective color is quite neutral, actually. Slightly blue, the reflective color. The transmitting color is quite neutral, actually. You see the CRI values. CRI values is 95.39. That means we see through inside from the outside, see the trees, see the flowers, it's very natural colors. The higher the CRI index, the better the view, the side views. This is the effects of the project. On the left side, the glass samples. On the bottom one is the reflect color, slightly blue colors on the clear sky. And the bottom one, top one, it's transmitting color from inside out. We just put the glass on, against the tree or see through the glass. You can see that the colors are very natural. For the second project, you can see T means the transmitted colors. You could see the transmitted colors, the A coordinates is about -5, and the B coordinate is about 1.45 something. These transmitted colors are slightly, or actually slightly yellowish colors, actually transmitted colors. But for the reflected color, you could see the coordinates, A coordinates about -4.5, and B coordinates about 4.6 actually. It's slightly, very slight blue-green color tone actually. You see the CRI is around 90%. It's still good, but it's not as good as the previous one. The previous one, the CRI is about 95%. It's very good. This is the glass sample. The left bottom is the glass sample. On the clear sky, the reflect colors is slightly blue-green, actually. The transmitting color, you could see that you see the trees, against the glass, you could see it's very, very natural color. On the right-hand side is the some pictures of projects. You could see the glass very clear, actually, clear look. For the solar projects, could see the transmitting colors, actually A coordinates around -6, and the B coordinates about 3.22. This means the transmitting color is still a very slight yellow-green tone, actually. The reflected color is A coordinates about -3.7, the B coordinates -7.7. That's those very slightly blue colors. The CRI is 92.7. It's very good. You could see the glass samples on the clear sky, the reflected colors. And the top one is the transmitting colors, just press glass against the tree to see the natural colors. On the right-hand side is the pictures of the projects. So actually, that's all I want to say today. Just to show you, some we have done some several projects in Vancouver under the glass and the samples of performers with different makeups, different colors. Yeah. Thank you.
Thank you very much. Can I ask all the presenters back up on the stage? And folks, you can help yourself to some refreshments. We're going to go for about 15, 20 minutes. And then we've got one final session and a reception at the end of the event. So if you're able to, please do stick around. Thanks. Okay, folks, welcome back. One more session, or I guess one block of sessions. We're almost there. Hopefully everybody enjoyed the chips and the cookies. So we're going to get right into it. And I'd like to invite up to the stage Charles Marshall from DIALOG and Amy Montgomery from RDH. And they're going to talk to you about deep energy retrofits. Take it away, folks.
Great. Thanks, Luka. All right. Welcome back, everybody. It is our mission to make the next 20 minutes informative and exciting and bring the energy to this session after the snack break, so here we are. Thank you very much for the opportunity to be here today on behalf of DIALOG and RDH Building Science. My name is Charles Marshall. I'm an engineer and partner with DIALOG in our Toronto studio. I have the pleasure of co-leading our sustainability and building performance practice. and have had the great privilege to work on this project, 25 St. Clair Avenue East. So happy to talk to you today about how this project is a great example of a deep energy retrofit. And then Amy and I will tell you some war stories from the front line of what happens when you do one of these projects and what we learned along the way. So just a little bit of agenda. This 20-minute presentation fits into 3 parts. We'll do a project intro and give you the background info. We'll talk a little bit about the enclosure of this building, the before and the after, and the solutions, how we got there. And then Amy will take us on a deep dive into some of the stories learned and the resulting performance. So, from a project intro standpoint, I want to share with you some key building stats and why we're so happy to talk about this project. We think deep energy, deep carbon, deep green retrofits, whatever you call them, are a really critical part of Canada meeting its climate change targets, particularly if we want to do so while making cities healthier, happier, and more inclusive. And that's why we're so excited to talk about this project and ones like it. So, every great story needs a starting point. This is the existing building as it was. These photos are probably from about 2017. And you can see at the bottom here some sort of key stats. This was originally 2 buildings, one built in 1954, one built in 1959. So both well past their original service life for most systems, but good bones, great location, and great candidate for a comprehensive recapitalization and major building retrofit. It's a fairly large office building, 10 stories above grade plus 2 below grade parking levels, and about 440,000 square foot of area. All the occupiable area in this building is office use. And like we said, we're really bullish on deep retrofits. Not every existing building should be a deep retrofit candidate, but certainly, like any real estate story, it's about location, location, location. So to have this great building situated at Yonge and St. Clair in a rapidly developing neighborhood, exceptionally connected to transit, connected to nature, connected to opportunities for active transportation, makes it a great candidate for a second life. And here you can see, actually this is cool, this photo is about a week and a half old. This project was completed in September 2023, so very much going through its process of opening. On the right hand, you can see the predicted performance. We're just initiating now a comprehensive measurement and verification program for this project. It's going to be really important to track and verify some of these KPIs for energy and carbon performance. But you can see here the predicted performance. And this was very much envisioned by our client, the Government of Canada and Public Services and Procurement Canada, PSPC, to be a flagship project, a demonstration of sustainability, innovation, and decarbonization. And the numbers on the right are not normal. Usually we design a high-performing office building. We try to be below 100 kilowatt hour per square meter as a benchmarked energy use. This building is targeting to be in the 60s. So very much demonstrating what's possible when it comes to a deep retrofit, in the hope that others will see that as a demonstration of viability and follow along. And we truly believe the climate and the planet need that. You can see the predicted energy savings here. So in the neighborhood of 70% energy savings versus the pre-retrofit building and 80% GHG savings. So really trying to aim for that deep, deep reduction. We won't go deep into certifications and things like that today, but this is a zero carbon design certified building with the CAGBC. It was part of their initial pilot program for CAGBC's zero carbon program. It's a building certified candidate project that's on the way, and we're on the cusp of getting LEED Gold, hopefully even LEED Platinum certification. So definitely a balanced and holistic approach to sustainability, while we'll focus mostly on thermal and carbon today. We'll sort of go quickly through this in the interest of time, but it takes a lot of strategies to create a comprehensive deep retrofit project, inclusive of enclosure and other systems. So you can see here renewable energy generation on site, strategies for saving and reusing water, that high performance building enclosure, really important to reduce heating and cooling loads and make a low carbon design viable while enhancing thermal comfort. We'll obviously get more in depth into that today. And then sort of at the bottom here, you can't see it, but below this building is a geo-exchange heating and cooling system with about 50 borehole geo wells underneath the building. So that's really the star of the show and helps enable that exceptionally efficient and low carbon performance. And just quickly to touch on this, we really advocate for that load shedding approach to low carbon. Begin by really understanding the building and the internal gains within it, reducing heating and cooling needs while enhancing comfort through that high performance building envelope, further reducing loads and improving efficiency through heat recovery and other energy recycling systems, and then finally embracing that heat pump based all electric energy plant for low carbon heating and cooling. A little bit through the numbers, and won't go too in depth into today, but you can see sort of that pre to post retrofit and performance, and enclosure is a huge, important, necessary part of this, and obviously there's other contributors as well, but you can see that the blue bar graph here is the pre-retrofit, the green bar graph is the post-retrofit, and you can see almost complete reduction in heating design through the employment of heat recovery, significant reduction in space cooling and lighting. Almost all natural gas becomes electric consumption. In Ontario, we have reasonably low carbon grid, so electrification is very much the path to low carbon. And then on the left-hand side here, you can see, so this is ultimately going to be a TGS, Toronto Green Standard Tier 2 verified project. We're in the process for that under an older version of TGS. So we're not on TGS version 4. But if we were, this building would be performing to the highest tiers. So again, really striving for that flagship performance and showing that we can make an existing building perform better than a new building. Increasingly, the conversation is shifting from operating carbon to embodied carbon, and it really should. We've got a long way to go here, a lot to learn together as an industry. On this project, part of the reasons why we're so in favor of deep green retrofit projects is saving all that carbon in the existing structure, locking up that carbon, extending it for another 30, 40, 60 years. One of the things we didn't go in great depth into, but you can sort of see in this picture, is one of those existing 60-year-old buildings we're reusing was a predominantly steel structure. The other one is a predominantly concrete structure, so a little bit of structural gymnastics there involved with preserving that for another 60 years. These projects are not for the faint of heart, lots of technical complexity there, but the prize is really worth it. So structure in this building represents about 75% of the embodied carbon, so all of that is reused original structure. And you can see here that we calculate about 7,800 tons of CO2 equivalent saved in embodied carbon by reusing all that concrete and all that steel. So this is very much a strategy we think we need to embrace in mass in order to enhance our cities and meet our climate goals. And then just a quick note here, increasingly the conversation shifts to whole life carbon. How do we avoid distinguishing between embodied carbon, operating carbon? It's all just carbon. We obviously want to save the most that we can, obviously within the boundaries of capital budgets, project budgets, schedules, et cetera. So we really are increasingly trying to think about our projects through a whole carbon lens and optimizing for all those factors at the same time. So what about the enclosure? I'll give you sort of the high-level version, and I'll pass to Amy, our expert, to dig into the real complicated stuff. But here's the high level. So as you can see, the existing buildings, the height of aesthetic taste here, obviously, and thermally, about what you would expect from a building that was constructed in the 50s and probably had sort of minimal capital investment since that time. So a double-glazed, air-filled curtain wall system on the left with no argon, krypton fill, no thermal breaks, no coatings, relatively low performance compared to modern systems. Spandrel with backpan insulation, almost uninsulated masonry walls performing at about an R3, so lots of room for improvement. Our approach was really, as always, to take a look at the microclimate, take a look at the resources available, take advantage of sun, provide exceptional daylight while providing transparency and also excellent thermal performance. And you can see here the result. The glazing ratio is relatively low. 23% is pretty low for an office building, but does help with thermal performance. 200 millimeter semi-rigid insulation for walls and about an R28 effective performance. Triple glazed IGUs and thermally broken curtain wall. And then obviously striving for the highest levels of air tightness as demonstrated through, calculated through design and then demonstrated through measurements on site. So with that, I'll pass to you, Amy, to take us through the details.
Thanks, sounds good. So with that kind of overall project context set, I just wanted to completely shift gears here. And we're going to do a little bit of a deep dive, or as much of a deep dive as we can do in the next 9 minutes, into some of the more grittier lessons learned, maybe some of the challenges and things that tripped us up along the way. We thought today we'd be in a room full of people that have lots of experience and knowledge, so we could kind of treat it as a safe space, pull back that curtain, and go into some of those nitty-gritty details. So as Charles mentioned, we already are starting with a really high performance exterior wall. We're kind of in that territory of R27, R28. And we know that if we put that exact same amount of insulation into a spandrel backpan, we're definitely not getting that same level of performance out. And that's why people like me are always telling architects to, scrap the spandrel and go with a quote-unquote real wall, an exterior insulated framed wall. And that's the approach that we took for the 25 St. Clair building. So even though you're standing there on St. Clair, you're looking up at that north facade, it reads the whole thing like it's curtain wall. But in fact, there's just that kind of diagonal strip near the feature stair that's truly curtain wall, and the rest of the facade is actually an exterior insulated framed wall with punched windows in it. And from a thermal performance standpoint on the surface of it, that sounds really great to someone like me, but I think that's an assumption that I want to just dig into a little bit. So this is a section of the exterior wall. We've got our exterior sheathing, membrane, stainless steel cladding attachment clips, little free promotion here for the EJOP folks in the room. Exterior insulation built up in a couple layers to get that 8 inches. We've got that subgirt system, then a membrane to kind of conceal the insulation at the open joints of the cladding, and then of course this lovely terracotta cladding on the exterior. So I think we're doing the best that we possibly can do really in the exterior field of the wall, but the trick comes to the interface with those punched windows. So the windows are pushed out of the plane of the exterior wall, and part of that is really achieving that curtain wall-esque look where we have the glass of the windows in line with the adjacent cladding, and that's causing us to kind of push those windows out, 10, 12 inches from the exterior sheathing plane. And that in itself requires some structural support. So now we've got some structural steel at the head and the steel of the windows to take the load. And these are large dimension triple pane windows, so the load from those is not trivial. So we've got that exterior insulation in the wall that's butting right up against our window frames. But as you can see, we're not getting as much insulation coverage at that shoulder of the frame as we would like. So in trying to meet this design intent of that curtain wall look, we are ending up with a bit of a thermal bridge at this condition here. So, we think we've done a good thing by swapping out our spandrel and having insulated exterior wall, but the question is, once we add in the structural steel, once we add in all the thermal linear transmittances, the psi values at the window perimeter, do we end up that much further ahead? And the answer is a little bit surprising, at least for me. We end up, that R28 wall comes down to something closer to R10. So it's not actually that different than what we'd expect from, say, maybe an equivalent kind of, full height level of spandrel. But I have to say I'm kind of cheating a little bit here. I've purposely kind of cherry-picked the one part of the facade that has the highest glazing ratio. Obviously for the St. Clair project, we had 2 full facades that had no windows in them at all. So our overall R value was much, much higher than this R10 that I'm showing here. But I just wanted to make that point that, for certain configurations, geometries, window to wall ratio, it's not necessarily that slam dunk that, we might think it is to swap out the spandrel for exterior wall. And we shouldn't really, we should really be paying attention to that in our thermal bridging calculations and making sure that if we are doing this approach, we are making sure we're doing as much as we can to mitigate those thermal bridges. It's kind of one of those necessary things. We can limit thermal bridging as much as possible, but probably not eliminate it. So really it's coming down to being diligent, crunching those numbers, and then often it's just a choice of kind of the lesser of 2 evils. So thermal bridging, another way of dealing with that obviously is by using thermal breaks, which is what we've got at the post bases of that structural support system for the rooftop PV. And as everyone in this room will know, the sort of most effective way of using that thermal bridge is to make sure it's aligned with the insulation as much as possible. Well, for reasons that we don't really have time to get into, but kind of related to construction sequencing, et cetera, we ended up with that insulation sleeve at the post base being a little bit shorter and not connecting up to that thermal break. So we've got a gap of structural steel that's exposed to the exterior. Not ideal, really, thermally. But that's just one of the things that we have to deal with. That's a reality. We're all dealing with this on projects. There's changes that are happening in tendering and construction that are modifying that original design intent. It's our job to kind of take that in stride, evaluate it, and help teams decide, what's the trade-off between cost, constructability, and performance. And in this case, it turns out that that revised detail doesn't have a drastic effect on the thermal performance. Certainly, it's much better than having no thermal break at all. And if we take that kind of R50 insulation in the roof, and it turns out that this revised detail gives us maybe about R35 instead of R36. So, it's not a drastic change here. And I mention this example because as someone that advocates for high performance buildings, I never want to accept, a drop in thermal performance if I can help it. But in this case, the math doesn't really bear out a really strong case for, rejecting that revised detail. So, even on high performance buildings, we do have to compromise sometimes, compromise strategically. So I've just got a couple of minutes left here to talk about air tightness testing and some of the challenges with that. And a lot of that comes down to our very tight, downtown Toronto site. So it's really compact. Obviously, one of the toughest things about the site is the TTC streetcar loop that comes right around the building. And that's obviously impacting access for all of our enclosure facade installation. So we've got different phases of scaffolding, swing stages, all of our curtain wall, our punched windows, sheathing, membrane. It's kind of all going in at different times, at different phases on different elevations. And I know that there's like 3 or 4 RDH guides out there that talk about air tightness testing, and they say, do that mid-construction test when your air barrier is complete but not yet concealed by interior or exterior finishes. But, on this project, our north elevation was still putting windows in while the south elevation was completed, 3 months ago, all the way out to the cladding. So, it's just not gonna happen. We don't have that perfect point to do air tightness testing on a full building scale. So we ended up revising it to a guarded test where we just interrogated those top 2 floors to allow us to do a little bit of diagnostic testing and the opportunity to maybe do remediation work if needed before the construction finished. As we all know, doing air tightness testing requires quite a lot of prep. Obviously, we're sealing off those big penetrations for HVAC through the enclosure. But when it comes to guarded testing, particularly in a building like this where not all of those interior components are always finished, there's a ton more prep work, 5, 10 times more prep work that has to be done because we're talking about sealing off elevator shafts, interconnecting floors where we have stairwells between floors, those bays where the material hoists are coming up, et cetera, et cetera, et cetera. So it ended up being a bit of a nightmare, and to be perfectly honest, while we're doing our testing, we probably spent 60% of the time and effort on just troubleshooting all of that temporary sealing, and only 40% on actually looking at the exterior wall air leakage. So, in retrospect, we probably could have just kind of scrapped the quantitative part of this test and just done a lot more qualitative testing. But in the end, all's well that ends well. We ended up getting the guarded test done, and then just earlier last year, we completed the final whole building test and confirmed that 1.5 liters per second per meter squared at 75 pascals that Charles noted earlier was the target. So just with my last slide here, I wanted to note an article that my colleague Dave Stanton wrote in the latest issue of OBEC's Pushing the Envelope magazine, which you can just get free online. And he's making the same point that I've just made. There's this assumption that doing guarded testing is somehow easier, cheaper, more straightforward than doing a whole building test. But it might be true in some cases, but in many cases, particularly for existing buildings, it's actually a lot more work. And the second point that he makes that I'd like to point out is the fact that you really need to have a testing agency that knows what they're doing when doing particularly guarded testing. We've seen a couple of reports recently published where folks have done guarded tests and they haven't adequately controlled for the air leakage between the guard floor and the test floor adjacent. And that can lead to some pretty big errors in terms of the actual air leakage versus the air leakage that the software is measuring in the door fans. And so, depending on the condition, that error could be, upwards of 100, 120%. So pretty significant. So the point to make is just that if you're going to go through all of that effort to do the guarded test and all the preparation, just make sure that the practitioners are going to make sure you get a result that's actually valid. With that, I'll just quickly acknowledge the project team for the successful retrofit project that we ended up having. Thanks.
Thank you.
That was fantastic. I think it just goes to show that we make so many decisions during schematic and early design phases, and we make all kinds of assumptions. And without going downstream to look at how the details are actually performing, you're just not, you're off track. Those models are just over-predicting performance. So that was fantastic. The thing that was weird, the R3 masonry wall, my rule of thumb for conventional like condo window wall is R4. So it's really great to see how far we've come along in 70 years.
4 decades.
Yeah. Thank you, that was fantastic. Next up, Peter Dushenski from GlasCurtain. Come on up, Peter.
Thank you. All right. We are still here. Fantastic. Yeah, we're doing it. The cold hard facts: achieving beauty, durability, and daylight north of 60. My name's Peter Dushenski. Get this out of my way. I'm the managing director of GlasCurtain. We are a Canadian manufacturer of fiberglass framed curtain walls for primarily triple glazed applications. And it's great here to be up on the stage with such a really illustrious group of speakers. And Zak is this global event, and it really feels like we're part of something bigger when we're here. There's one in Shanghai one week, and there's one in Berlin the next week, and they're all over the world. But at the end of the day, architecture is a very regional practice. Architecture depends very much on the geography of where we are when we're designing our buildings. And when we're designing in Canada, we confront a unique and uniquely challenging set of circumstances, not least of which is our famously cold weather. And maybe Craig Applegath will, say, well, it's not going to be like that forever. We're a couple more degrees, and I tell you, out there, here in Toronto, the last couple of days, it definitely feels like summer. Coming from Edmonton, where it's about 5 degrees and raining, it is definitely a lot more temperate here. But suffice to say that Canada is globally known and recognized as a pretty chilly place. We're known for a few things, I would say. Maple syrup, Justin Bieber, and our icy, icy cold winters. But this climatic reality doesn't seem to stop our world-class architects, from many of whom are in the room today, from designing some of the most beautiful and striking contemporary buildings in architecture today. And possibly even because of these constraints, we see such incredible architecture. After all, is necessity not the mother of invention? So today we're going to talk a little bit about exactly this, which is invention. And yes, of course, its trusty sidekick, innovation. To do so, we're going to highlight one particular project, a special one in particular, the Nunata campus at Nunavut Arctic College, designed by Teeple Architects from Toronto and Sibonell Architects from Winnipeg. Do we actually have anyone from any of those firms here today? Hey, fantastic, fantastic. A few hands. Wonderful. So we're speaking to the converted. So this is completed in 2019, actually, but this was in the pre-times, if you will, pre-pandemic. And this project today maybe isn't the latest, greatest that we have, but is architecture really about jumping from the latest fashion, from one thing to the next? We certainly would hope not. For most of us in this room, architecture is about standing the test of time. And I feel like some of this will also be, reiterating what Jeff from Engineered Assemblies was talking about with such incredible enthusiasm. So it's great that he's been able to pave the way. But architecture is definitely about standing the test of time. It's about durability and the test of the elements. And really, what better example than working in Nunavut? So in speaking about this project today, we'll delve into the critical importance of integrating beauty, durability, and daylight into this building, but really into all buildings. So now you might be asking, and no, you're probably not actually asking this because I know everyone in this room is well versed in this, but why do beauty, durability, and daylight even matter? Aren't there more important fish to fry, you know, in architecture today, especially in the face of increasing environmental concerns? You know, can't we just ditch all this fluffy, feely stuff about daylight and, you know, nice buildings? Aren't there bigger fish to fry about reducing, you know, embodied carbon, reducing operational carbon? And certainly there is. Certainly we have to do a better job of having more durable buildings that amortize that embodied environmental impact. Because that, when we build our buildings, that material is coming from somewhere. You know, a stork does not deliver the building materials to our buildings and, you know, drop them off and assemble them. These all come from somewhere. And so we need to do, you know, especially during these periods of historical transition, which you are clearly in the midst of, when the pendulum feels like it's swinging from one way to the next, we need to be mindful that this pendulum doesn't swing too far to the other way, and too far, in this case, away from beauty and daylight. Indeed, to deprive ourselves of beauty and daylight is, and natural views, is to deprive ourselves of our physical and emotional well-being. As mountains of research will certainly attest to, and the whole field of neuroarchitecture and neurobiology certainly supports this, and also our ability to learn and to be productive, which is so much of what we're doing in our interior spaces. And of course, there are mountains of research to support this as well. And then there's the all-important connection to land, and to our land. And this is a funny one because you know, we like to think, certainly in you know, some of our remote areas, that, you know, the connection to land is an important part of, you know, indigeneity and our First Nations peoples and the Inuit peoples. Their connection to their land is something that they're looking to maintain when we're building buildings in these remote areas. But ultimately, it's true for all of us. We're all part of the land. We're all part of nature. And there was even a funny anecdote of, you know, talking to one of the speaker, or sort of the conference organizers here today, and she was saying, yeah, you know, my Uber driver was driving me, you know, to this conference center, and he didn't know which way north was. Right? We were so disconnected from our land, by and large. Part of that is, you know, living in shadows all the time, living in these concrete jungles. Part of it is our orientation of our windows and our glazed facades to our buildings. And especially when Canada, you know, Canada is one of the most naturally, you know, yes, Canada is known for being cold. It's also known for being one of the most naturally beautiful places in the world. We should do well to embrace this, you know, what you might even call a God-given abundance, right? And this is very much true in Nunavut, as well as the rest of the country. And you can see here where this particular project was located. Well, I guess I have a little pointer thing, don't I? Let's try that. They seem to be a bit funny, but let's try this pointer. Pointer, there, yes. So we are here-ish, is that right? Yes, and Nunavut is about 3.5 hours by plane northeast of here. So if you think this is, you know, 1,000 kilometers on an island, on Baffin Island, and it's a beautiful place, but it is very remote and a very challenging climate to work in. And so you might be nodding, yes, Peter, we should be building our buildings to embrace the best of Canada. But how are we actually supposed to do that in this day and age, and particularly in this place? Okay, so we might not be designing 100% glazed buildings in this climate. We're not doing, you know, the Renzo piano courthouses. As beautiful as those are not suited to every climate. And so what we have here are a few examples on, you know, with the 10% here. That's sort of conventional architecture in this climate. And in many ways, that's actually also what energy codes are, you know, in the prescriptive sense at least, aiming to achieve, is a much more constrained window-to-wall ratio. Of course here, whose cursor is that? Of course here in this climate, these are, you know, this is a function of necessity. This is not a nice to have, this is a need to have. But with, you know, with our fiberglass frame systems, we were able to triple the conventional window-to-wall ratio from 10% to 30%. And this is what's possible when we use high-performance building facade components, such as our fiberglass frame systems. And this is, again, at 63 degrees north latitude. So it's no small task to achieve this balance between thermal performance and comfort and durability and sustainability. And so it requires imagination, creativity, and yes, ultimately innovation. So it is that architects who specialize in cold climate architecture, as well as those also, specializing in net zero, passive house, LEED platinum buildings, especially in colder climates, are constantly pushing those of us in the glazed facades manufacturing industry to improve our thermal performance of our facades, of our products, so that we can deliver the desirable window-to-wall ratios that, again, engage with the environment and open up the connection to the land and allow daylight to flood in and improve our well-being. And so all of this is a huge challenge in most parts of Canada, but who said we're going to get a little challenge get in our way? So we're not going to get too much into the details, but just at a very high level. So how did we manage to do this, to get a 30% window-to-wall ratio at Nunata campus? Well, with a little technology made by Canadians for Canadians, right? Who would have figured that Canadians would be really good at making stuff that works in a cold climate? Funny how that works. And I know there are going to be, some other conversations about overseas procurement, and there's absolutely a time and a place for that. But the colder the climate, I assure you, the better we are. It's like a Canada Goose jacket. Who do you want to buy your Canada Goose jacket from? Well, mostly Canadians. But you can see here some of the systems that we are applying. So we have a fiberglass frame here. We have a conventional triple glazing here as well. We also have a fiberglass frame with these T anchors, and these are made by a company called Solera. Advanced Glazing is also a Canadian company as well, and these are aerogel-filled daylight units. So these are the ones that you can see with the translucent effect interlaced between the transparent facade there in the upper left-hand corner. And so with these units, the standard triple glaze units are going to be with a fiberglass frame about R7 overall thermal performance. So it's really quite good compared to a conventional system. With the aerogel units, we're over R10 combined frame and glass. So this is what's possible, and arguably, potentially even what's necessary for the future in terms of balancing beauty, durability, and daylight, especially for public buildings in Canada. And beauty and daylight we've touched on enough, but durability. Why might durability be necessary? Well, I know Jeff was talking a little bit about this, and Craig was talking a little bit about this as well. And we should probably ask ourselves, in addition to the future of climate uncertainty, 30 years ago, everyone thought that the world was going to get a lot colder. Today, it seems like the world is actually going to be getting a lot warmer. So there's uncertainty there. But there's also uncertainty in other things, like skilled trades for maintenance. I haven't heard a lot of, maybe someone's touched on this. We've certainly talked about, had conversations about skilled trades for installation, absolutely critical. And then there's maintenance as well. These buildings require maintenance and repair. They are not static objects. They are built, they start degrading on day one, right? They're kind of as perfect as they will ever be when they're built, and they do not stay like that for very long, unfortunately, especially in a climate where you have, probably plus 20 degrees in the summer and minus 60 in the winter. So you have an 80-degree swing, and that's a lot of freeze-thaw cycles. Calgary kind of gets it the worst with the, Chinooks and these kinds of things, but a lot of buildings in Canada are under this kind of stress where they're seeing big swings. And maybe not all of them in downtown Toronto particularly, but certainly by the time you're in Ottawa, you're seeing a lot of these kinds of swings. And so, the future of skilled trades is also a question that I think many architects are starting to ask in terms of durability. And Nunata campus didn't have the luxury of asking about this question as if it were some far in the future concern. Due to its remote location, again, maybe I didn't mention this. So yes, it's a 3.5-hour flight, but the only way to get materials there are actually by sea lift. And that sea lift, that window is actually only open 2 months a year. So the other 10 months a year, you got what you got. So the future of durability, and that is sustainability. Sustainability and durability are inextricably intertwined. So it's not just the thermal performance, R7's great, thermal bridging, fiberglass frame, is a much better insulator than conventional aluminum framing, to be sure, but it's also, the differentials of expansion contraction between these materials as well. So the glass is quite thermally stable, and fiberglass, being more than half glass, is also a very thermally stable material, and they're moving together. The gaskets that they're holding in place, which is where, these gaskets, you can sort of see these gaskets over time will start to get stressed, and will, that will lead to air leakages, condensation risk, and more. So here, fiberglass excels. It expands at half the rate of aluminum, and at almost identical rate of the glass. But I see I have less than a minute left, so I will jump ahead here. I think a slide to yes. So we stand here at the beginning of a new era of architectural design, leveraging innovative materials by Canadians for Canadians in our vast and beautiful country from coast to coast to coast. It's essential to recognize that this is a journey that we embark on not alone, but together. And advancements that we see today in glazing technologies and building materials are the fruits of collaborative efforts between manufacturers, architects, engineers, and building scientists. And each group brings something important to the table to provide beauty, durability, and daylight into all the buildings we inhabit, no matter how demanding the application, whether that's LEED, passive house, or cold climate buildings. There's more potential to do better together. So with that, we'll say thank you very much.
Thank you very much, Peter. That was really inspiring. Okay, you've stuck with us for this long. Stick around for one more session. Last but certainly not least, we've got the second of our two panels today. And Peter gave away the script, but it is on overseas procurement. So I'd like to invite up to the stage as the chairs get set up, Moran Olsha from WZMH, who will introduce the rest of the panel. Come on up, folks. And remember, when this wraps up, we've got a reception next door. So if you can, absolutely stick around for that. Thanks.
Yeah, okay, great. So we're going to be talking about overseas procurement for facades, some of the challenges that we see in different projects, some of the advantage and disadvantage of doing it. And I have a great panel with me today. The first one is Dustin Tran. Sits right beside me. He's the managing director for BM Windows from
Vietnam.
And he will be talking and representing basically the manufacturers from overseas that we procure the products from. The second person with us is Andrea Rinaldi, sits over there. Andrea is the VP Business Development and Procurement at Multiplex. And his recent project in Toronto is one, Delisle, which I worked with the Multiplex on, and it's a great project. We'll talk about that a little bit later. Also with us is Todd Holland, founder of TRH-CW Services, Inc. It's a new company. However, he's been around for a while, 28 years of experience in procurement of local and overseas curtain walls, as well as basically helping projects from beginning to end. Last but not least is Jerry Lang. Jerry is a senior associate and facade leader at Architects Alliance, and he's a graduate of U of T, University of Pennsylvania, and currently is a student, Doctor of Design at the University of Calgary. We're going to start, you can see on the images here, we're going to start with Gary. The first question, when we started talking about the whole issue, the whole discussion about overseas procurement, was why do we even select products from overseas? We just talked about the carbon footprint of different products, the challenges of overseas procurement that comes with delays, QA/QC, et cetera. So why do we even do that?
Thank you. We didn't start out procuring the very large pieces of glass you see for this. This is a large house. The living room window areas, for instance, are glass panes that are triple glazed. They are 3 by 8 meters in length. They weigh 7,000 pounds. I'm crossing unit measures here. And the goal was just this very simple, pure idea of only 3 or 4 materials that are exposed. Stone glazing, some black metal, and that's mostly it. And what the simple qualities of the simple expression are an extremely complex section that you see here, trying to make everything as flush and monoplanar as it can be. The floor, you have to do extraordinary things to get the floor flush with the grating, with the steel bit of structure to hold these 5,000 and 7,000 pound windows. And we were initially, we had the glazing engineered by our friends Eckersley O'Callaghan, as well as a firm in Montreal. And we had set up and started the process by working with the people in a very large manufacturing or IGU plant in Collingwood, which is only about 50 kilometers from where this house is. The big problem was that by the time it got to the point of really putting money to the objects, it was about $500,000 cheaper to bring the glass from Spain. This is something that I think could be discussed a little bit, but and if you're thinking that this is like the worst energy criminal project that you've seen today, we did an energy model not too recently, and the most energy consumptive part of this house is the lighting. So I think that would be something to start a discussion with, is that.
Absolutely, and I think that the first question was, why is it so expensive when we have production happening 50 kilometers away, and it's still cheaper to go to Spain? Todd, would you like to talk about that a little bit?
Sure, and with respect to that manufacturer, they're also very good. But the realities in today's market is there's a lot of companies out there that can make glass like this, especially from Europe, China, different places, and they have very large operations. And some of them use state-of-the-art equipment that has very high production rates and does very large volume. So when you start looking at it in a comparative format, it's hard for a company that's a little bit smaller to compete, because when another company is making 10 times more from the same equipment, working shifts, maybe using higher production equipment, it makes it hard to compete. But unfortunately, in a level playing field, that's what happens.
Right, and when we talked about that before, and one of the things we always talk about is the economy of scale. And if there was enough reason or enough demand to produce something as unique as this, then maybe those smaller companies around here would be able to compete on the price and be able to deliver. But I think, Andrea, you had an opinion about that.
Yeah, so I mean, I agree with Todd. I think we're still seeing in the current environment, cost remains a key factor for a lot of owners in a go, no-go project environment. And with a bit of a hangover from the interest rate hikes that happened a few years ago and construction costs generally being high, even if you're specifying local materials and trying to promote a buy local strategy, when it comes to a construction manager or contractor, to look at budgeting and finding efficiencies and cost savings, we'll call value engineering. If we're talking to our supply chain, overseas options will quickly come on the table. So I'm not sure if it's enough to just start trying to specify local products necessarily. And we've talked about, do you subsidize the industry? I know there are some tariffs that are imposed on some unitized systems that come from overseas. Do you look at that as an option to help grow the local industry? Now, obviously, those are very controversial, policy-driven options, but I guess the main point is until pro formas are more viable, I think cost will remain a key driver. And if, as Todd mentioned, things are cheaper to come from overseas, I think we'll just continue to see that as the option in order to get projects off the ground.
Yeah, and that's one of the challenges that we all see consistently. So, Dustin, you are a supplier from overseas, and we do want to hear a little bit from you. How did you enter the Canadian market? What, you know, we're just talking about potentially tariffs and other roadblocks that potentially are being put in this market, but you managed to get in. So tell us about that.
Yeah, go straight to the question. To be frank, break into the Canadian market isn't just look. Beside the price solution, it's the result of meticulous planning and the technical, the solid technical foundation we built over the years. From the beginning, we have concentrated to develop our system, facilities and personnel to be prepared for the international demand.
So I wanted to...
Not only that.
Yeah, let me just... I'm trying to get back to the video, because you shared with us a video about your facility. See if I can manage. Yeah, so let's talk about that a little bit. So that's the facility in Vietnam?
Yeah. Not only that, Beam Window is a part of Vietnam's largest construction group with nearly 30 years experience in construction industry. And Beam Window is leader in facade industry in Vietnam across Asia. We have been completed over 550 projects, both domestically and internationally. As BM Window, we always try to enhance our quality control to meet the international standards.
So we'll talk about that a little bit afterwards. I just wanted to let that video complete. This is the facility that shared with us. This is your team that brings a lot of value to the table. And then this is another cool video, I thought, that shows the system. So just going further to some of the challenges that we see with overseas procurement, and we talked a little bit about time and quality consideration. So we know time is money, and when we have to wait for a delivery, when it needs to come from overseas, and sometimes there are challenges with that, which we'll talk about. But first, before we start, I just wanted to hear from you, Andrea, about the design assist and early deliveries that helps us to overcome some of these challenges.
Yeah, so what you're seeing up on the screen here is our One Delisle project. That's at just north of Yonge and St. Clair on Delisle Avenue. So that facade was done by way of a design assist. So we had glass, operable vents, and sliding doors, all coming from 2 different suppliers in Ireland, as well as metal panels from Spain. So as Moran mentioned, we had a design assist agreement in place with a local tier 1 trade, and their supply chain was based over in Europe, like I mentioned. And so from a CM's perspective on this project, what we really liked about Design Assist was, in addition to the general benefits of greater collaboration and earlier planning, I think we're seeing that with Design Assist more and more, but in particular with overseas procurement, it allowed us to understand our subcontractors' supply chain a lot better and a lot earlier on when it comes to capacity and production, as well as long lead time items and risks with overseas shipping, we were able to get a better handle on that. And contrast that with, the typical bid build where maybe we're only interfacing with the sub and their supply chain remains, their issue, and we're not at the table with their supply chain able to understand what are some of the constraints or quality issues or challenges they may be facing, that we can maybe face them together as a team with the architects, with our construction management team as well. So that was really helpful on One Delisle, obviously a very unique facade. Some of the challenges that come with that kind of greater visibility in your supply chains, in their supply chain, especially when you talk about overseas sourcing, is some of the commercial risk that comes along with that. So, on this project, only 12 to 14% of the contract value was for installation. The majority of it is materials. And so when you're dealing with these suppliers overseas who are manufacturing and shipping locally to be fabricated locally, they want payment. And so when you're making payment for materials that are being manufactured overseas, those goods are still overseas. And so, what happens if the storage facility burns down or something happens? So you've paid for those materials, they haven't arrived in Canada yet, and the chain of ownership, I guess, or title to those materials, how do you control that or at least manage that risk? So we spent a lot of time at One Delisle with those suppliers, putting in place agreements and offsite storage arrangements and understanding, the circumstances under which the materials would be stored when they're coming to Canada. A lot more time went into it than I think we initially thought when we got into the design assist arrangement. So it ultimately ended up being to our benefit and to the project's benefit, but I guess the point I'm making is you have the benefit of greater visibility in your supply chain, but with that comes the added complexity of putting arrangements in place that protects your interest when you are making payment overseas and the materials remain overseas. You have to also think about that. And we did engage local counsel in those jurisdictions to make sure that what we were paying for was protected before it arrived here for fabrication and ultimate storage in Canada.
So one of the things we did here also to mitigate the impact on construction schedule is that we're storing a lot of these. So what story are we at right now? So
we're, in terms of structure, we're just coming at the ground floor with our structure, but we already have up to level 27 fabricated and sitting in storage here in Hamilton, actually, ready to deliver to site. So that was another big kind of risk mitigation factor that we took into consideration. And so, up to level 27, like I said, structure only at ground floor, but facade level 27 already.
So we're storing it basically on close to site, not relying on the overseas storages, so that could be a challenge later on.
Exactly.
So
exactly
this
right.
is an interesting, sorry. Okay, so this is another project that I worked on 76 Adelaide, and this one has curved glass that was procured from Spain, and the challenges that came with that is that mid-construction, the company or the supplier went bankrupt. So luckily we had those in storage close enough, as you said, and this is really where we kind of learned our lessons, and you need to mitigate that, in the next project. So. But Jerry, you had a similar issue in a big house, a little house that with the same challenges. So tell us about that.
Well, there are about 25 large units like this, triple glazed, very thick. They were designed to have no vertical mullions, and so it's entirely wind load, held at the top and the bottom. So it made for a massive unit that weighs about 30 pounds a square foot. And 25 of these units were shipped from Spain. This is really at the time when COVID is starting to get serious, and 5 of them were broken. in addition to that, this is just the design, but that unit that you see lifting the glazing into place is the only one of its kind in North America that could be cantilevered on a crane underneath a big concrete overhang with approximately a ½ an inch tolerance. But anyway, the issue is the shipping, as we were discussing, is that the issue is that these things break. And 5 of them were cracked when they arrived on site with that very expensive rental machine and COVID.
And then you had to basically wait for delivery. How long was that? A few months?
We started installing these 25 units, and they were going at the rate of about 1 a day in October. But you see here, that's not October. The wait for the new glass, not even up there does it look like that in October. It took until about shortly after Christmas to get all those installed while renting that machine for the whole time. Instead of 2 weeks, it was about 3 months.
Interesting. So moving on from time management and design assist, thinking about the quality control. So one of the challenges as architects that we have is shop drawings review. So we design all these great facades and all those complexities, and we find a manufacturer, and then we need to review the shop drawing. So Jerry, why don't you tell us about this one?
Well, these 2 towers at the corner of Bremner and I guess near the bottom of the city, and 2 of them, there are 57 and 67 stories tall, which is fairly big for 15 years ago. When the bidding went out for the glazing, the company that won the bid was a Chinese company that promised us to do the entire building in curtain wall at the budget of window wall. And so the client was hard pressed to turn that down, as you might imagine, many millions of dollars. And so the process started. And what we found was that because the manufacturers were not local and they were eager to get into the North American market, what happened was that when shop drawings started to come in, and the shop drawing book was like this for a project that size, these aren't regularly shaped towers, and we had to review the shop drawings for at least a year because there were always gaps in Canadian standards of engineering, Canadian code issues that had not been made clear to them, or they had not accepted. They just continually revised a bit of the drawings, sent them back, and so the poor person reviewing the shop drawings was occupied for about a year to make this thing finally happen. That's a real problem. That is a terrible stress on the fees as well as anything else.
And Jerry, but eventually they do meet all standards, the ASTM, CSA, et cetera. We all...
On about the 8th try, yes.
Eventually. So talking about QA/QC and meeting local standards, Dustin, tell us about the QA/QC processes that you're employing in your facility and in your processes.
Yes, QA/QC is one of the top priority when we export our product overseas. Given the distance involved, different in products, standard cost and language barrier. Moreover, with 100, if not 1,000 companies competing your business, it having different level of capability and quality focus is challenging to determine which one is suitable for your project. However, I argue that's why there is significant gap between the best and worst. The best and worst manufacturing overseas isn't the same with it was 10 years ago. At Beam Window, we have we have comprehensive quality management program in place that reflect the expectation of our international clientele. Before, let me share about our quality control process. Before the manufacturing begins, we develop technical plans and processing solution for each project. Our team of engineers and experts carefully review the project technical document. Following this, we invite the project developer, also international experts, to our factory in Vietnam, to our facility in Vietnam, for in-depth, carefully discussion and critics of the solution and document, as well as evaluation of our factory, our workforce, also technical capability. We then establish a specific quality control process, as you can see on the screen, developed by our international expert and approved by design consultant. With the complex project, we create detailed tutorial video for each production step. Can you play?
Yeah, it's right here.
The video shows how our worker examine the panel. Additionally, we also conduct continuous training based on our QA/QC inspection. And during PMU, we hold morning meeting with our worker to get update and feedback any from the project team.
Todd, you...
And our QA/QC.
Yeah, go ahead. Sorry.
Yeah.
Sorry, keep going. Sorry.
Yeah, our QA/QC team work along with a third-party inspector chosen by our client to ensure top quality standards. This collaboration and international teamwork drive big window success. From material inspection and product monitoring to the final project before we ship it. And the last thing is things go wrong. This is fact of life. The crucial question is not what if something goes wrong, but what happened when it's there. There are many strategies here. The key is the forward planning, clear directive, and proactive implementation. SB window is very important to select our team member based on the core value of sincerity, responsibility, and quality. Yeah, I'm sorry, the video is not follow
it's
my...
longer than, doesn't follow us, our...
Yeah,
okay.
this is a PMU we make before we mass application.
So I think, Todd, you worked with Dustin before, and you have the experience also of seeing this in action. So we know the philosophy about QA/QC, we've seen all those flow charts, but how does that really work in reality?
Well, when we went to this and we knew it was going to be foreign sourced, we developed a pretty extensive program with the contractors we were working with, to review potential bidders from overseas, review everything from their financials through their capability and production, to make sure we knew who we were dealing with. I've been lucky enough to be working with BM for the last year on the project here. And, we provided them with a very extensive package from all the project specifications, drawings, all the test requirements, everything, to meet the architectural requirements from, Giles Robinson and Foster's and Core, and to make sure that they understood exactly what we were expecting from them. It also included the quality program.
Mm-hmm.
It also included using a third-party production monitoring. A friend of mine, Frank, is that I've been working with since 2007. And we provided a lot of support and a little extra look because, for example, the project that we were involved with was very technically challenging. Mm-hmm. And it required you pay a lot of attention to detail. And we couldn't just allow just luck to have it. So we had a lot of people watching and a lot of people helping. We also did a lot of things in advance. We created a schedule, which actually BM is following, which is also following our construction schedule. And we even talk about lead time. So, for example, BM right now is about 5 or 6 floors ahead of installation with material on site. We believe that's very important. In production, they're much further ahead, but it takes 6 weeks for material to get from Vietnam to Toronto.
So how does the third-party assistance help, works? Is it over there, overseas, or does it happen here?
Oh, no. So they're like our eyes and ears in NBM's factory. We have people there every day, provide daily reports of what's being done.
I see.
Checking all the processes, just keeping an extra eye, in addition to BM's quality processes. And just to make sure everything is going according to plan. And also mentioning if they find a problem or any issue, make sure it was resolved. It's very comforting when you're dealing with somebody overseas to know what's happening every day. It can sometimes be a tall order, but you want to make sure. It would be very unrealistic to expect production on a very complex project to have no issues whatsoever.
Yeah.
But if you know about them right away and you can deal with them quickly, and also the production monitoring company is very helpful in that way to make sure things kept moving and the quality was as required and as specified, in many ways exceeding it. And we have to meet all our requirements for people like Dow for the structural glazing warranty. We have a lot of requirements on the project, and as he showed the PMU, which was done, and we did that in conjunction with our partners on the project. In fact, Bass Installations was there to help us out, so that we tried to keep it as intended and as planned and designed since the start, and it was very helpful.
So one of the things we started with is that a lot of it is driven by cost. So, the reason we do overseas procurement is because we're able to find the right product for the right price, and we manage to put together systems that allow us to overcome delivery challenges and other challenges. But the more we talk about it, the more we're hearing about more cost that goes with it, whether it's a third party, boots on the ground that tells you what's going on there, or long-term facilities, storage, up to a 27th floor. Can only imagine the size of that facility and the cost of that. I'm going to ask the question for you, Andrea, in terms of cost analysis. At the end of the day, do we really save a lot of money doing that?
Yeah, I mean, in our experience, yes. We have seen significant savings, so we think that it's something that we'll continue to have to manage as we go along with it. And you see shipping disruptions, and even I think we're waiting on understanding whether or not there'll be a rail strike happening out of ports in Montreal. Like these become more important for us to consider as the overseas procurement becomes more commonplace, or more commonplace, I think what we're seeing is, we're willing to, we want the lower cost, and so we're having to put in place, like you said, those structures or parameters to manage that, and it's just becoming more common in our operating procedures to make sure that we are equipped to manage it as it comes. And it's the nature of the market right now. From our perspective, is that cost seems to be driving a lot.
I think it's actually amazing how many things we all put in place, from the architect to the construction manager to the consultant to the fabricator to make this happen. So one of the things sorry, go ahead.
Come back the first question. I would like to share something about how to break into our capacity. Would you like to hear that? We are the facade fabricator for the biggest project in Toronto now. We're lucky about that. But besides that, our investment in cutting edge technology and skill staff enable us to achieve the highest quality standards. And our factory are equipped with Alumatech machine from Germany, and we have received the list silver certificate. So that's we try to enhance our quality control procedure to ensure we deliver the top tier product for our customer. And at buildingenvelope, we value our employees by nurturing talent, fostering a collaborative and inclusive culture, and driving innovation. Moreover, we collaborated closely with reputable Canadian consultant firms and quality control agency. Our robust partnership with Atlas Facade, a key player in Canadian markets, ensure our system design and fabricator process meets on local cost and performance standards, as Mr. Todd just said. And at buildingenvelope, we our dedication to our motto, sincerity, quality, and responsibility drives everything we do, regardless of geographical distance or the complex of the projects. We always try to deliver top-notch results with integrity and reliability. Thank you for more sharing. Thank you very much.
Thank you. And just to, before we wrap up, what we see on the image here is a visual mock-up that you had in your facility. And I think I wanted to, maybe before we finish, talk about a little bit about mock-ups. We all use that as a QA/QC method, and we have two types of mock-ups. We have the visual mock-ups and we have the performance mock-up. Todd, let's talk a little bit about the difference between the two, why we do one here, one there, and
definitely we like to do the visual mock-up near the site because you want to get as many team members involved to review it, make sure it meets everybody's expectations. Usually that's where you're first seeing the finishes at large scale and the lines. You actually get to see something. So generally, we do that very close to the site. The performance mock-ups, however, I like to suggest doing them close to the facility doing the manufacturing. The main reason is it reduces time doing the performance mock-up because of shipping, but also should something happen, like a piece of glass get broken, something get damaged, or should there be an issue, you have very close direct control to get replacement materials and to correct it, because time is money. And if you have a PMU and you have a problem, you're spending the owner's money and you want to get it fixed quickly. So for that reason, For example, the mock-up that we did in Vietnam, about 10 kilometers away from their factory at an accredited facility that was reviewed and approved by the project team and the consultant beforehand.
Yeah, I think for One Delisle, we had to go to Miami simply because of the qualification of the type of test we wanted to do.
Yeah.
And then we did the visual mock-up on site. As you said, you know, you want to get all stakeholders to be able to see that. We are at the end of our panel, so I just wanted to thank everyone for joining me. It was great and interesting as I expected. I hope everybody here enjoyed it. Thank you very much for your time.
Thank you very much. That was great. Okay, this is it, folks. What a day. That was a lot of fun. Hope you learned a lot. I certainly did. I always get really pumped when I go to these events, and then I go to work tomorrow and I check my email and I forget everything. So before you go and refresh yourself and enjoy the after-event festivities, please just think for 1 minute of one thing you're going to do tomorrow to maintain the momentum from today. So a follow-up with a contact that you made, sharing something you learned with your project team, reaching out to a distributor or a manufacturer that you learned a little bit more about. Just one thing, and do it tomorrow, not next week, because you won't do it next week, trust me. And with that, thank you very much. This was a lot of fun.
Okay. Hello. Yeah. Thank you. So just before we wrap up, a round of applause for Luka. I think he expertly moderated the panel. Thank you, Luka. I hope all of you enjoyed today's event. We had a different set of speakers speaking from last time around with new topics. And until we return next time around, I hope you all have a great time. And as I said this morning, those who have given us permission to share their presentation with you, we'll share a YouTube link of all the recording from today, along with the feedback form. Please do fill that up, and you can watch the recording. Can I have the speakers of this last session on stage? And can we have someone from Rainers on stage? We'll finish the photo opportunity and then meet you for the post-event reception outside. Thank you.